ever want to build a search engine from scratch in the era of ChatGPT? Like, why even bother calculating term frequencies and vector embeddings manually when you can just dump everything into the context window and call it a day? Okay, I know everyone and their dog is an AI engineer these days because they know how to write a prompt, but in this course, and specifically in the pipeline that we're going to build in this course, it's what separates the prompt engineers from the actual AI engineers. Isaac Flath has over a decade of experience in machine learning, and he's designed this course to not just teach you the basics of AI augmented search, but really all the fundamentals of modern search engines from the ground up. But before I dump you right into the glorious math of high-dimensional vector spaces, let me give you a bit of a teaser about what's going on here, considering this is quite the deep dive. You're gonna learn all about search and retrieval augmented generation, or RAG, but we aren't just gluing libraries together. We're going to build a lot of this stuff from scratch in Python so that you can understand it at a deeper level, which is something that actual AI engineers that are actually earning money doing this stuff in 2026 need to know. We'll start off exactly the way you should start off learning about search, and that's by ignoring LLMs entirely. Isaac's gonna take you back to the roots with pre-processing and TF-IDF. You'll learn how to clean raw text and build inverted indexes. You'll basically be building the technology that powered the internet back before neural networks were talked about by business executives. You'll actually write the code to rank documents based on keyword density using algorithms like BM25. And only then will we introduce you to the more modern stuff like semantic search. We'll move away from just matching keywords and start actually using embeddings and vectors to find documents based on meaning, not just matching tokens. Then Isaac is gonna cover chunking strategies because how you slice the data really matters when it comes to finding relevant results. And then we'll get to hybrid search, where we blend old school keyword scores with new school vector scores to get the best of both worlds. And once we have retrieval down, we'll look at re-ranking and evaluation to surface the absolute best results. And finally, augmented generation, where we combine our retrieved context with the Gemini API, the LLM, to synthesize grounded, accurate answers. As a bonus, we'll even get into some of the bleeding edge stuff like agentic workflows, where autonomous agents can refine their own queries, and multimodal RAG, where we extend our system to actually understand images alongside text. Now, I do not recommend sitting down and binging this course all in one sitting. Get your hands on the keyboard and actually follow along. In fact, do one better. Make a boot dev account, it's free, and actually go ahead of Isaac. Implement the search logic yourself, and only then watch him go through that same lesson so that you can do his approach and understand his commentary and his solutions only after you've had a chance to experiment for yourself. Now, as you probably know by now, all the content in this YouTube video and frankly, all the content on boot.dev is totally free. That said, all of the interactive features on boot dev are paid. So if you want to be able to submit your own assignments, view solutions, chat with boots, get a certificate of completion, and all that kind of stuff, you'll need a membership for that. And if you do want a membership, just use Isaac's code, Isaac, to get 25% off your first year if you choose an annual plan. And part of your payment will also go directly to Isaac to help support him and his content. One important side note here, we'll be using Gemini's free tier for this course. And at the time of recording, that should work just fine, but Gemini has been making a lot of changes to their billing structure. So there is a chance that by the time you're watching this, you might need to hook up a credit card, but don't worry, you won't need more than a single dollar's worth of credits to complete this course on a paid tier if for some reason you're unable to use the free tier. And one last note, the only reason we can put our time and resources into creating these free courses is due to your support. So please like and subscribe to our channel here on YouTube. It just takes a second. It allows us to produce more and more of these long form video courses and release them for free. So thanks for doing that. Now, let's write some Python code with Isaac.
Hi, I'm Isaac. I'm going to be covering the Retrieval Augmented Generation course, walking through the whole thing. Pretty excited for this because Retrieval is everywhere. Agents use it, most products use it that have AI integration, and these are the fundamentals you need. So let's jump straight into it. First thing we need to do is install the boot.dev CLI. This is a pretty important step because when you're working with things in the AI realm, it's very easy to get a number that looks plausible, because how would you know if a very large decimal is the right decimal or not? That's just slightly wrong. And so this lets us test and make sure we actually did it properly. So let's follow the instructions. We need to install. I already have it installed, so it'll look a little different. To install the boot.dev CLI, I can take these instructions. We can log in to boot.dev with this. Don't mind the messy desktop. I'm logged in successfully. The next thing we need to do is run and submit. Over here on the right of our boot.dev lesson, we'll have run commands for a lot of lessons, and this does a submission for us. Let's do this. So our run command without the -s is going to run it locally so we can see the output. It's RAG, not AI slop. No one wants AI slop. We got the expected output. So this describes the expected output that we're supposed to see. We got that. So let's go ahead and submit and see if we got that in all the edge cases. So we passed. We can move on to the next lesson. What is search? Imagine trying to find a movie on Netflix by scrolling through every single movie. Search is non-negotiable anytime you have more than just a few items. But search algorithms have gotten way better with AI. You may have noticed. Keyword matching used to be the standard. Now it's the bare minimum. Users want search that understands meaning, context, and intent. That's where RAG comes in. Retrieve information. Augment an AI prompt with that information. Generate a response with all of that context. You've probably noticed that when you Google something these days, you don't have to type in exactly the right words, which is what basic keyword search requires. You can have typos and use synonyms because Google supports semantic search as well. If I type in movie about the lunar landing, I get back fly me to the moon and Apollo 11, even though I didn't use those exact words. And RAG, or context engineering, that's the next step after semantic search. It's bringing modern AI into search. So search and retrieval kind of go hand in hand. They're the same thing. It's really one of the most fundamental pieces for using AI, or really almost any software. Usually, to solve any problem, there's more information than you could possibly fit. And so you have to pick and choose what you include or exclude. A lot of times coding agents do this with an agentic search, like a file system search. This course is going to be covering semantic and keyword search. That's been used, Cursor is a big coding agent. They've been having a lot of luck with using semantic search for large enterprise scale code bases. That's been there, and that's kind of been making a resurgence with some of the work that's being done. You need to be able to find information. If you go through Netflix, you don't want to scroll through every movie. You have to pick them. And RAG is about using this retrieval and this search inside of some sort of LLM response. So you type in a query. You get a bunch of relevant documents. This might be movies, it might be files, it might be code, it might be whatever. You put that into an LLM prompt, some sort of prompt, and then you get a response. And so the response is smarter because it has actual relevant information like right there. You've told it what is important. So you get much better results, fewer hallucinations, much more accurate. So we're going to build, in the true boot.dev style, build a real project. So we're going to build this product called Hoopla. It's a Netflix-like streaming service, building the search bar out. We need the movie data to go through, and we need a Python environment. We need to be able to run code. So let's do this. So we're going to use UV. Here's the installation docs. You can go there and install it. I've already got it installed, so I'm not going to worry about it. And you can run these commands to initialize the project. That's going to create like a PyProject toml and some other files. And we can see now we have this RAG search engine folder with a whole bunch of files. I'm going to go ahead and open VS Code there and use that instead. Don't judge me for that desktop. It's a little messy. So now that we've initialized, we've got a few files that auto created for us. So we initialized it. We have a git ignore. These are just files we don't want to push into GitHub, that are not important or could have secrets. We have a file that dictates the Python version. This is just a dummy app to show how you can build using this environment. We have a PyProject toml, which has some basic information. There's a lot that can go in here, but the name of the project, the version, what Python version, and this will be any dependencies that we use along the way, and then an empty README. So we've got the core parts of our project. So we need to create a virtual environment at the top level of our directory. Let's go ahead and do this. UV Vim. We can see we now have our virtual environment. We want to make sure it's in the get ignore, and we want to activate the environment. If you use Python a lot, I recommend making an alias for this because it's just a pain to type it all the time. I have mine to SV, which is exactly the same thing. Source vim bin activate, just a pain to type. So you create an alias for that. All right, so we need to create the data directory in your project root. We need to download the movies data set, and we need to add this data. We don't want to push the large data file to version control. Good, so let's do that. So we want to make the data directory. We want to open this up somewhere. Great. We can write to an app.file, and we can write this to, was it movies.json? That was not what I wanted. I don't think it worked. Okay, so let's see. What did I do wrong here? Wrong capitalization. Great. Okay, so we got our movies.json there. Let's just open it up so we can see what's in here. Yeah, we see a JSON file. So there's the movies, and in here we've got each of our movie titles. All right, so we got a whole bunch of movies. Great. So perfect. We wanted to add this to our getIgnore file. So we can do this. We can see it's grayed out. We're good to go. And I think that might have been the last step to go. We can run, verify we've got everything we'd like. Perfect. Let's go ahead and submit. We passed. We can move on to the next lesson. Okay, next we need to start creating. We got our data. We need to start creating the product. So we're going to build it as a command line script, a CLI, so that we can play with it. Typically, when you're building, I would recommend starting with a CLI. It's nice and easy to change and experiment, play around with, and then when you have something that you think is worth integrating in, move it to integrate with whatever more complicated thing you have. So let's do it. Okay, so we're going to create a CLI directory. We're going to get rid of the main py file. We don't need it. In the CLI directory, we're going to create a new file called keyword search and paste in this code. So we can make our CLI. We can go into this. We needed to create a keyword search.py, paste that in. Let's go ahead and see what this is. It's a Python script. We're going to take some commands, run a search command. We can see the search command doesn't do anything yet. That's going to be our job to implement. So we can run this with our command. I named the file wrong, so that's good. The tests will be looking for the exact file, so we do need to be precise in this. I'll have a little bit more flexibility. And so this is why copying is a good idea. Copy, paste. So we ran it, we didn't get an error, doesn't do anything as we saw. Update the search query to print this. We also need to delete the main py, so let's do that. We needed to print this. Okay, hang on a second. Let me figure out how to disable this tab completion. We are trying to learn here. Okay, so we can print. We can use a formatting string. All right, okay, so we still got something here. Okay, great. So now we print that out just like it said we should. Let's see if we get that. Searching for your search query. Okay. So I think we're in good shape to run the thing, see if we've got it working. So we ran this, we ran our run command, we got searching for Boots the Bear. We are expecting to get searching for Boots the Bear. So let's go ahead and submit, and we passed. So we're good to go to the next lesson. Okay, we're ready to start implementing search. We're going to start with basic search, focusing on keyword search. It is considered basic. It's been around a long time, but it's still actually used in almost all like modern high-end search systems. The reason for that is because when you're looking for really precise terms, nothing beats keyword search. If a doctor is searching for COVID-19 because they have a patient that has COVID-19. They don't want respiratory viruses in general or pandemic diseases, things that are semantically related to it. They want documents that say that particular condition. On the other hand, it doesn't do everything. If you were searching for alien movie, you would want something that says invaders from Mars, even though it doesn't specifically say the word alien in it. So you need both. We're going to start with the keyword search, build that up. Throughout the course, we'll build in hybrid search to include semantic search and re-rankers and LLMs and all kinds of stuff. So let's make it really work. There's a million ways to do this. You can use a functional style. You can use lots of things. I'm going to build it one way, but you should feel free to have the creativity to try coding it however you'd like. So we need to load the movies. That makes sense. We're going to iterate over all the movies. If the title contains the search query, we'll append it, print the results. Great. We'll truncate the list. So I'm going to do this a little out of order. I'm going to start with the printing of the results and then work backwards from there. We already print this. I know I need to print that. So I need some sort of results. I don't know what that is yet. And I know from this, I need an index 1, 2, and 3, and then I need the title. We can say the index and a result in our results. So enumerate. Enumerate basically just loops through it and gives you the index location as it loops through it. And so then we'll have this f string where we give the index location, and we probably want something like result.title or something like that. Okay, so that's what we need. We could implement it in line or implement it above. That's going to get messy, because if it was just this one thing and I knew I was only going to need to do a perfect text search, I might, but it's going to get bigger. So let's just build it right from the beginning. So we're going to create a small lib folder. Oop, I already got a lib folder. Inside that, I want to create a keyword search pi. I'm going to go ahead. I'm going to clear all pi cache. I have a remove pi cache alias as well. If you're curious, it kind of does this. It's kind of another handy thing if you work with Python a lot to be able to quickly get rid of all of them if you need to. Okay, so we also need to load the movies. That doesn't sound like to me like it's something specific to keyword search. Any kind of search, we're always going to need to load the data. Let's create a search utilities file, and we can't search until we load it. So let's start there. So we're gonna do this. We need the project root. We're gonna need the data path. We're gonna need a function to load the movies, and I think that's about it. Yeah. Okay. So let's deal with paths first. The most common way that people use is they do like this OS library. I'm a fan of the path object. I think it's just a little bit nicer. So I'm going to use that. Let's do our path, and we want the path to start from our current file. So we have a consistent thing. We can make sure that that resolves. And we don't want the current file. We want to go, we're in this directory, we're going to go up to CLI. So in lib, we want to up to CLI up here so we can get up to the data. So we could do .parent.parent, but we could do a little bit of a shortcut. So that's our project root. And our data path then is going to be project root into the data into our movies.json. Now that we've got that, we can go ahead and use the JSON library. So we want to open our data path. That's going to be God, these pop-ups are really aggressive today. In read-only mode, I'm not going to trudge around settings to figure that out, but okay. We go json.load. We need to load the file. We can return the data, but let's go take a look at the format of the data. Yes, so we could return it and we get a dictionary with just movies in it, but the only thing that's in it is this list. And so I'd rather just return the list. I think that'd just be a little bit cleaner. So we're just going to index into it here. And so this is going to return a list of dictionaries. So we can load our movies. In theory, that works. Let's go to the keyword search. We need some sort of search command. We definitely need to pass in a query because how else is it going to search? We definitely need to use our load movies function. We need the data. So we could say from lib import load movies. So this is going to be from lib.searchutils. We're going to import the load movies. Okay, so we've got the movies. Let's go back to our assignment. So I loaded this. Great. Iterate over all movies. Okay, so we can use a filter or a loop or a lot of things. I'm going to use a loop. Print the results in this format. We kind of did that. And we only want 5 results. So what I'm going to do, I'm just going to say in results. Call it top K, in. K means a lot of things, so I'm just going to say, let's just call it top results. Well, we'll call it in results. Okay, so we go data equals load movies. We can say for movie in the data. So for each one, we're going to go through. If we go back to our data, that's going to be one of these. I'm going to call this movies, actually, just for consistency. Load movies, loads movies, and we iterate through each movie. And we wanted to see if query is in the title. So we could say if query is in movie title, then we can go res.append the movie. Okay, so then we have all the movies. We can say if the length of our results is, once we get to end results, then we can break out of the loop and we can then return our results. So we could return here and return here. I think this is just a little simpler. The other thing we could do is we could make all this a list comprehension. I don't think it'd be terrible for something, this small, but it might get more complicated later, and I don't want to deal with it. So I'm going to keep it as a loop. We need to go into our CLI because we actually need to use this. So in theory, we go search command and we run our args.query through it with our limit of 5 that it said. And we can say from lib keyword search, import our search command. In theory, that works. Oh, maximum of 5 result order by IDs ascending. Okay, I don't think I did that. I just stopped here. So we actually need to get, oh, actually this will work. Now, this is something that you might have to think about when you're actually implementing it, because the IDs are in order, in ascending order. So I could take the first 5. Do you always want to guarantee that they are always going to be in order? You could build it to grab all of them and then sort it after, so that if the data shape changes, you don't have to worry about it. I'm not going to change the shape. So I think that'll work. So let's go ahead and run our run command. This will run these two and we'll see what we get back. All right, we got back the Great Valley Adventure, the first great train robbery. That seems to check out. Failed to spawn. All right, so let's see what is going on here. So we got the output, but we're getting an error as well. Oh, that's just the expected output. Okay, I see. Failed to spawn. No such file or directory. Okay. So if I look, I'm actually in the wrong place. So I need to be at the root of the project. Dict attribute has no title. That makes sense because if I go, I need to index in here. We could make a data structure so that the dot notation works. It's kind of nice, but I think it's a little overkill for where we're at. Okay, first great train robbery. What do we have? The Great Valley and the first great train robbery. The Great Valley and the first great train robbery. Okay, so I think we're in good shape. Let's go ahead and do the -s version to submit this and see if we pass. All right, this is perfect. Great, we can do an exact search. That's nice. There's a lot of edge cases that wouldn't go well, so let's start fixing those. Normally, if we search for the alien, we'd want it to match alien or aliens. We don't really want to say this is not a match for those because the title is different or it's not plural. And in fact, in more cases, there's lots of them. So like case sensitivity, typically for keyword search, we don't want that to be a match. We don't want punctuation to cause an issue. If I type in, I want a great sci-fi movie, I don't want that not to match this because there's an exclamation point, great exclamation point. So I can't just work on queries, I have to deal with punctuation. Tokenization, I do want to match on words. If I say amazingly great Matrix movie, I would want that to match this because it's got 3 and the 3 most important words, even though they're in different orders and all that. So we want to break it down at the word level. There's words that don't add any value that we can just remove. Right now, we'll just remove them so there's just less junk for us to sift through. Eventually, it's actually a part of the BM25 algorithm that we're building up to over the course of a few chapters, and we'll see a little bit more about that later. The fact that the is in here, or is not that important, so we might want to remove those stop words. And then finally, we want to do stimming or limmatization. A good example here. So if you'd say like run, ran, running, all of those kind of match to the same word, and we'd want to take care of that. So let's start. We're going to do one thing at a time, and we're just going to do lowercase. So we're going to match to lowercase, update matching logic to dot lowercase or wrote the search query and the movie title before comparing them. There's a few things we could do. I could change this to lowercase here. I don't really want to do that. I want to go into here and say, here's the query. Let's just create like some sort of like clean text function. And for now, it's just going to do something very simple because we just looked and saw that we're going to want to do quite a bit. So it's a little silly to make this function. Actually, let's just, you know what, I'm just going to count it out. Well, let's not over-engineer things too early. So we want to lowercase this and we want to lowercase that. We can just do that. Pin the movie, we're good to go. We will create a function when and if it makes sense rather than doing it too early. Okay, so we got searching for country, no country for all men. Okay, so we saw lowercase, it matched to uppercase. That's great. Let's make sure we've got the right results, but I'm just gonna go ahead and submit. Okay, great. We got lowercase. One more down. Let's jump over to the next thing. Okay, so the next thing after the capitalization is punctuation. So let's take care of that. We want Boots the Bear, exclamation point, to strip out the exclamation point, or the wonderful bear comma boots, we want to strip that out. So we want to strip it out everywhere. There's some edge cases there. We're not going to worry about them. We're just going to implement the simple version here first. Okay, here's some standard library functions to use, but let's go ahead and do this. So now I actually do want to extract this out into a function because I have more than one thing. We'll uncomment what I just did there, move this out. I can take my query and I can clean the text, and I can clean the text of the movie title as it goes. So that should work exactly the same. You can lowercase it. Now we need to remove the punctuation, and then we can return the text. So what do we need to do? In the standard library, there's this thing for string punctuation. So let's take a look. Go into Python. We can say import string, and we can see what string.punctuation is. Conveniently, it's got all the punctuation. So we can use that to remove them all. So to import string, so we know we're going to need the string.punctuation. Let's see, what do we want here? Let's go back and look here. We want to use the .translate method. We already looked at punctuation. Okay, so what does this do? Returns a copy of the string with each character has been mapped through the given translation table. Great. Now I want to translate all of the string.punctuation things to be nothing, just to remove them. So that's good. Make trans, this makes the translation table it needs. There is 2 arguments. 1 argument, it must be a dictionary mapping. I'd rather not do that. There are 2 arguments, and in the resulting dictionary, each character in the from will be matched to the character in the same position as 2. If there is a 3rd argument, it must be a string whose characters will be mapped to none in the result. So that sounds exactly what I want to do. I want to map all the characters in the 3rd argument to none in the result. So let's do that. So we had text.translate, which takes a translation table, which is make trans that we just looked at. We wanted to map, just gonna get rid of this. We said if the 3rd argument is there, it's going to map all the characters from this 3rd argument to none. And so that should do it. So this is gonna clean it from here, it's gonna clean it from there. And I believe that should be all we need. So let's go ahead, we'll run our test, and I should see it's magic Charlie Brown. It's magic Charlie Brown. Very good. So let's go ahead and submit, and we get one more edge case handled. Great. All right. Very good. Tokenization is splitting them into pieces called tokens. Word-based tokenization means you're splitting it into words. There's lots of tokenization methods for different types of algorithms. You know, a lot of times for retrieval, we're using word-based or very similar to word-based. For LLMs, often they're subword tokens, or even some are character level. Like if you want a model that does really well at languages like Chinese, a lot of times there's individual character level tokens instead of word-based. Different algorithms have different kind of tokenizations. For keyword search, we're going to do this word-based tokenization, but be aware there's lots of different ways of tokenizing. So we want to split the query into titles and tokens, and then we want to update the magic logic to allow matches where at least one token from the query matches any part of a token from the title. Oh yeah, any part of a token from the title. So let's go ahead and work on this. We've already cleaned the text, so we probably want something to tokenize the text. We could add it in here. It feels like a little bit of a different thing. We might want to clean text without splitting it up. So I'm going to create it different. So tokenize text. We get the text. The first thing we want to do is we want to clean the text. So we can do that. We'll of course want to tokenize this. Ooh, that's probably going to change a little bit. Okay, so let's leave that alone for now. The core of this is this logic. So let's just work on that first. So we can say tokens. How do we get the tokens? Well, text.split. And we can then return the tokens. So that should split on white space. I believe that should work, but we said we only wanted ones that are there. So we can say basically token for token if token. You can do this with a for loop. I did it with list comprehension because it's basically just a loop with that. Seems simple enough. Okay, so we took care of that. So now we need to be able to compare the query to the document, say, has some matching token. Okay, so we have the query and we have the document movie tokens, basically. So we want this to be a Boolean. So we want a function that tells us, given these two things, are they a match or not? So I know I need to go through each query tokens. And the reason I know that is because I say at least one token from the query. So that tells me I have to iterate through it somehow. And then I have to any part of a token from the title, which means I'm going to probably have to iterate through those as well. So I can say for query token in query tokes. Now I know I need to go through for movie token in movie tokes. So now I have every unique combination. What is this complaining about? It's complaining that okay, fine, I'll spell it out. Okay, so I have every combination. And so then now I need to say if the query token is in the movie token. So, okay, so I have every combination. So if any of the query tokens is in any of the movie tokens, so it's not an exact match, it's not an equality, it's a contains, then I know I have a matching token. If I get through all of this and I haven't exited, then I know I don't. Does that make sense? Okay, yes, I think it does. So I have the search command. I've cleaned the text query. Really, what I need to do is I need to tokenize it. So I have my query tokens. I go through this, and I'm going to say, if we have a matching token between my query tokens and my movie tokens, so I need my movie tokens, then I want to append the movie. So how do I get movie tokens? Well, I need to tokenize it with our tokenization function we had. We had tokenized text, and we're tokenizing the title right now, if I remember right. And once we get to the results, then we break. Okay, so let's think about this. We split it, we removed it, we did the matching logic. Okay, let's test it. I'm not completely confident. There's a good chance I did some bugs, but let's try it. Furious 7, Fast and Furious. Very good. All right, first try. So that's very good. So let's recap what just happened here. We cleaned the text. We tokenized it by splitting. This if token says only if it's not none-like an empty string would be none-like, so that filters those out. This is going to go through every combination of query tokens and movie tokens as I loop through both of them. And if any of the query tokens is a part of any of the movie tokens, it's going to say it matches. And that's what we do. We go through every movies and we say, hey, look, if any of the query tokens is a match, if this query tokens was a match for these movie tokens, then we're going to append it and go up to the limit. So that makes sense. So let's go ahead and submit and see how we do. All tests passed. So very nice. We're cruising right along. Okay, stop words. So the next edge case we need to take care of are tokens and words that aren't useful for search. There's many of these. Some of the common ones, for example, are a, the, is, of, in, and these don't really mean anything. For example, if you have the Terminator, you don't want this to match the bear because the matches the, like that doesn't tell us anything about the movie. It doesn't add any value. It's just a stop word. It's a filler word. And so we can fix this edge case by just removing stop words. And that's very common to do in keyword search, at least. So we're going to go ahead and get rid of a bunch of those stop words. There's a whole bunch of ways to do this. Okay, so we can create a new file with stop words, and we're going to paste words at the end. So we've got a list of a bunch of stop words. You can look through them, but they don't mean a whole lot. We're going to read the stop words from a file and store them in a list. Remove any stop words from the user query tokens in the title before the matching logic. Let's get to it. So I'm going to copy this. We're going to go to data stopwords.text. Let's go into our data stopwords.text, and we'll just paste that in. Great. So we've got 200 of these. We can go ahead and add this in. First, we need to load our stop words. I'm going to go ahead and put it here. I could put it in the keyword search file, but I've already got the data path here. Having one place that loads all of our data files, just knowing I go here seems clear. So I'm just going to say load stop words, and I can say with open, just like we have above, our data path. We can say our data is equal to lines. This returns a list of lines from the stream. And that's what we saw here. Every word's on its own line. So I'll go ahead and deal with that. And we can return that. So this should return a list. So stop words, unknown words. Okay, that's fine. Let's go into our keyword search and let's handle this. We're going to, in addition to importing load movies, we're going to load the stop words. And here, I guess we do it right after here. So we can say stop words is equal to our load stop words. Should have it. And so here, what we can do is we want to say if that exists and token not in stop words. This is where list comprehensions get a little annoying, is that like it's totally fine to just do a quick list comprehension. And now it's still okay-ish, but it's kind of annoying. So let's just fix this. So we can say for token in our split, we're going to say, I'm just going to make a little helper function here, which is, so if there's a, let's just pass in a token. So if the token is there and the token is not in stop words, we will return true. Otherwise, we will return false. So we have kind of made this simpler. If we add a third condition here eventually, then it starts being messy again, and we'll just refactor it. But for now, it's fine. So for token split, we'll say if we filter the token. So if this is true, meaning it is a token and it's not a stop word, then we can append that token. And then we can return our result. Does this belong here in its own function? I don't know, but it's fine for there for now. Maybe filter's not the best. Filter, yeah, I'll leave it for now. So we've got that. That happened to the tokenization. Let's go ahead and read this. So we created this stop words text. We read them in. We did a read and then a split lines to split it in a list of words. Okay, we did read lines, which kind of does that for us, I think. We'll find out. Remove any stop words from the user query and the tokens before the matching logic runs. And I believe we did that because we put it in the tokenization, which is called on both of these. Okay, so let's go ahead and give this a shot. So what is the result we're looking for? Hot potato, hotel chevalier, kill shot. Expected this. Okay. So this did not work. All right, so why did it not work? I'm just going to run this on its own and let's debug. Searching for the hot shot. So I'm guessing it's matching on the. So I'm guessing it did not actually remove this. So let's go ahead and just print out. Let's do some print statement debugging. So this should never have a stop word in it, but I bet you it does. It does. So let's go a little bit up the chain here. This should be a list. This will be a big output in the terminal. I don't care. That's fine. Okay. That was a little more than I expected. Okay. Print stop words. Load. So this is data. Oh, I see. That was a stupid bug. Stop words path. So what we need is so this is movies path and this is stop words path. And I'm going to do this. So we can do movies path is now data path movies.json. Stop words path is now data path / stop words dot text. I think data stop words dot text. Okay. So then I can update this to where this is instead of going movies path, that's gonna update movies path, and this is gonna update here. All right. This is printing a list. It's got new lines there, which I don't, really like, but let's just remove our print statements, see if it works, and if not, maybe we need to strip that out. Okay, let's make sure. So these results are definitely still not filtering out the, I think it's because of that new line character. So we need to remove that. So let's go ahead and say, I'm going to strip off that new line character. All right, what is its problem now? Okay, so we've got this. If this is true, meaning there is a token and the token's not in the stop words here, we're going to append this token.strip if that's the case. So this strip actually needs to be up here. So we need to get this off, clean this up, see how this works. This is not a clean way of doing it. Still not working. So one thing we could do is we could do the read and then the split lines. But I'm really curious as to why this is not working. So I'm going to go ahead and do this. Figure this out. Let's say if the is in a token, then let's print the token. And the reason I'm doing that is because I'm seeing these here, and I really want to figure out why they're in there. Let me just take a look here. I'm going to print it before and after, and I'm going to go ahead and remove other print statements. Okay, so this is here. So, okay, so that's here. Token is not in stop words. So this leads me to say, let's take a look at our search utils. Let's go ahead and print our data here. Can run again. Okay. Return a list of the lines. Hint can be specified. So what is strip do? So let's try this. Let's just try this read and data and then the split lines. And let's see if that does it. Yes, so it does. Okay, so I'm not stripping this off properly. So let's do this. Let's just use what it says. We'll accept that I'm a little silly for doing it this way. We can remove all our print statements debugging. We can double check that this still works. We can remove our print statement debugging. We can check that this works. Hot potato, hotel chevalier, kill shot. That's there. Okay, let's go ahead and submit. Great, stemming is next. We have a list of words, tokens, whatever you want to call them, and we want to reduce them to root form. So this is the idea, is that running, runs, ran, run, we want these all to match. Now, we've kind of solved some of this earlier where we said like, well, if we say run, let's just make sure that the resulting token has run in it rather than an exact match. And that matches run, runs, and running. However, it doesn't match ran. So English is kind of funny that way. And it doesn't match the other way. You know, running is not a subset of run. And so it misses most of the edge cases. You can see watching, watches, watches goes here, etc. Now, there's an infinite number of edge cases here. Typically, you use a solution that somebody else has built, and you can kind of think about it in this case where you can say, well, what if I remove the S from the end of words? Well, there's words that end with S that you can't remove that aren't plural. What if you remove the ing? Well, it's like, okay, you remove the ing and then you've got running. Maybe you say, well, let's remove the ning if in this case, but then you have an edge case of like string. Ing is part of the word and it ends with it. There's like these tense things where the spelling changes. There's just a whole bunch of edge cases. And so we're going to use a very popular NLP library called NLTK to handle it for us. This is, I believe, the first dependency we need to add. This is how you add them with UV. We're going to use this Porter stemmer in here. So let's talk about UV here. What we see is in PyProject TOML, that's where we said our dependencies would be. I have no dependencies here. When I add them, it does add a dependency here. So we can see, we can track all of our dependencies there. If we want to make sure it's installed, which it has, we can do UV sync and it will sync our PyProject TOML dependencies with our virtual environment. And so we can remove the virtual environment and re-add it if we need to. We got that. We want to import the Porter stemmer. This is a common type of stemmer based on a stemming algorithm created by a guy named Porter. So great. Or a person named Porter. I guess I don't know if it's a guy or girl. Let's see here. Okay, by someone named Porter. So here is the Porter stemmer. So we can import that. We need to create an instance. After removing the stop words from the tokens, we need to reduce each token to its root form. Keyword search. Okay, so after we've cleaned up the tokens, after we removed all the stop words, so we've done that here, we need to stem them. So let's do that. First, we need to import our Porter stemmer. We need to, we'll do Porter. That is a lovely, horrible name for it, but I'm going to deal with it for now. We can think about naming later. Oh, they gave us a better name for it. I'll just use that. So this is our stemmer. After removing the stop words from tokens, reduce each token to its root stemmed form using the stemmer.stem token. So we append, we can say, let's take our token and we can say stemmer.stem our token. And yeah, that gets appended. This is another reason why this loop is nice. We could have done multiple list comprehensions back to back. When you break it out often, you can remove several loops. So let's give this a shot. We can see we're looking for Virginia's run, take the money and run, woman on the run. Virginia's run. All right, so we've got this. This works perfect. Very good. And very good. We've passed. That's chapter 1. Awesome. Chapter 2 is next. All right, chapter 2. We are on inverted index. An inverted index is what makes things fast. So normally an index, you have some sort of location and you go to a value. So if you think about index location 2 would be 10. Index location 0 would be 1 in here. In this case, in a list, in this case, we have the value and we want to map to the location. So it's inverted. This gives us very fast lookup. It's kind of a way of caching things so we don't have to redo the operations and the creation of a bunch of stuff every time. So let's jump into it. We're going to create a new inverted index class, and it should have an index, a doc map, add documents, and a get documents method. Okay, so let's go ahead. We'll put that in here. So we're going to go ahead and do that. Let's see, did they give us any starter code for this or no? Nope. Okay, inverted index class. So we can put that here. Let's just put it up here near the top. So we're going to create our inverted index class. we know we need initialization, and we needed a index, a doc map. So this is going to map our documents, and we're going to need an index path and a doc map path. So let's go take a look at what this is. Okay, a dictionary mapping token to string sets the document IDs. Enter tokens to sets of document IDs. Okay, so we want a dictionary of sets. So what we can do is we can use from collections, import a default dict. Default dict is just a dictionary like normal, but it has a default value. So we can use our default dict and set that to be a set. So this is going to be a dictionary of sets at this point. The document map is going to map the document ID to the actual document. So that makes sense. And then we need a couple of paths. So we've been defining paths in our search utils. So let's create a cache path. We can set that in, let's do, I guess, project root / cache maybe. Doesn't really matter where we put it, but let's just put it there. So we can say cache path / index, and we can, try and see what this is going to be. Probably some sort of compressed file. And we can make this cache path / docmap.pickle, and we need to import this. So now we've got that set up at least. So let's look at our next set of instructions. Okay, so we have the index, we have the docmap attribute, we haven't done anything with it. An add documents method. So let's go ahead and create that. Get document method. Okay, a build method, and looks like a save method. Build and a save method. Okay, very good, very good. So I guess let's follow our instructions to see what we're supposed to do with each of these. Add document method. Tokenize the input text, then add each token to the index with the document ID. Okay, so we need to tokenize the text, and then we need to add each one to the index. Wait, add each token to the index with the document ID. So we actually need to go through the tokens for token and tokens. Let me just get this out of the way. Add each token, so that's the for loop, to the index for token in the set of tokens, because we want unique tokens. We now need to add to this. We get the token, and we're going to add the document ID. So what this is going to do, it's going to make this index be token to doc ID 1, doc ID 2, etc. We can look up a token and see all the documents that have that token, meaning we don't have to scan every single one. So that's good. A get documents method, it should get the set of document IDs for a given token and return them as a list. So we can say get document IDs. So we can go into our index for a particular token and return that as a list, because that should be a set, I believe. And this should work because this is a default dictionary. So if this term doesn't exist, it should be an empty set. Sorted in ascending order. All right, great. Okay, so that should be the get documents. I'm going to call that okay for one line. There's nothing super tricky about that. Great. A build method. It should iterate over all the movies and map them to both the index and the doc map. When adding the movie data to the index, okay, so build method. I'm just going to copy this step over. My memory is not the best. Build method. Okay, so it should iterate over all the movies. So that means I need the movies, right? And then I need to go from movie in movies. Add them to both the index and the doc map. So I need the document ID. Let's look at our data just to see. Okay, so it's not doc ID, it's just ID. Add them both to the index and the doc map. So we have this add doc map, which needs the doc ID and the text. So we can add documents. We can take our doc ID and we need the text. So that should work. So we do, I think we want the description here. Great. When adding the movie data to the index, add docket, concatenate the title and description. Okay, so for example, this. So I screwed that up here. So we can say text. So we added that to the document. I guess I had it here. Use that as the input text. Okay, and the document map is the document ID to the actual document. So I should be able to say document map is the document ID to the actual document, the whole movie. So I think we got that build step down. A save method. It should save the index and doc to using the pickles dump. Index.pickle.pickle makes sense. What I did, I think, have this method create a cache directory if it doesn't exist. So we need to create the directory, and we can use the os.makeDirs, And we should have the cache path here. And there's an argument here. It's exist okay, which basically means if it exists, that's okay, just ignore it. And then we need to save these. So we can open, we have our index path and our doc map path. So we definitely need to open those. And we do want to write this time. And we want to self.docmap path. We want to, basically do this. Okay. And we want to, dump. Hang on a second. We need to import pickle. Pickle is just saves files in small formats, basically. So we have the object and then we need the file. Okay, so we have the object, which is the doc map, and then the file, which we opened. And this is, we want to do pickle.dump index with the file. So I think that works. So let's check this off. Add a new build command to the CLI entry point. Builds the inverted index to save to disk, and it should print a message containing the first ID of this whatever thing. Oh, it's given a print. So let's do this. I'm going to make the build command function here. And this is going to, so what do we need to do? We need to initialize the inverted index. We need to build. So what does build do? We probably want to save this as well. I don't know if it said that, but we do. Once we save it, we probably want to get the documents for this particular one, and then told us to name this docs, so that's fine. I can do that. So then we need to import this into our CLI. Cool. What are we doing here? Add a new build command. It should build the inventory, and doing so should print the message containing the first ID. So we need a new command here. So we definitely need to run the build command. We need something here. Add subparser, add parser search. Does that work? Boom, boom, boom. So let's give this a shot. We'll try running it, see if this works. So we should see a cache directory get created somewhere. So we got the cache directory. We got the doc map in index here. Okay. Inverted index object not subscriptable. Oh, okay. So this actually, I was right, kind of right. I was half wrong. I was wrong in both cases. So this should actually be docs because it's the get documents that returns the list. I'm not trying to index into the inverted index into the results of get documents because this is returning the list. So let's try that again. Okay. So let's see. We got Merida 4651. Great. 0, 0, 0, 0. I think we're in good shape. So we can go ahead and try and submit and see if we got it right. Cool. Okay, we have an inverted index now. So that's our core data structure for this TF-IDF that we're building to, which is pretty exciting. So we built it. We'll use it next. All right, using the index. So we've got this index. We said it was so that we could quickly search for stuff, but then we hard-coded a Merida in there. So let's actually use it. So we're going to delete the hard-coded search from my build command. Add a load method that loads the index and the doc map from dicts. Okay, great. Let's do it. First, it said let's delete this. I'm just going to comment it out for now. Might be nice to just have the syntax there. And we don't have a load method, so let's go ahead and load. And what we need to do is we need to define our index and define our doc map. We need to open the files. So we had index path. And we wrote them before, so we need to read them. And we can do index as pickle.load the file. Okay, so we just need to do the same thing here with open self.docmap path. We want to read that here. And this, we want to also load pickle.load the file. I think we can mark that off as done. Okay, update your search command to load the index from disk. Load. Wait, update your search command. Okay, so we need to create our inverted index here, and we need to use our load command. So we're updating the old search command. We're not creating a new one. And if you remember before, we just had it and enumerated through. So this is what we're updating to be a little bit smarter. Remove your logic for iterating over queries and movies. Okay, I truly can remove that now, so I'm going to clean that up. Instead, let's just take these instructions. We're going to go over each token in the query. So we're going to get, okay, so each token in the query, we'll use the inverting index to get matching documents. And once we have 5 results, we stop searching and return them. Print the resulting document titles and IDs. Okay, so iterate over each token in the query. So we still need this. So for query token in query tokens, iterate over each token in the query. So now we need to use the inverted index to get any matching documents. What do we have here? get documents for each. Okay, so this is matching docs. Okay, so this is the matching docs. Once you have 5 results, stop searching and just return them. Print the resulting document titles and IDs. Okay, so then I need to probably for each matching doc, I need to check. And what does get documents return? Does this return the actual documents or does it return the document IDs? Lists of index. Index. Okay, so the index is a list of document IDs. Okay, so this is actually not matching docs. This is matching doc IDs. Use the inverted any matching documents for each token. Okay, so so we can say result and we want to keep track of which ones we've already seen because we need the resulting list, but we don't want duplicates. That's what a set is for. And so we can say if the matching doc ID is in the set, then we don't need to do anything. Once you have 5 results, we stop. Okay, so if the length of our results is greater than or equal to 5, which we have end results here. I'm going to say end results is 5. Then I can do this. Okay, then we can just return the results because that's what we want. And if we get through, we just want to return whatever's left if we don't ever get to 5. Okay, once you have 5 results, stop searching and return them. So that's this. We've never appended. So if it's in the scene, we continue. If it's not in scene, we need to add it, the matching doc ID. We need to get the doc, which is the document map. And if we remember, that is, we made a comment up here where we said doc map is the document ID to the document. So by indexing in with the document ID, we get the actual document. So this is like the matching document. And we can append to our result.append that matching document. If we have 5 results, we stop. Yeah, so okay, I commented this out, but yeah, I really truly do not need this. Okay, so let's see what else we got. That might be everything. Okay, we're gonna submit the CLI test. So we're gonna run this. We should see Madra whatever. Okay, so this succeeded. That is Madra whatever. Nonsense token assault. This should give Klansman, and it did. So I think we're ready. So we can just go -S to submit, and we passed. So we have now used the inverted index for the search, which is going to be much faster. You have to build it once, but it caches all that information, which is pretty important. It's essential in all applications. Lesson 3, Boolean Search. Typically, you want to use and or and not logics as well. You want a search bar where people can either have some sort of syntax to do advanced searching. That's pretty common. You also are going to want, drop downs and UX affordances. Sometimes people, a search bar doesn't completely replace the ability to filter. Filtering is really, really useful. So we want to add these. So if you're trying to alter an existing query to return more results, which Boolean operation would you use? I'm going to transcribe. In order to get more results from a Boolean operation, you're going to want to use the OR operator. If we think through them, the AND operator means that 2 criteria have to be true. Both criteria have to be true. That's going to be a smaller subset of OR, which is either one of the 2 must be true. So you'll get a lot more results with OR than AND typically. And NOT is another thing where you have to fulfill 2 criteria in order to clear it instead of just 1. You have to fulfill a true and a negative. And so an OR gives you the most results. Whoa, I passed, and look at that. Look at all these achievements after I destroyed my Archmage status. All right, well, bye-bye Archmage status, I guess. Such is life. I'm now one of the plebs. It's all coming back quickly. I guess these are all the Discord ones. Okay, so term frequency is what we're implementing now. We could find the documents that contain our search terms. So we were looking up a document ID and we were looking up a term and getting all the document IDs that had that term, but we can look at how often they appear. For example, this example here, Boots the Bear teaches students programming while enjoying his salmon for lunch. The students gather around eagerly as they learn debugging techniques, and all students leave with new coding skills. So we could say that, yeah, okay, this passage contains the word students and it contains the word salmon, but that doesn't really tell the full story because students shows up 3 times. And so for the sake of this passage and looking at just term frequency alone, you can say, well, students is probably more important to this than salmon because salmon only shows up once. We'll talk about later how to do diminishing returns because if You just said students 100 times. That doesn't mean it's super more important, but term frequency does matter. Now, we don't want to recount it every single time someone does a search. Documents don't change, so we can add this to our inverted index to keep our term frequencies. So we're going to add a new term frequencies attribute, and we're going to use a counter object. As you might have guessed, a counter is an object optimized for counting things. Let's start there. So we are going to add our term frequency, and this is also in the standard library collections module. Okay, so we have our term frequencies. We're going to update our load and save methods with a term frequency pickle file. So let's go ahead and take care of those with open self.term frequencies path just to match this F. We can do exactly what we did above, just with term frequencies. And same thing here. We're going to do open them self.term frequencies path. We'll read those in and we can load those. So we need our term frequencies path, and we can make that our cache path / term frequencies.pickle. Okay, I'm just going to reorganize a bit. Okay, so there's that. Perfect. And this is going to, so let's see. It's a dictionary of document IDs. Okay, so we got his here. What we need here is we don't actually need a count. We actually need a dictionary. We need our default dictionary of counters, because when we look at a counter from collections import counter, let's see here, counter dot, I don't know, we can do update 5, and we can see we update with 5 and 4. Each one has 1, and so then if we update again with 5 and 3, we can see it's counting. 5 has shown up twice, 1, 2. 4 and 3 have only shown up once. And so we count that. But this doesn't really help unless we're not trying to count across all the documents. We're trying to search for specific documents. And so we need one counter per document. And so that's why we're doing the default dict. So we can index into the particular document for that. So we got this term frequencies there. So that's good. We've loaded and saved them here. So that's good. And so we need to now update our add document method, and we're going to update the term frequencies for each token of the document. For each token, increment its count in the counter for that document. Okay, let's start with that. Add tokens. So we can do self dot. So we know we need to update our term frequencies. We need it for the document ID. That's already passed and provided, so we're good there. We just saw in the Python REPL that we can update with the update method, and we can pass in our tokens. And so now this document ID will continue and will count all the frequency of the different tokens. So that's all we need to do there. Then we need to add a new getTF. Okay, I'm going to go ahead and paste this in here. So we have a getTF method. They gave us the arguments here, so I'm going to paste that instead. Okay, so we added the new method. That's great. It should return the times the token appears in the document with the given ID. So we need to tokenize it because we have a term. Okay, so we need to tokenize the term. If the term doesn't exist, okay, be sure to tokenize the term, but assume there's only one token. If we assume there's only one token, then we're fine. We could add error handling in tokens. So we could say, instead of assuming, we could add in some sort of thing. So I think that's a little bit better. If there's more than one, raise an exception. Okay, so we're not actually assuming there is only one token. We're actually checking if there's one. Okay, so we did all that. It should return the times the token appears in the document with the given ID. So we've already got this term frequencies thing. We know we index in from the doc ID because when we look at add document, it's here, and we've already updated it here. So we don't need to update it. We just need to index, not tokenized text. We want the tokens. And I guess really this isn't tokens, it's token, because we're validating that there's only one. It's a list, even though it's a list of one, so I can just index in there. So that, I think, solves that. Add a new TF command. You should take a document ID and term, print the frequency. Okay, so we're gonna need a new TF. So I'm gonna go down and follow the pattern we did here, where we have a build command and we have a search command. And I'm just gonna make a TF command that we can call. Take a document ID and a term. It should print the term frequency for that term in the document. And so that is pretty much what we built up here, right? We got the term frequency for that token in the document. So that's a bad name for it, but that's okay. Print the term frequency of a term in the document with a given ID. If the term doesn't exist, it should print 0. So basically, we just need to print this, it seems. Let's see what the output is expecting. Yeah, it's just looking for the number. And we need to rerun the build, and then we can do this. Okay, because the build, we can't do, we actually have to create the index here. So we need to index equals index.load, because we want to load all of our data. And then we want to do the index.getTF. So then this is what we use here. So we can add, so we have search command, we have build command, now we have TF command. We need a doc ID, and we need a term. I think that's what we're supposed to use. Document ID and term as arguments. Great. Document ID to check, and the term is the search term to find counts for. Okay. So we also need this TF command here. And we can just run our TF command, I think, because I think we had the print in there. So we need to do the build step, and the build step is going to need to add a new cache. Let's go ahead and run our build step, our UV run our CLI script with the build, and it fails. Okay, great. First argument must be callable or none. Okay. I see. So the default dict actually should take a callable, and this isn't a callable because it's called. And so when a default dict, so for example, a set, when the default dict is created, if you index into a new thing, it actually takes the callable and calls it as a function. In this case, it uses this, which for a class is the dunder call. It's the same thing. I need to give it something that I can do a callable on. And so that's why that failed. So let's see if I have any more bugs. And hopefully, if we did this right, we'll have a new thing in our cache. Great, we have our term frequencies. So that's pretty cool. And we can go ahead and try and do this run and see if we're getting the right answers. Missing 2 positional arguments, doc ID and term. So TF command. Okay, that's kind of a dumb mistake. Let's fix it. This TF needed doc ID and term, but I didn't pass them. Round 3, let's see if we got this right. We expected code of 0, and it's expected to contain 1, 0, expected 4. Okay, so something here is not working right. 24 trapper, 424 trapper. Okay, so I guess the first thing I tend to do is I go back to the data. So 424 and trapper. So let's make sure trapper. Let's just double check here. So trapper is definitely in there. So it's definitely a bug. That should definitely work. So it's definitely a bug on my side. Let's go ahead and let's step through and see if we can think through what might be causing an error. So we have the default dict as a counter. We have a path to term frequencies pickle. Okay, so that should be good. So we have the default dict and we have the path. To build it, we write. We saw that written. To load it, we do this. So that should be okay. So the building and the loading look fine. Let's add the doc. Let's look at the add document. So when we go through this add documents, we tokenize it, and then we take the term frequencies, go into the doc ID, and we update the tokens. Okay, so this should be good. So we're calling a set here, but we don't actually want to dedupe. Like we want to dedupe it to say, is this term in this document? But when we're doing the counting, we actually do want the duplicates because that's what we're trying to do. So I think that's okay. So get TF, we're going to tokenize the term. We double check it's here, get the first one, and we go here. So that seems right as well. We use get TF with the doc ID and the term. So as far as I can tell, all of this is correct. What is this? Let's look at the CLI again. So we are passing the doc ID and the term. We have the TF command. That matches to our case statement. The document ID should be an integer. I wouldn't think that would cause the problem. So that passes through here. Why would that cause a problem? That passes to our TF command. Our get TF is going to look at here. You know, I'm just going to actually just say that I don't care. I guess this is why you do type hinting, huh? Okay, well, let's just try and run this. I think that might be the issue. Okay, so we are getting the right answer now, 1 and 1, 4 and 4. Okay, so we can go ahead and submit. Okay, great. So that was the bug, just the wrong types. Let's move on to the next lesson. Okay, inverse document frequency. Inverse document frequency is common words that are specific to our data set as opposed to generic stop words. The idea here is we want to see how many documents in the data set contain a term. And if that number is high, then that's bad. That's why it's inverse. So the idea is we have a movie data set. And so actor may be a great keyword to narrow the search in some data set, but in about movies, every movie is going to have actors. And so we'd say, what tells us the most about this sentence? Well, if every single movie, every single record in our data set is a movie that has an actor in it, then these words are going to be not that useful. Like movie doesn't tell us anything about any document at all. Not because it's not a good word, but because every single document in our data set is a movie. And so that's going to have an inverse document frequency that says it's in all the movies, so that term isn't very important. However, coding, that's going to be in much fewer movies. Only movies that have something to do with coding. And so that's going to have you want that to have a really high weight. The fact that coding it is in there and instructor is in there, those tell us something about the document, whereas words that are in every movie are not. And there's a scale there. If there's a very common term, say the term bear, can get a very low score. If there's a very rare term, like cyborg, it gets a very high score. So the more rare it is, the more valuable the term is. And in other words, the more informational it is, that term is in that document. It distinguishes it from other document. If it's movie is in every single document, it gets a score of 0. Basically, that term doesn't matter at all. Now, we removed a lot of ones that are going to be in every single document when we removed stop words, but these are other ones. And so we've got a formula here. We get the total document count, how many documents we have, divided by the number of matching documents, and we add 1 and do a log to prevent a division by 0 error. Let's go ahead and implement this. So we're going to add an IDF command to our keyword CLI entry point. Take a term as an argument. Okay, so we have get TF here. Let's just add get IDF right next to it. So that takes a term, and we're basically going to want to return, we're going to want to return the IDF. So we're going to need the documents for sure. We're going to need to tokenize the term. We know we're going to need to do that. We did this above where we just verified that, so we could just take all of this here. We tokenize the term. We've only got 1 token now, so that's great. Load the index in the doc map using the load method implemented. Self.load. I don't want to put this here, actually. I want to do it just like this. Okay, so we can get our document count. That's going to be the length of the document map. So this is let's see here, a map of the document ID. So this should have all the documents. So the length of that should be the count of the documents. We saw this formula here that we're building towards, so we can copy that. So that's really what we need to return, which means we need to import math. Okay, so we have the doc count. So that's going to be this. This is our document count. We need our term document count. And this is where our index becomes super valuable, because if we remember, our index is a set. And what we do is we put in a token, and then we get a list of all the document IDs that have that term. So we just do this. So let's change this to, we need to cast this. We need this not to be a list. So I'm going to go ahead and just do that. We index into the token. That gives us a list of all the documents with that token. We take a length of that, and we've got the term document count. And so we need the IDF command, I believe. Let's go take a look. Load the index in the doc map. So this is IDF command. This needs a term because that's what we did. And we need the same thing here. We need to load our inverted index, load all this stuff, and calculate the IDF, and then print the IDF value and format it in this way. Okay, so we need to print that. So we do idx.get IDF, and we pass in our term. I built the print in here, so I'm going to build the print in here. It seems like this copied snippet was putting it in the CLI thing. That's okay. You can do things a little differently, and I will just do this. So we've got this IDF command. It loads the inverted index, loads it, get IDF. Okay, that's good. So the next thing I need to do is I need to add this to the CLI. So I need to import this. I need to add a new parser here, because last time I screwed up types. I need to be careful about this. That's a string, so that's good. I need IDF, calculate, let's fix some of these help commands. Calculate term frequency, and this can be called calculate inverse document frequency. This should be build cache. So then we can add this in case IDF. You can say IDF command takes in our term. Okay, so in theory, we did everything. So let's give it a shot. What should we see? 5.52. Okay, So we got that one right. 5.52, 3.29. All right, I think great. We did it in one, so we could try and submit. Pass. If you're interested in building any kind of AI-powered search system, we need to talk about TF-IDF. It's one of the most powerful tools for getting meaningful results in a context-specific way. Let's break down the acronym. TF means term frequency, how often a term appears in a document, like how often polar bear appears in a movie description. IDF means inverse document frequency. How rare is a term across all the documents in a set? Like how many movies in all of IMDb contain the term polar bear? TF-IDF is a super simple formula. TF multiplied by IDF. The result is a number that tells us how important a term is relative to the entire data set. For example, the term actor might appear very frequently in a movie description. That's TF. But it's in almost every movie description, so it has a low IDF score and gets a lower overall score. The term polar bear shows up a lot in the movie The Golden Compass, but not in many other movies, so it gets a high overall score, which is what we want. We want to find terms that are frequent and somewhat unique, not just frequent in general. TF-IDF isn't a new idea, but it's still an amazingly efficient way to augment search engines and recommendation systems, and it's a great tool in RAG pipelines and other context-aware AI systems. All right, cool. Okay, we got to put it together. So we calculated TF, we calculated IDF, so now we're going to do TF-IDF. So let's talk about what this is. We talked about term frequency, and that is how often a term appears in a document. And the more times a term appears in a document, the more impactful that word is. That makes sense. Something that mentions, the example we gave was something that mentioned students 3 times, but salmon only once, is probably students is the more important word. IDF is talking about it from a different way. So instead of saying how important is this term to this document, which is how frequently it is, this is saying how important is this term in differentiating between documents. So if the term salmon only appears in 2 movies out of all of our data set, it tells us quite a lot if that word is in the movie description. The word movie, if that's in every single document, it doesn't actually tell us anything. It's like, hey, what movie is about a movie? It's like, well, that's a stupid question because it doesn't tell you anything whatsoever. We need to put them together. We've calculated them separately. How often a term appears in a document, how rare is a term across all documents. Okay, so we got a really complicated formula. We take them and we multiply them together. So let's go ahead and take care of this. Okay, so add a TF-IDF command in your search entry point, calculate TF-IDF, print the value. Okay, so let's go ahead and do this. In our keyword search, let's just keep building the same pattern here. We have TF, we have IDF, we have get TF-IDF, self. We need the term for IDF. We need the doc ID for the TF, and we can say self.getTF equals the doc ID and the term. IDF equals the self.getIDF, which only needs the term. And we return TF-IDF, which is those multiplied together. So that's great. And we can create a TF-IDF command with doc ID and the term. And really, that's just going to do these steps. But I also need my term frequency. Oh, wait, no. I don't need this at all. Get, because I just created the TF-IDF command, so I can do argument or method. So that should do it. Let's read through our instructions. Take the document ID and term as arguments, load the index in the doc map using the load method, calculate the TF-IDF, print the value. Here's the value to print. Format the floating point to 2 decimal places when printing. They gave a print command. I will go ahead and put that here. Follow that pattern. Okay, so let's go here. Term, doc ID. And this should be actually TF-IDF. So that should be it. We can add this to our CLI now. Add this down here. So this requires a doc ID and then the term, and args.term. And let me make sure I was naming this right. It is a TF-IDF. Okay, so then we can add this here. This one already has doc ID and term, so I'm just going to copy and steal TF-IDF, term frequency, inverse document frequency, search term. All right, let's see if we got this right. So what do we see? 2.14, we got that one right. 24.13, so we're calculating this properly. We can see when we look for Trapper, very good. So let's see if we can submit. All tests passed. We just calculated TF-IDF, and that is the end of chapter 2. Very nice. All right, chapter 3, keyword search. This is where we're going to take TF-IDF and add a few finishing touches on it to make it more stable. So there's three key problems with that we had that we want to fix in this chapter. One is we want a little bit more stable scoring for our inverse document frequency. And inverse document frequency was like how rare it is. And then there's term frequency saturation. And so this is about a term appearing too often. So if I think about a recipe, if you're cooking something, you want to know, is this recipe a salmon recipe or not? If the word salmon shows up once in the recipe, it could be a salmon recipe. But it's also possible that it's a recipe primarily for some other fish or some other meat. And there's a note that says, hey, you can substitute, chicken for salmon in this case, or you can substitute out trout for salmon if that's more accessible, or some sort of note about, a dietary thing that you can replace. If it shows up 5 times, then it's probably in the ingredient list and it's probably mentioned several times throughout the recipe. And you're probably pretty confident that this is a recipe where salmon is a core part of it. If it's mentioned 10 times, I guess maybe you're a little more sure, but if it's already been mentioned 5 times, you already know it's important. And so the number of times isn't like linear. It kind of falls off a bit. And so we want to account for that. It showing up 1,000 times does not mean it's more salmon. And this is something you want to prevent in your data set from like really overweighting things based on that frequency. And then the last thing is document length. If you have a recipe that's 1 paragraph long and it mentions salmon 3 times, and you have a recipe that's 100 pages long, very long recipe, but it mentions salmon 4 times, that's very interesting. You might want to say, hey, the much, much shorter one mentions it almost as much, even though not as much. And so you want to normalize for that length. So we're going to cover all of that here. So this is the more stable IDF formula. What we're going to see here is this numerator is going to count documents without the term plus the smoothing effect. And then we're going to count documents with the term. We add this half to prevent division by 0. It's called Laplace smoothing, and we add 1 to make sure IDF is always positive, which is, handling some edge cases. This might sound a little janky. That's very common though. Okay, so let's add our get BM25 IDF to our inverted index, then we'll talk about it. We'll use the BM25 IDF formula, which is, accounting for the total number of documents and the document frequency. We'll tokenize the term, and then we'll add it to there. So let's go ahead and copy this so we can add this to our inverted index class. So here we are, get TF, get IDF, get TF-IDF. Let's add BM25 IDF right after the IDF so we can compare. You can see they both require the same thing. It's inputs, and our instructions show we'll use this formula here. So we know we need that. And let's break down what this actually does. So just like all the others, we need to tokenize our term. And if it's not 1, we'll raise it. So we'll go ahead and copy this. Again, these are patterns you can decide as you're going. Do you want to refactor them out? My goal is to kind of explain each step, so I'm going to leave it a little bit more verbose than I normally would. But here we go. We have tokens. We have length tokens. Naturally, just like the others, we want to get the token for that term. We did that here. I'm going to put it in line here while we think through the formula. We still want our document count, and we still want our term document count. Here we can just use this token. Now we can do our formula. So let's start with what we had before, and then we'll improve it. So before we had a doc count plus here, we're going to say our doc count minus our term document count. And remember, this was looking at the index, self.index of the token. And if we look at token, this is adding document IDs, and it is a set. And so what document count really is here is this is how many documents contain that term. And that's, the document frequency. So then from here, we have our document frequency again, plus, let's fix these, 0.5 plus 1. And so here we've got our document count, it's our N, minus our document frequency, our term document count, plus 0.5. And we're going to divide that by the DF, the term document count, plus a half, plus 1. And this should give us what we need. So now that we got all that figured out, let's go ahead and add it to our index. So let's see what it needs us to do. So we added the new method. We used the BM25 formulas where N is the total number of documents and DF is the document frequency. We want to tokenize the term and validate that it's a single token. Okay, we did that. And return the calculated BM25 IDF score. So let's double sure we did that. Yes, we did that. Okay, so we've got this longer formula. Okay, and now we want to add this BM25 IDF command and then add a new BM25 IDF command to our CLI script. So here we go. It's giving us some code. That's nice. So let's go ahead and pop that in there. We've written this quite a few times, so you should be able to see the pattern. We've got BM25. We've got the term as a string. We need to handle this as a case here. We want BM25 IDF, probably. We need our BM25 IDF command. So the commands are these. I guess we could, oh, nope, they're these. So if I was to follow the pattern I had been, it would be BM25 underscore IDF. In this case, it's specifying to have the underscore command. So I'll go ahead and do that. But in this case, I could name it whichever. It's the CLI one that you want to make sure is correct because that's what's being called by the tests. All right. And this follows a similar pattern. Again, you know, you can refactor some of this repeated steps out if you'd like. So this is, what was this? We have get BM25 IDF, get BM25 IDF, and then we put in the term. So then now we can import that into our CLI. We can call that with our term. Let's see if it has a special thing. Yep, special print. And then we'll submit and fix all the bugs. All right, very nice. Let's give it a shot. All right, we've got this error. That's just my environment. So let me get rid of that. That's just some UV stuff. Okay, so we expected 5.5 and we got it. We expected that, and we got it. We expected a score of 0.6, and we got it. Okay, so what is this showing? This is showing Go gets a low score. That's not very rare. I would have guessed that characters go lots of places. Actor is medium. There are lots of movies about actors, or it's mentioned, that term is mentioned. And grizzly is most rare. So the number of movies with a grizzly bear in particular is a lot more rare. So that all seems to make intuitive sense. So let's go ahead and submit. All right, awesome. So that's fixing the first of the issues with TF-IDF. All right, term frequency saturation. So we talked previously about the problem of having the same word too many times. This is where we're actually going to fix that. The example I'd given was if you have a recipe that mentions salmon one time, salmon is related to that recipe, but it could be that it was like just a note that says something like, hey, if you don't have trout, you can substitute it for salmon, or you know, any other kind of fish. If it shows up 10 times in the recipe, then you're almost certain that it's a recipe about salmon. If it appears 100 times, it's not like it's 10 times more likely that it's about salmon. It's like there's a limit. You know, the first few mentions matter a whole lot, and then it falls off a bit in importance. That's what this does. So instead of term frequency, which the basic term frequency we did was however many times it appeared in the document, that was the weight it got. BM25 uses a term frequency with a modifier here, a variable that you can tune. A pretty common value is 1.5, so you can set it to that, and that does pretty well in most cases. And what you'll see is for the first mention, it's the same thing when you have this parameter at 1.5. For the second mention, instead of adding like a linear thing, instead of like +1 and then add another 1 to get to 2, it adds much less. It adds 0.4 for the second. So it's still a decent amount. And then to get up to 5, it's only 0.5. You add 0.5 for 3 more placements. And so you get 1 plus 0.4 for 1 more, and then you're getting 0.5 for 3 more spots. And then you're getting 0.3 more weight for 5 more spots, and then 0.1 more for 10 more spots. And so you can see it grows much, much slower. The first few occurrences matter the most. You get a weight of 1.9 for the first 5 and 2.3 for 20. So you multiply the term frequency by 4, and you do not multiply the weight by 4. And so the graph looks about like this. So your basic term frequency grows linearly 1 to 1, and BM25 term frequency will plateau. So we're going to implement this. We're going to use the K1 value of 1.5. So we're going to have a constant in our files for that, because that is a tunable parameter. We might want to change that later. We're going to add this function to my inverted index class, and then we're going to add it to our CLI. And yeah, let's go for it. So let's just add this, get this out of the way since it's very quick. Let's go into our search utilities. We can add that. Let's add it to the top. I think that's a parameter likely change. Then we can add our new BM25 TF. And so you can see the term frequency takes the doc ID in the term, which is what our previous term frequency did, but it also takes in this new parameter. We're going to default it to that argument though. All right, so here we go. This is not where I want it for now. I'm going to go ahead and place it. So we had get TF-IDF. We had, okay. Let's place it right after the regular TF so we can kind of compare what we're doing here. It's new in BM25. So you can see doc ID and term are still there. We have this new parameter. We've got the yellow squigglies, so we can make sure to import this. And let's just format this a little bit. Okay. All right. We fixed the yellow squigglies. We're on the right track. So one thing you'll notice about this formula is that it uses the term frequency directly in it and then adds to it. So what that means is we can use our previous calculation and then add here. So let's take a look at our formula. We know this is the formula we want to return, so let's go ahead and calculate it. So our previous term frequency was self.getTF. We already calculated that. And we can simply pass in our doc ID and the term. That should resolve what we want there. And now we need to add it to our CLI. So BM25 TF command, and this would take the same thing, doc ID and the term. We're going to do basically the same thing here. And we are going to say, get this. And we need to pass in the doc ID. So we're just calling the function we did with the new parameters. We can go over to our CLI. Let's make this a little bit more readable. We now have got our BM25 TF command. I'm going to go ahead and copy this. We could type it all out, but we've done that many times already. I think we're expert CLI people now. All right. We need to handle it, and we need to do this print statement to format it, and we'll be good to go. So case, we called it BM25 TF. We know we need to do this printing. We know we need to use our formula, our command that we did, get BM25, here we go, args, and we want our doc ID, our term, and our K1. We also need to import this from our search utils file. So let's import this, and let's go ahead. Let's see if we got it all. We did not get it all. Okay, BM25 TF takes 2 positional arguments, with 3 were given. Okay, so I must have missed the extra argument here. So let's go ahead and take a look. Is exactly what I did. So this needs K1, and we'll default that to our, what did I call that again? BM25 K1. This needs to get passed through. And let me just make sure I did it properly up here as well. Okay, let's try it again. Okay, let's see. Expected. Okay, we got that one right. 2.31, 2.31, 2.17, 2.17, 2.0, 2.0. Okay, so this is really great. So we're seeing the term frequencies a lot more stable. Let's go ahead and do the full submission here. All right, we passed. So this is actually a pretty important lesson. It might seem like this smoothing effect isn't that valuable, but this really, really, really helps stabilize things quite a lot, and you'll get a lot better results with this. So this was actually a fairly simple idea of just smoothing it out that had a pretty big impact. All right, lesson 3 is on document length normalization. So this is a second kind. So we talked about term frequency being if you have too many of the same word in a document, at some point there needs to be diminishing returns because it stops being signal. Well, this is tackling a different thing you need to cover, which is the length of the document has some relation to how many times it shows up. You know, for example, if you have a recipe that's a very simple recipe and it's just one paragraph, and it mentions salmon twice, those 2 times salmon is mentioned may be pretty decently high signaled. Now, if you have a very long, complicated recipe that has salmon twice in it, but it's a 6-page recipe, you may rethink that, hey, the six-page recipe that only has it mentioned twice in the entire document, well, it's only mentioned twice in 6 pages. This other one is mentioning it twice in 1 paragraph. That might be more impactful. And so that's what this is all about. The idea that we're going to add this length normalization factor to it. So we're going to take the length of the document for the average length of the document. That's going to give us an average length if it's longer than the average. So if our document is longer than the average document, it gets penalized. If it's shorter than the average, it gets boosted, and it just kind of do it. Now we have this B, which is normalization strength. Basically, this parameter controls how much we boost or penalize the documents. Common value is 0.75. And so what we'll see is we'll use a B value of 0.75 and a K1 of 1.5, and we will implement this. So our length normalization factor, that just goes into our term frequency here, goes right here. So we get 1 minus B plus B times that ratio. Let's go ahead and implement this. So we're going to add this into our search utils, and then we're going to add a new doc length attribute. So search utils, we'll put it right here. We'll of course need to import that. So I'll just take care of that now. We needed, I forget what it's called, a new doc length attribute. That's going to be a dictionary. We'll need the length of every single document. That's going to be in tokens. And what we'll need is a doc length path, because we will want to cache this as well. It's not quite as expensive as some of the others, but still don't need to calculate it many times. So we can add this cache to our save and our load. Well, since we're here, let's just add this to calculate it. It's very straightforward. Self.document lengths. We're going to do it for each document ID, and we're going to set that equal to however many tokens, whatever our length is. Now we need to take this doc lengths paths, and we're going to do the caching step. So let's add this to our save and our load, wherever those are here. I'm going to go ahead and there we go. It's doc lengths path. We open that file and then we dump the doc links. So that looks good. We'll then do the same thing here. We're going to open the doc length path and then we're going to put it there. Okay. So we've got that. We've got doc links. When we add it, we'll do it. We'll cache it. We'll load it. That's good. We'll need to remember to rebuild, everything. So that's good. Initialize it as an empty. We did that. Okay, we updated this, count the number of tokens after tokenization. We stored it. Okay, so this is great. We're making really good progress. We updated the save and the load. All right, so we add a private helper method. So when we look at this formula, we need the average doc length because we're going to take the length of that document, so say it's 100 tokens long, and divide it by the average length. If this ratio, if it's perfectly average, the doc length is 100 and the average doc length is 100, and this is 1, and so this doesn't do anything because it's multiplying it by 1. If it's shorter than the average, this is going to be, doc length of 50 divided by an average doc length of 100. So this is going to be a half. This will make things smaller. That will make the denominator smaller, which means the overall thing will be bigger, and vice versa. So let's get that average doc length. So this is a private helper. Handle the edge case where there are no documents, return 0.0. This is a little bit of a judgment call. Handle the edge case where there are no documents, return 0. Would you really want it to return 0, or would you want it to raise an error if there are no documents to return? It depends a little bit. If you've got like a static data set that you always want to search, maybe you would want to surface an error. If you're doing something like retrieving from a user store, you may not want to raise the error because it might be that there are none. So get the average doc length. So we had our self.doc lengths. This has all of them in a dictionary. We can get all the values here, and let's just print a few. See what this looks like. Let's do this. Let's build our index so that we can play around with it a little bit. So to build it, we want to run our CLI, keyword search CLI, and run our build command. So if we did this right, we should see, once it's done in our cache, a new file, and that file for our document links. Okay, perfect. So we've got that. That did show up. Let's go ahead and use our REPL. So we could say from cli.lib.keywordsearch.py, keyword search, import, and let's just import our inverted index. Had to run it with UV there. All right. So we could do what we do to initialize it all the time. We can grab that from down here. Just initialize the inverted index and load it in. All right. Inverted index equals inverted index. Great. And we can do the load. Now what we want to do is let's take a look at our inverted index dot, what was it called? Doc lengths dot values. And let's see if we can look at the first 5. Okay, dict object values is not subscriptable. So let's cast it to a list. So we got a whole bunch of numbers. This is a few things he could do. Maybe the fastest would be to put it in like a NumPy array and do it. We could also do something like, I think math has does it have a mean? Certainly has a sum. Really? All right, let's go take a look here. Python standard lib math module. What does it have? Ceiling math here. All right, well, it would have it. I don't really want to add NumPy as a dependency right now, so we're just going to do it kind of the little bit of a silly way. Let's just do a loop. Lane will love this because he likes programming like he's in Go. Okay, so we have our self.docLengths. Oh, we commented this out. Great, now I got a bunch of places I've put it in. Get rid of this one, and we'll just continue on here. All right, so we have our docLength values. We can put them in a list or something. I'm not sure that that's completely needed. We can say total is equal to 0, and then we can say for L and lengths, we can add it. So this gives us the sum. Once we have the sum, we can return the total divided by the length of him, and that should give us the average. Okay, good. So we've got that one. Handle the edge case where there are no documents, return 0. Okay. If self.docLengths, let's just do this. So if that's equal to 0, there's none of them, we'll just return 0.0. Update your BM25 TF method to add a B parameter, calculate length normalization, and then update the final formula. And then we add it to the CLI. So I already imported that. So we've got this. We got the BM25 TF. So we've already gotten this. We need to add B. So we need our doc length, because if we look at this, this is our whole length normalization. So we need B. We've got B already. We also need the doc length and the average doc length to add in that length norm. So we get average doc length, which we already have because we just calculated the average doc length. But the doc length we have as well because we have our dictionary that we used. And this is based on document ID. Maybe a safer way to do this, safer way to do both this and this would be to use .get. I think we're going to leave it for now. So we got the doc length. We've got the average doc length. We can say if the, let's take a look here. We did this, we did this, we did that. We did not do this. Okay, update the final formula. Okay, so we got to do our TF. Let's see here. So if our average length is greater than 0, then we want our length norm. We need to calculate a length norm. And that's going to be the formula 1 minus b plus b. So then taking that from here, 1 minus b plus b, times that ratio, doc length over average. So that's the doc length over average doc length. Else length norm is just going to be 1. And that gets added in right here. TF times K1 plus 1, we already got that, divided by TF plus K1, but then we need to do times that length norm. And so what this is going to do is it's in the denominator. And so based on whether it's, long documents will get penalized, short documents will get boosted, and so we will have normalized. So the last thing we need to do is we need to add this B parameter into our CLI. Given the parser that the tests are going to expect, we need to rerun the build, but we did that already, so that's good. And, okay, we've got that. We need to import this, and then we need args.b to be passed. Okay, now time for the moment of truth to figure out what bugs I need to fix. All right, so failed to spawn CLI. Okay, so what did I do here? I need to be in the root of the directory, I think. Namespace BM25 TF command, so that's line 52 in CLI. Okay, that should be B. All right. BM25 TF command takes 2 to 3 positional arguments, but 4 were given. Okay, I need to add it in to the command down here, BM25, and this needs to get passed through here. All right, let's move on to the next bug. Awesome. Okay, 2.35, very good. 0.09, that's what we got for police. For Maya, we got the correct answer, and for cheese, we also got the correct answer. Okay, this is great. So let's try and submit for real. See how we did. All right, we passed. We are on to the next one. All right, BM25 Search. We have made those 3 improvements for the length normalization, the IDF calculation, and the term frequency, kind of that diminishing return saturation thing. We've added those all in, and so now we can do BM25, which implements them. Now, just like we had TF-IDF was TF times IDF, BM25 is BM25 TF times BM25 IDF. However, that's the score for that documented term, because the IDF is how rare a term is, and the TF is how often that term appears in a document. What we need is kind of an aggregated score, like one metric that says how relevant this document is across, all the terms that are in the search terms and in the document and all that. So that way we can say like, hey, this is 0.5 relevance and this one's 0.6 relevance, so 0.6 is better. And so we need to aggregate up to at the document level, not the document term level, so that we can compare. The way we do it is, as always, we tokenize our query. We do this BM25 score for every token in the query. For the document, we add that up. We do that for every document, and then the highest documents win. So let's go ahead and start this. So we're going to add a new BM25 method to the inverted index. We're going to use these that we calculated and multiply them. So that is the first step. That's quite straightforward. So let's take care of that first. So we have a get, like some sort of TF-IDF function. Great. Oh, that's not the one I wanted. Great. This is the one I wanted. So we can do a BM25 TF-IDF function by using our get BM25, get BM25 IDF. So we completed that step. That gives us a score for the term and the document. So we're getting the document ID. That is getting the term frequency for that document ID and term. And then we're getting the rarity of that particular term, multiplying them together. And so the next step is we're going to aggregate this up. So let's go ahead and take a look at this. So we're going to do a BM25 search. This is going to have a query and a limit. And let's go through this. So first thing we need to do is tokenize our query. Okay, so now we've got a bunch of tokens, but these BM25 TF-IDF takes in a token. So I think we're going to need to do a dictionary, and for each document, we're going to go over each query token, which means a loop for token in tokens. Let me take a look here. Actually, inside of these BM25 IDFs, these are tokenizing the terms. So we don't need to tokenize in our search function. You can see for the IDF and the TF, I believe, they both do the tokenizing of the term. So that's a little redundant. For a little bit of performance improvement, we could do it here and change those functions to take a token instead. I'm going to go ahead and leave it. This is so that we can build it incrementally and every piece works on its own. But these are like refactors that you can think about as you go. So instead of this, I'm going to say for term in, let's see here. Yeah, let's just go ahead and tokenize it. I think this will work. Query tokens. We need our scores dictionary because we need to aggregate this up. And this is going to be at the doc ID. So we know at some point we need to do scores document ID equals the score. We know we need to go through each document. So we can say document ID in self doc map. So this will go through every single document. And for each document, we're going to go through the tokens for each token in our query tokens. We need to, so for this document, we have a score, and we need to add to the score the thing we just built. The thing that I improperly named is BM25 TF-IDF. It's actually just BM25. So we need to do self.get BM25, and this takes in the document ID, and it takes in a term. Okay. And then once we get the full score, then we have the score for it. Then we'll need to sort it. Okay, so let's sort them. Let's see, it's not necessarily the output docs because we haven't applied the limit yet. So we can say document scores. Let's call it that maybe. That's not really clear because these are scores. So let's just do sorted scores because that's what it is. Okay, we're going to sort them. We need to sort them. Let's see, we need to sort them based on the items. So we have the items. That's going to go into the dictionary and get the key and the value. And so we would need to keep those together. And what we need is, I'm just gonna move this over so we can see, is we need some way of filtering it based on the second value, because we don't want to sort it based on the document ID. We want to sort it based on the value, this score that we just added. So I'm gonna create a sort function. And what I'm gonna do is it's going to take in the key and the value, and it's going to return that first value. So this returns the value. Okay, so this isn't actually, so I just need the key. So this is the key. And actually, I think I can do this. This seems small enough. I can just do it in line. And this is going to sort it smallest to largest by default. And so we need reverse equals true. I think that'll do it. So that's pretty cool. Okay, so what have we done so far? We've got the tokens, we've tokenized them. We've gone through each document ID. For each document, we go through each token and we calculate the BM25 score for it. And then we sort it, which we don't need this anymore. Then I don't know. What do we need to do? Let's see. Each document, boom, boom. We probably just need to print them. Return the top limit documents along with their score. So I feel like results can be the sorted scores to the limit, whatever that limit was. Good. And okay, so then we add it to the CLI. We have a particular way to print. And so I guess this is the document ID, I think. Oh, number of parentheses, document ID. So document ID, document title, and then score. So what do we got here? We have the document ID, the score, but I feel like we need the title. So we have the doc ID and the score in our results. So that's what we got. And we need the title, basically. So we've got our doc map. And what's in our doc map? So where's our add document? So we term frequencies here, self.docmap. So this is the movie. Okay, so the doc map has the movie, and the movies have really everything in there. Okay, so this is what we want. So we want the doc map. So we go, and the doc map is based on the document ID. So self.docmap and the document ID. So now we've got everything we need, and we just need to match this format, which is, so the pieces of information we need to return are the document ID, the score, and the title. And that's what's needed to format this. So we can say results, format results. So we go through here, we have the doc ID and the score. We use that to get here. Really all we need at this point is the title. So we can just do title, I think. And then we can say format results dot append can be, we can make it a dictionary of, yeah, I guess doc ID title. Probably should spell that a little better. And the score. And then we can return that. So that should give us everything we need to format it. So I think the last piece we need to do is add it to, okay, it says you can add an optional limit. I'm gonna start without that. So it gave us a BM25 search parser and the query. So let's add this here. So we can say case BM25 search, and we can, what do we need to do? So we need to do the BM25 results is equal to BM25 search with our args.query. And then we need to do, for result in BM25 results, we need to print something. And what we need to print is, command should use the inverted, load the movie and print the results in this format. So, okay, so I'm pretty much working on this right now. So we need, let me grab a few of these. So we need to enumerate because we need this number. So enumerate. So this can be the index and the result. And we need to print the index space, the result dot doc ID, the result title. It looks like there is then a dash score and then the result score. All right, there is absolutely no way I did that. All right, so let's test it and then work through all the bugs. All right, okay. BM25 search is not defined. Oh, yeah, that helps. So I completely forgot to do that. So I was defining what I want the output to be so that I could come in and make sure that this matches. So let's go ahead and make sure we have that. So this should be, let's just add it here, BM25 search. This takes in a query. We could have the default for the limit if we want. BM25 search query. Okay, let's try it again. Very nice. BM25 search is not defined. Okay, let's import it now. All right, third time's the charm. BM25 search is missing one required positional argument. 25 search. This might be something we want to put in the search utils. Okay, fourth time's the charm. All right, space inventors. Okay, we need space Space Ace 10.65, 9. Okay, the Adventures of Galaxy Rangers 9.53. So this looks like a rounding error. Okay. Titanfall 9.12. Okay, so this is looking good. So let's fix the issue with our print. Let's see here. Def BM25. Yeah, let's just do this. Search. So where is this? This printing is going to happen here. And let's do this. Okay. All right. 5th time's the charm. Let's see. Okay. Space Ace 10.65. Good. Adventures of the Galaxy Rangers 9.53. Good. Titanfall 9.12. That's perfect. Good, good, good. All right. I think we're ready to submit. And this is going to be a full BM25 search, all from the ground up, all local. So I recommend everyone go code it yourself. There is a big, 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 big difference between watching someone else code it and coding it yourself in terms of understanding. So go sign up for boot.dev. These first 3 chapters are free. So yeah, that's great. Next up, Semantic Search. Okay, so we finished keyword search, so semantic search. Keyword search sucks. Well, it's good for some things, but it has limits. If you search for exciting adventure movie, you're never going to find thrilling journey in an exact match keyword search, even though it's obviously a relevant result. Semantic search solves this problem. It doesn't look for similar text-based matches, it looks for similar meaning. Semantic search understands that when you search for thriller, you're probably also looking for horror, suspense, and adventure, even though you didn't use those exact words. Semantic search is best when queries tend to be conceptual, like movies about friendship or bear movies good for kids. But keyword search still does well when the searcher knows exactly what they're looking for and type The Revenant or Yosemite. The inner workings of keyword search are easy to understand. Do the characters in the query and the result match? If so, great. Semantic search is a bit more complex. It uses things like word embeddings to cluster similar words together in imaginary space. When a user searches for royalty, the search engine returns king and queen because those words are close together in that imaginary space, not because they share any character subsequences. So keyword search is really good at like finding specific words that are matches. And that tends to be really great in like technical disciplines or when the user knows what they're searching for, because in really technical disciplines like, legal or medical and things like that, there's very precise language that matters quite a bit, but that's not always the case. So sometimes you just want to search for something like action movie. I don't know what movie I'm going to search. I don't know if I'm looking for an action movie that happened in a mall or an airport. I don't know exactly what I'm looking for. I just want to find something that's an action movie that I just want to watch. That's where semantic search comes in. I don't necessarily need to have all the details. And so if you say action-packed films, things like gripping or suspenseful or journey or things like that might show up. If you're looking for happy movies, you'll want things that are talking about things being joyful or uplifting. Or if you say movies about friendship, you want movies that do, some sort of bonding. Yeah, so it's pretty important. And the idea is, let's go a little bit into this video, is that you've got all these words, and if you mapped them on a chart, you can see king and queen is naturally going to be closer to each other than a pawn or a castle. However, pawn and castle is going to be a lot closer to each other than, say, a boat or a rock. Maybe these are talking about, royalty. Maybe it's talking about chess. Don't know. The point is that they're all going to be closer together than here. And so if you could create this map, then you could say, let me search for royalty. Let me find the ones that are closest to that. So actually finding that is tricky. That's called an embedding. And instead of a 2D map, it's like 1,000 or more dimensional map. But that's what we're going to be working on throughout here, is to create that. It's actually pretty important. Semantic search is, people have said RAG is dead. And by RAG, they mean dense vector semantic search, when it's a little bit more all-encompassing than that, but it's making a comeback. So like here's Cursor, improving an agent with semantic search. I'm recording this on November 25th. This was released November 6th. So this was Cursor, even for coding agents where semantic search has traditionally not been as useful, is making a comeback. This is another one by Mixed Bread. This was just released, I think, in the last week. That brings semantic search to coding agents. Parallel AI is another company. And you can see this is introducing the parallel find all. You can see this is November 18th. So this is in the last week. Here's their parallel search, which is another semantic search thing, I believe, November 6th. And so you can see this is, semantic objectives. So you can see that this is like really, really useful. So let's jump into it. So the first thing we need to do is set up our CLI. We have this keyword search CLI. That's not really what we want. We want a CLI for semantic search, just so that our files don't get massive. So let's do semantic search CLI.py. I think that was the name I was supposed to use. Semantic search. And again, the tests are going to look for this, so you do have to be exact. Cool. We do that. We want to run the tests, and we expected that. We got that. So let's submit. Cool. All right, we passed. So very nice. All right, lesson 2, embeddings. So now we got that. We'll talk about embeddings. This is that numerical representation. I showed the little chart where it's like 2-dimensional. We can do the same thing, but you can imagine 2 dimensions, and then you can imagine 3 dimensions, which is like a cube. Above that, yeah, you can't really visualize it. So this is the idea in 2 dimensions. You can think about 3 dimensions, but yeah, above that, it's very, very hard. And what we'll see is when we think about these points, what we'll see is that king and queen are very similar to each other because they're pointing in almost the same direction. Whereas another word that's not as related is a different direction. And so you can imagine every single word has these. There's, tens of thousands of them, or every single token, I should say. And yeah, by measuring that, we figure out how far these points are away, and that tells us how similar it is. So the trick is like, how do you make those embeddings? All right, what's the reason that we represent text as vectors? So it takes up less memory. That's not the case. To ensure that every word has a unique coordinate in 2D space, well, we're going to have a whole lot more than 2 dimensions. We're going to have a much bigger vectors than that, so it's not that. To convert text into binary for faster storage and retrieval, to capture the meaning of text with distances between vectors similarity. So this is the one. The converting text into binary. Binary kind of implies 2 options. We aren't trying to optimize storage and retrieval. When we create it, we're trying to give us an apples to apples comparison. So that's the right one. Perfect. Chapter 4, lesson 3 now, embedding models. So we just talked about embedding models, about how we want to have these points in space. That's like lots of dimensions. And then we can measure the distance between them to tell how close they are. So the question is, and this is kind of the whole game, is we need to create embeddings. We need to have embeddings where the distance is relevant. Like if we just pick random numbers, then the distance between them will be random. But that's not what we want. We want where the distance means how similar they are in meaning. And so we're going to use a pre-trained embedding model. This is pretty much how everyone works. Everyone uses a pre-trained embedding model. We're going to use this one called All-Mini-LM. It's small. We can run it on a computer. It's pretty good quality. We can run it locally. We have to download it, but we can run it locally. And you can read through the model card. Hugging Face is a very common place that hosts all kinds of models. It's a common training library as well. And you can get more information about it here, which I would recommend. Then we're going to go ahead and get it set up. So here's the lines to load a model. And what we need to do is we need to add the sentence transformers dependency to our project. So we can go ahead and do that. Perfect. Check. We create a new library module. So Semantic Search Pi, and then we'll want to do all the importing stuff. And we'll need a verify model. All right, so let's take this and we're going to take it and we're going to move it into here. So we're going to create a new semantic search.py. Just going to comment this out, and then we can start creating our functions that we need. So first we needed a semantic search class. Semantic search class. We needed a constructor. So let's go ahead and set that. We need to define our model. So that's great. Here's the model we need. So we can just put the name in there for now. We need to import sentence transformer. So this is the class. And we'll actually initialize the model because a string doesn't quite cut it. All right, so now we have all that. We have that. Outside of the class definition, create a new function called verify model. So let's do this. And we want this to create an instance of the semantic search class. So semantic search and prints model information. So we want to print model loaded and the dot model string representation. So I believe this f string will automatically stringify the max sequence length, max length. Okay, great. Where max length is the max sequence length of the model, that property of the model. So I think we did that. Find model, semantic search. So we did the model loaded. We did this, I think. Verify back in your semantic search CLI script, a new verify command that should call the verify model function to print it. Okay, so let's add our case in. We want to call the verify model. That means is we need to import the verify model. So that's going to be lib.semantic-search import verify model. And we need a subparser thingy. So let's grab it from here. Parser, we have subparsers. I think I'm going to set it up in the same way as the other. And I think the parse args comes last, so we can just make sure we're consistent with what we did before. That comes at the end. Okay, let's do a verify. And we can say, call this verify the embedding model loads properly. Okay, so that's cool. We can try and run this. The first time it'll be a bit slow because it's going to download all this, but it will save the model to some sort of cache directory by default. And so it should only be this slow once. Okay, it does some details. It does say the sequence length. Is that what it's expecting? Max sequence length 256. And what was it expecting here? Okay. Yeah, so what you'll see is there's a transformer architecture, then there's a word embedding dimension, a pooling layer, and pooling really is very simple. You're doing some like mean pooling, for example, is you just take the average of stuff to like compress it down, but instead of taking the average of everything, you average stuff around it to compress it down. Or like max pooling is you do the same thing, but you take a max. So it's a very simple idea, and then you normalize it. So we got the results we're expecting here. So let's go ahead. We'll just give this a shot. Go ahead and skip to submitting. All right, we passed. We can move on to the next lesson. Lesson 4 for model selection. You do want to choose the right embedding model. Now, if you're going to start with implementing a semantic search and make sure, and you want to like verify it's a good fit, see that you can get good results, my recommendation is to start with an API. Cohere and MixedBread have good ones that you can hit where you can just hit an API and they'll just deal with it for you. Now, over time, you may want to reduce cost or reduce latency by doing your own or have something more custom, but at least you have a baseline. So there's all kinds. There's general purpose ones that are supposed to do well in lots of domains. And so any kind of general document retrieval. There's ones for medical or legal or specific. There's ones that specialize in doing more languages. So depending on your use case, this leaderboard of models is nice to check out because you can look at a leaderboard based on, memory, number of parameters, how well it does. This is a good guideline, but you can't just pick the top one and use it and trust it because there's a lot of accidental, well, depending on who you ask, how accidental or on purpose it is up in the air. But there's a lot of leakage where models are overfit to the testing set. They're not supposed to see that data, but there's a lot of leakage and crossovers where it may not be right. So the Google embedding models tend to be good. There's quite a few. The Ch1 ones tend to be good. So take these with a grain of salt. Pick some of the ones that are in the right range that makes sense. If you see one that's, 10x smaller than the others in its area and performs 10x better or just as good with them, try it, but be wary. It might be that there's some measurement error there. So this is helpful, and you can sort by what kind of domain you're looking for or what kind of languages you're looking for different benchmarks there, human benchmarks, etc. So that's a good thing to check out when you get there. But again, I wouldn't necessarily jump to the specialized, medical ones. I would start with the API, see how that does. If you need lower cost or latency, then compare like a general one to a specialized one, because even a specialized medical one may be trained to, some data sets are very specific to like graduate level medical school exams. And so if your use case veers too far off from that, you might start to see degrading results. And so you do want to measure and check. So why is it important to choose the right embedding model? Different models vary in speed, quality, and suitability for specific use cases. That sounds good. Okay, what else? OpenAI will give you those sweet API credits. I think OpenAI should give me some more some credits. I would love that. They produce identical results regardless of context. That's obviously not true. We just saw a leaderboard where there's lots of different things. A general purpose model will always perform a domain specific or multilingual model. That's not true as well. So let's move on. All right, so vector operations. Vectors are lists of numbers that represent points in space, direction, distance, or magnitude from the origin.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
When it comes to things like semantic word embeddings, a vector's direction and distance from the origin represent the meaning of a word. Imagine a giant 2D space where this area has words like happy, joyful, and excited clustered together, while another area has words like sad, depressed, and angry. Similar words have vectors that are closer together in that space, while dissimilar words have vectors that are further apart. Let's look at two vectors, 0.5, negative 0.2, 0.8, 0.1, 0.9, negative 0.3. We can add vectors element by element. So 0.5 from the first vector plus 0.1 from the second vector gives us 0.6. Negative 0.2 and 0.9 gives 0.7. And finally, 0.8 and negative 0.3 gives 0.5. This is vector addition. And in the context of semantic embeddings, it means this concept mixed with that concept. For example, a vector for family-friendly movie plus a vector for horror movie will give us something like a family-friendly horror movie. Vector subtraction removes concepts. It's like saying, I want this, but not that. So take 0.5, negative 0.2, 0.8 minus 0.1, 0.9, negative 0.3, and you get 0.4, negative 1.1, 1.1. For example, horror movie minus bear movie will give us a vector representing something like a horror movie without bears. So vectors are lists of numbers. That's what an embedding is basically. So we need to be able to manipulate them just like we can add and subtract numbers, just like we can calculate distance between points on a graph. Just because we can do all this, we can also do this with vectors, with more vectors. And so the idea here is we want to be able to calculate distance between vectors. So these represent a distance. Now in two-dimensional space, we can you think of it as rise over run or something. In a vector, when we add them, you can see we can do 0.5 plus 0.1 is 6, and so on and so forth. And so we can add these sequentially. Negative 0.2 plus 0.9, which gets 0.7 there. So we can solve this with a loop, actually. So let's go ahead. So we have this add vectors. So this is going to be in here just to learn the concept. We'll return the sum as the new vector. So if the input vectors do not have the same length, we want to value error with a helpful message. Okay, so we can say if the length of vector 1 does not equal the length of vector 2, then we do exactly what it says and we can raise a value error. Value error, vector lengths must be equal. Cool. And we'll do the same thing for the subtract. So we can copy that over and check. Next, we're going to iterate over the indices of both input vectors. And you can see add, subtract the elements. So let's go ahead and do this for the add. So for I in range length of the vector, and it doesn't really matter whether we do vector 1 or 2 because we're getting a number here and we know they're equal. So we can do either. We can have a list and we can say results.append the vector 1 position with the vector 2 position. And then we can return our results. Okay, so that's one way to handle it. So we can see clearly what that is. I think we could also, if we wanted to be fancier, we could say like value 1 and value 2 in zip, like vector 1 and vector 2 together. And then we could, instead of indexing in here, we could kind of zip these together. So that's another option. Let's just keep it a little bit more verbose here. We get an index, we go through every single one, and we index in. And we're actually going to do basically the same thing here. Iterate over the indices of both and subtract the second vector's element from the first and return the resulting list of differences. So let's go ahead and run it for past, and we'll see that's exactly what happens. So Let's submit it. All right, very good. So vectors are lists of numbers that represent coordinates in space. So this is lesson 6 on dimensions. 2D space is easy, 3 units right, 2 units up. 3D is a little bit trickier, but you can still visualize it. And eventually you get to, I think we had over 300 dimensions in this, and sometimes you get 1,000 or 2,000 dimensions. It's hard to visualize. So if we think of how do we visualize this, and we can't. Geoffrey Hinton was godfather of AI. He's considered. He did a lot of really great work. And his advice when somebody asked him how to visualize 14-dimensional vectors is to visualize a 3D space like a cube and then say 14 to yourself very loudly. And so this visualization of it in space doesn't work because we have no concept where that is. In math, though, we do. We have lots of different dimensions here. Okay, so why do we use vectors of 100 dimensions instead of 2D or 3D? Oh, okay. So we could say a word that we are creating a vector for is very nuanced. For example, to create a vector that represents the meaning, the semantic meaning, let's see, for the word, let's say bank, can't be expressed in just 2 or 3 numbers. The definition is hard, even for this easy word, because it could be a bank for money, a river bank. I could bank on that. And so the word embedding must contain a lot of information. Cool. So let's see what it tells us. I must have remembered it from the solution. Okay, you explained well. High dimensional embeddings must contain a lot of information. Yeah, so that's that. All right, let's move on to lesson 7, the dot product similarity. So we want to measure similarity between vectors. We've talked about this distance and how do we do this. The dot product's going to show how if they point in the same direction. And the way we do it is we multiply these elements together. And so we can see for the dot product of these two, instead of adding or subtracting, I'm going to take 0.8 times 0.5. 0.5 times 0.4, 0.5 times 0.6. So we get these 3 numbers after doing that, and then we add them all up. So that gives us the dot product. The bigger the final number, the bigger the dot product. It'll be negative if they're in opposite directions. And so, yeah, let's go ahead and do this. NumPy's library, I mentioned it before. I think it stands for Numerical Python, and it does a lot of linear algebra operations that it can just do this for. And it's very fast because under the hood, it's working in C and not Python. And so that's a library to get very familiar with, but it's good to know the foundations. So let's go ahead and take care of it. We want the same length thing, so let's add that. So if the length of vector 1 is not equal to the length of vector 2, we'll raise a value error. Vector lengths must match. Okay, iterate over the indices of the vectors. Again, we maybe use it for this. So for I in range, length of a vector of one of them, doesn't really matter which, multiplying each corresponding pair. So we'll need to save that somewhere. We'll say results.append vector 1 of I times vector 2 of I. Great. And then we need to sum them. Okay, so this was a little bit of a waste. So let's start this at 0 and let's actually just append to this. This can just be a result. So now we just append to that. So that gets our running sum and we can return the result. Okay, cool. Looks like we passed. All right, very nice. We can move on to the next one. All right, lesson 8, cosine similarity. So dot product works, but the magnitude of the vector, meaning like how big it is, has a big impact. As you can see, there's a direction. We talked about that being related to the meaning, but there's also how long it is. And so these point in the exact same direction, meaning they should have a very similar semantic score. Very, very semantically similar, but they might be quite far away simply because one is bigger and stronger magnitude-wise, and we don't want that. We want to normalize. In our case, we usually don't care about the magnitude, just the direction, and this magnitude is a lot about confidence and strength, not necessarily meaning. And so we want to do a distance and a similarity measure that accounts for that, and that's called cosine similarity. This is the most common way of measuring similarity in vectors. However, it's important to note it's not always the one that's used. You want to look at what model you're using, and you look at the model card, like wherever you got the model from, like Hugging Face, and you look at what the model is trained with. If the model is trained to create embeddings that have a minimal cosine similarity for similar vectors, then you should use cosine similarity. If it's trained using a different metric, you should do a different metric. And so cosine similarity is the model. We'll look at that, our model is trained on. So let's go ahead and look at this. So we typically have values between -1 and 1. So it's kind of this unit circle. This is more convention than anything. And we calculate it in this way. So we take the dot product, and then we're going to normalize it by dividing by the product of the magnitudes. So how big they are. And that makes them kind of all on the same scale. So we measure how much the vectors align, and then we remove the length bias. So let's go ahead and do this. So first, we need to do the dot product. You can see we've got the dot product here. This is what we did in a previous lesson. And then we've got this Euclidean norm, which is going to give us the magnitude. And so let's calculate this. So if we aren't the same length, we'd like a failure. So let's do that. If length of vector 1 is not equal to the length of vector 2, then we want to raise a value error of vector lengths must match. Okay, check. Calculate the dot product of the vectors using the dot function. Okay, and then calculate the magnitude using the Euclidean norm. If either magnitude is 0, return 0. Good. Okay, so let's say length, we'll just call it length bias here. So we'll do the Euclidean norm of vector 1. Let's see here. So let's do vector 1 magnitude, and let's just do this one piece at a time so we can see. Vector 2 magnitude. So we can say the dot product is the dot product of vector 1 and vector 2. Okay, so we've got this dot product, we've got the Euclidean norms. If either magnitude is 0, we'll return 0. So let's say vector 1 mag is equal to 0, or if vector 2 mag is equal to 0, then let's return 0. And I don't think this is necessary, but I like grouping things with parentheses. I find it helps me read it a little bit better. And this is just because we just want to make sure we're not dividing by 0. And so then now we can return the dot product divided by the vector 1 magnitude times the vector 2 magnitude. So we can run that. Oh, we failed. What did we fail on? Pass, 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 pass. Fail. Okay, so this expected result is 1 and we got 10. So what did we do wrong here? 1 times 10. Okay, so what should it be? Let's see, the dot product should be 10 plus 40. So we got the dot product, we got these two. Our actual results here. So we should be, did I have something wrong? So the magnitude of A times the magnitude of B. So we have the dot product of A and B. We did that, divided by the magnitude of A times the magnitude of B. This might be a bug. Let's ask Boots. Boots is always helpful. He's never lied to me. Where does this fail? Boots. I am getting one failure in the run. Do I have a bug, or is the answer solution incorrect in this case? Oh, okay. Yeah. Nope, that's fair. That's fair. This would be vector 2. Okay. I lost 50% of my experience for that. No. Okay. All right, lesson 9, why cosine similarity? Well, you want to use the same metric that our embedding model was trained on. That's the simple answer. So if we look here, we can say we fine-tune the model using a contrastive objective. Formally, we compute the cosine similarity from each possible synonym pairs. So because they use cosine similarity, that's what we want to use. If they use some other similarity metric, which is rare, but it does happen, you want to match whatever the model does, because the model is not going to do well if you use the wrong similarity metric. I'm going to transcribe here. I don't want to type. We use cosine similarity because that's what the model is trained on. I look at the model card for our model, and it explains that it's trained with cosine similarity, and because that's part of the training process, we need to use it in search because the model is explicitly trained so that semantically similar things have a small cosine similarity, so we need to measure that same thing that the model's trained on. Yay, okay, I passed. I guess that means I know what I'm talking about. That's a good thing. All right, we have some text embeddings. We talked about text embeddings. We loaded our model. We could verify it was loaded. Then we took some side quests to understand what vectors were, which are what embeddings are, and be able to see how we can measure distance between them and do all that kind of stuff. And so now we're ready to generate the actual embeddings to work with. These are case insensitive often. They handle punctuation. It's a little bit easier to feed them in. There's a tokenizer that'll handle this for us that the model is trained with. Yeah, so it's trained with a unique tokenizer, and you have to tokenize the same way the model was trained on. And so you can read a bit more about this. And let's take a look. Let's take a little side to look. Can you give me examples of some special tokens that are used to handle things like end of document, end of sentence, capitalization, things like this that a lot of tokenizers use? Let's use, I'm going to use it up for this, but that's okay. So just like this. So often there's things like padding where they will pad it. This just means that, to make every vector the same length, they can pad it. But then there's also a token, depending on where it's used, for unknown. Maybe there's a word or something that shows up that can't be represented with the tokens, for a very unusual word or maybe a very unusual misspelling. There's, ones to indicate are there start of a sentence or sequence. There's end of sentence. And so there's all kinds of tokens. There's ones for could be some for capitalization, could be ones for all kinds of things on how they're encoded. And so these things are kind of accounted for in these tokenizers. Let's go ahead and get some embeddings here. In our semantic search.py, we're going to generate the embedding and input the text and use the encode method. Okay, so the encode method, that's pretty common to encode text to whatever. So the embeddings. So we can generate the embedding, and I think it was self text. We can do some error handling here. If there's no text or it's just a space, we can just raise a value error here. Must have text to create an embedding. Cool. So we took care of the first one. Use the encode method to do this. Okay. So let's do self model.encode. Encode, not encode. All right. And so we see we have sentences. So sentences is a union, a string, list of string. So we're going to go ahead and pass it in as a list. That is most common because that means you can do a whole bunch of them and generate a batch of embeddings when you want. And so we can just do that. And then let's take a look at the documentation for this. It expects a list of inputs. Okay, but we're only passing one. It also returns a corresponding list as output, but we only care about the first element because we're only passing in one input. Okay, so we can do that. It's fine. But return the embedding using the first index of the result. So we can just return this. Very good. Okay, so this should generate an embedding, and I bet we're going to add it to the CLI. Add a new top-level function to the same module, embed text, and then add that to the CLI. Okay. So that's great. Create an instance, get the embedding. Okay, so it's embed text. So we're going to print this. We're going to semantic search. Did I have anything I need to pass? No, I did not. Very good. So then I'm going to do the generate embedding with the text, and I can call that the embedding. So that should print out everything we need to add this to our search CLI. Okay, we can add our subparser. So this would be the embed subparser. And we can call this, what did it say to call this? Embed text command. Okay, embed text, case, embed text. We need to do embed parser dot add argument. We can double check what we did for consistency. Add argument, good, text. We had a type and a help, and that was all we did. So let's match that. Type equals string because we were casting it to a list, and then help is equal to text to be encoded. And we have embed text, which is encode text with embedding model. Okay, so that should work. Let's give it a shot. Let's run it. See what we get. Luke, I am your father. All right. 0.043, we did get that. 0.016, we got that. 0.035, good, we got that. I think we're good. So now we've got embeddings. We are in good shape. We pass. Okay, lesson 11. This is for document embeddings. We just embedded a string, so let's do it for everything. We need to do it for a bunch. And because when we do it for a bunch, it's going to take a good amount of time and compute, we're going to want to cache it. So we're going to want to save this in a file. NumPy I mentioned that as a library for linear algebra operations earlier, is a really good option for this. You could store it in several formats, but a NumPy file is a really great start. That's called a vector store. There's lots of other vector stores. LansDB is one. You can use Mixspread as a cloud API that can be a vector store. There's a SQLite Vec, which is a SQLite extension to be a vector store. There's a Postgres one. There's a whole bunch of vector stores you can use. We're going to use this NumPy on disk one to keep things simple so we can understand the concepts. So let's get started. We need to install some dependencies. So let's go ahead and do that. uv add NumPy. If you want to get on someone's nerves, just call it numpy. That's what I like to do. So we got numpy installed. Whatever you name your semantic search library module, we need to import it. That makes sense. Okay, so we need self-embeddings, self-documents, and a document map. So the document map is going to go from document IDs to the documents. And we're going to want to store the documents and the embeddings, and then build embeddings. All right, let's just jump into this. And so then for the build embeddings, we're going to want to go through each document. The key is the ID of the document, and the value is the document itself. Create a string representation of each movie and store them all in a list. So that's the doc title description. We did that similar thing when we were getting ready to tokenize for keyword search. And we use the encode and put them in embeddings, and we'll save this in this cache. So we only want to build the embeddings once. And so then we need to load and create to either build or load and create and add it to our CLI. So let's just get started. We're probably gonna have to jump back and forth a few times, but that's okay. Semantic search, import numpy as np. That's just convention to always import it. It's so common and everyone does it like that. So you should too. Okay, and so we're gonna need a build embeddings from the documents. To build the embeddings, we need somewhere to save them. Let's do that. So we're gonna need a self.embeddings. The embeddings are gonna be, I don't know what they are, self.documents. So we need embeddings, we need documents, and we need a mapping, a document mapping. So the map definitely needs to be a dictionary. I don't have any embeddings or documents yet, so we'll leave those as none for now until we know what to initialize them with. If we build the embeddings and we're given the documents, then we can store the documents. So we have that. So maybe starting that off as none is fine. So we need the movie strings as well. And these movie strings are what we're talked about here somewhere. So we did those 3 steps. Add a new build embeddings. Documents is a list of dictionaries, each presenting a movie. Okay, so that's going to pass in. For each document, add an entry to the document map, where the key is the ID and the value is document. Okay, so for each document, that means for loop. For doc in documents, so we have the document ID. The value is the document itself. So then we got self.document map. So that's the ID, and then the actual document itself. So we have the document ID to document. Okay, so we've got that. We can now look that up nice and easily. String represented each document. So the reason we need this in a list is because we saw in the encode here, we are passing this as a list, and so we want a list of to use, I think. No, because this doesn't process them in a batch, so maybe not. List is just convenient. So movie strings for documents. So let's do movie strings.append. Okay, so we have the document title and the document description, just like it was asked for. Okay, now we need to use the encode method on the list of movie strings. Oh, I was right. Okay. Self.model.encode. And so when we do the encode, we can pass in all of our movie strings in a batch. We don't want to index in as D0 like we did before, because we don't just have one. Show progress bar of true. Show progress bar is true, and this will be the self embeddings. And so, okay, so we've done this. We've got our embeddings. We've got our documents. We have our document map. So we probably just need to cache it using numpy save. So cache movie embeddings numpy. So numpy.save is file or file name to which the path is saved. Array data to be saved. Save an array to this. Array like. Let's see if it'll take, oh, so it should take this. So we could do self.embeddings. And then we'll also return self.embeddings just for convenience. Okay, so let's see, does that all work? Not convinced I'm using that right. Examples. Okay, so here's an example. We've got it. NumPy save, that's the out file, and then that's the variable. Okay, so this is good. Very good. So I think that's right. Okay, we need to build the methods only once. So let's go ahead and create this, and we're going to populate everything and then check if it exists, and if it does, load it. Okay, let's just get started with that. Load or create documents. Okay, so we have this. This first part's kind of the same because we have the documents, and so we can save this here. Oh, if we're building it, we want to reset, make sure that this is reset. So if you build it multiple times, yeah, because there could be some leftovers if the IDs are different. So we want to make sure to reset this. Okay. So this should be the same. Pretty sweet. So now we need to check to see if it exists. And so we have this previous path here, but I feel like when we did in keyword search, let's see, where did we do this? Didn't we have a whole bunch of paths somewhere? Oh yeah, we stored them up here so we could reuse them in both. So let's do the same pattern here. So we can say self.embeddings path equals this, and we'll use import path, the standard library for pathlib. That's just nice to use. Okay, so this is our self.embeddings path. Okay, so then we can go through and we can say for documents, we can create our document map. So we still need to do that. We might need to do this, but if we do, we can reset it. So let's go if self.embeddings path exists. So we can check to see if it exists. If it does exist, then our embeddings is just numpy.load, and let's see how this is used. Numpy.load, okay, and then just the file path. So if it exists, we have that. Let's take a look. Okay, check if it exists. If it does, load it, store it there, verify the length of embeddings is equal to the documents. So that makes sense. We want to make sure, because we're updating the documents here, and now we want to make sure that the documents and the embeddings match, that we have the same number, just as a safety check. So let's do that. If the length of self documents is equal to the length of self embeddings now, because now that we've updated them both, then I think we're going to return, right? Then return self embeddings, yeah. And so this exits the function. If this isn't the case, then we want to do something else. We would probably want to build the embeddings. Otherwise, return this of rebuilding the embeddings. So that's the function we created before, right up here. This already returns the self embeddings, and so we can return self.build embeddings. And what does that take in? I think that takes in the documents. So we can just give it the documents. Okay, so we did all that. So now what we got to do is we need a verify embeddings function, and then we'll need to add that to the CLI so we can verify it. Cool. So we verify the embeddings. That should take in the documents. We want to initialize our semantic search class. We're going to want to load or create the embeddings with the documents. So if it's cached, it won't rerun, right? Of course, we actually need the documents. Oh, I see. Yeah, we're not going to be passing this in here because that would be passing in our entire data set into the CLI. So what we need to do is we need to, from our search utils, import load movies. So yeah, let's do this. So we get the documents, and that's equal to load movies. And then now we can pass that in. So we took care of that. Load the documents for movies JSON into a list. I feel like it was already done, but let's just double check that. Because I feel like, oh yeah, so we took this data and then we indexed into movies. And if I remember right, the movies, let's just jump to the top here. Yeah, it already is a list. And so I think that should be taken care of. And then we print the number of documents and the shape of the embeddings. This actually returns embeddings as well. So we can just do this, I believe. Great. Okay, so add a verify embeddings command to your CLI script that just calls that. Okay, let's do this. There's no way I got all this right on the first time, but that's why we can check after this small step. Verify embeddings. We can import this. All right, cool. We'll of course need a new parser for this. This general verify isn't very clear, but that's okay. We'll leave this for now. Let's go ahead and see if we can run this and see how we did and fix all the bugs so we go. And I guess while we're at it, we can make sure that we actually are creating a cache via embeddings. Very good. And that's the NumPy file. So we seem to create it. That's good. We got a little loading bar. That's good. 5,000 vectors in 384 dimensions. Okay, so I think we're good. I think we can submit. All right. So now we've got embeddings for all of our documents. And so we're really clipping through this. Lesson 12. We have embeddings for every document, every movie. And yeah, all we need to do is calculate the distance between that and our query, which means we need to have an embedding for a query. Yeah, we can't, basically we have these and we can't say which one's closest to bear. The math ain't mathin'. And so we need to convert bear to an embedding as well. Now, we need to make sure that whatever we do on the documents, we embed our query in the same way. And so let's go ahead and do this. So we implement the query embedding functionality. We're going to add this embed query text function that does it. We already have the functionality, and we just need to add it to our CLI. So let's do this. All right, so let's go down and let's embed query here. So we have our Semantic Search class. We can generate embeddings on our query because I think, does that already handle the casting to a list? I don't remember. Yes, it does. Oh, it was right. It was right on screen. Okay, so that already casts it there. There's some specific print stuff for the tests. So we can dump those in. This is going to print the query. This is going to do the embedding. This returns the embedding, so we can do that. And the shape, so it can do the test. We're going to need to add this to the CLI now. So let's handle that. The CLI should be embed query, so we can handle that. Very good. Cool. So we can do this. We're going to embed the query. This is going to be the query. This is the user query to be encoded. Encode the query with embedding model. We already did this. We already did that. Let's see if we pass. Shouldn't have done that. Okay, let's take a look. Failed step 2. Okay. So let's do this one at a time here. I'm going to zoom out just one. I hope everyone can still see it, but I need to be able to see what's going on. And let's do one of these queries at a time. So it's expecting 0.072. Let's see what happens when I run this. Oh, it doesn't even do the thing. Okay, let's see why that might be. So it doesn't go. This needs to be embed query. I gotcha. Okay, that looks better. Let's go ahead and try again. All right, failed step 1. All right, let's take a look here. Expected to contain 5,000 vectors and 384. So what does it get here? Okay, so we're still not getting this. Okay, so what are we getting? UV run, verify embeddings, funny bear movies, add a new embed query. Oh, so this is running the verify embeddings. Okay, so that's the embed. So this should be the embed query parser probably. Is that the whole issue? Nope. Okay, verify embeddings is here. Yes. All right. So what in the world's going on here? I am going to zoom out one. Sorry, people. Okay. Semantic search CLI.py, verify embeddings. So what should this do? Okay. So this verify embeddings should go in down to, so this should be here. So this should this be verify? Oh, hang on. Verify embeddings should be this. How did that get tangled up? Okay. So I'm back to passing that. Let's take a look at this one. 0.72, 0.14. Okay, so now we're at here. So now this one, this embed to query, should take in the query. So we got 0.72, 0.14, 0.001, 384. Okay, so now this is looking better. I probably should go through and check the last couple, but let's just give this a shot. I've already failed several times. What's the worst that could happen? Okay, we are good. So word to the wise, be careful about your CLI stuff. All right. One important thing I mentioned earlier is you really need to use the same embedding model for your documents and your queries. It has its own lesson because this is a huge bug that I've seen in lots of systems. And I've done consulting work with a lot of companies where this ends up being the problem, where there's a different model or something accidentally where maybe they just have two separate functions. The easiest way is to have well refactored code and just be very careful about this, that you're making sure you're calling the same model and you don't have duplicates and you don't update. One of the things I think is really hard is with AI in particular, whether it's embedding models or LLMs or stuff, that I think is one area where it's even harder than a lot of areas, is that if you do things wrong, a lot of times you won't get an error. And you won't even get a failure. And you might even get reasonable results in a lot of cases. And yet, it'll just be subtly worse than what you should be getting. And so it won't feel like a hard error. You can't easily do an assertion for it unless you put a lot of time into it like we did for this course. And so this is just something you really want to be careful of, because it's very possible that you get vectors of the same length that are trained on similar data sets. And so when you run things, you get answers that seem somewhat plausible but aren't very good. And it could be that your system is just completely, totally broken with the wrong embedding models. And instead of getting an error, it's well, I have two vectors of the same length. I can do math. And it just gives you, not the best answer. So you want to be very careful of that you're using the same one. Why must you use the same embedding model? Oh, I should have just transcribed all that. Let me do that again. You need to compare apples to apples. A model is trained to generate embeddings so that the semantic similarity of two embeddings that it outputs are very close. And so if you use two different embedding models, They're going to be on two different scales. They're going to be mapped to different mathematical space. Even if they have the same number of numbers or the same dimension, which they might not, but even if they're the same dimension, when you measure the distance, it won't be an accurate comparison because you've put them through two completely different systems that are potentially trained on different data sets. To get an accurate calculation, you need to embed queries and documents into the same space, which means using the same model. All right, I passed. So implementing semantic search, we have all the pieces. We have cosine similarity, which we calculated before. We didn't do it locally, but we did it in the browser. For how to measure the distance, we can create embeddings with our model for the documents. We've already done that and cached it. And then we created the embeddings for the queries. So we have everything we need to do a semantic real search. So yeah, let's do it. Cool. So let's add a cosine similarity function. So we need to do that. We did this before and we did it manually. We're going to use NumPy, which is optimized and written fast in C. NumPy is a function, a library you want to get ready. Oh, we don't have to implement it again. Okay. So you can see instead of our own dot function, we're using NumPy dot. Instead of our own magnitude, we've got this here. But that's really the difference. We saw how to do it the slow way in Python. So let's go ahead and add this. We can put this right here. Okay, we've got our cosine similarity. Great. Always feels good to mark it off. And now we need a search method. Let's see if we're going to check if our embeddings are loaded. So at the top here, we've got this embeddings. If we have loaded them, then if we've built them, it'll be here. If we've loaded them, it'll be defined here. So we can just check and say if embeddings is none, then we can raise a value error. Embeddings are loaded. Okay, they gave us a specific message, so let's do this. Use that. They might be testing for this. Okay, generate an embedding for the query using self.generate embedding query. So we already created that, and then calculate the cosine similarity. Okay, so we can say query embedding. Okay, and so then we need the cosine similarity between the query and all the documents. And so that's what it's going to tell us to do, I bet. Calculate the cosine similarity between the query and each document embedding. And so we'll have a list of the similarity score in the documents, and then we'll sort them. So let's go through and we can say, let's see, similarities. Sure. So let's go for document embedding in self.embeddings. So we're going to go through every embedding, sort the similarity score. Okay, so for each embedding, we'll go similarity is equal to our cosine similarity of between our query embedding and our document embedding. Okay, and so then the similarities can be our similarity. We probably want the actual documents as well. So let's do that. The document embeddings and then docs. So, okay, so we have our similarity score document tuples. We want to sort the list, so we can do similarities.sort, and then we can sort it by, which is it? So let's do lambda x. We want to sort it by the similarity, and it'll by default be ascending, but we want them in descending order. Yes, we want them in descending order. Great, so we marked that down. So we've got that, and we want the top results up to limit as a list of dictionaries. Okay. So we can, for sim and similarities to the limit, we can probably do a dictionary comprehension here because we said we wanted a list of dictionaries. No, we want dictionaries here. Score, title, and description. Okay, so we have score, sim. So this is going to be score, and this is going to be doc. So we can do score, and then we can say document, what was it? Title and description. I'm not sure that should be a list comprehension. I'm going to be honest there. In your CLI script, add a new search command. It should accept a positional query string, a limit. Okay, let's create this here. Search. Okay, so it needs a limit and a query. So let's do query and then a limit. And that should default to 5. Did we have this something in the search utils for this? Oh, I created a constant. Maybe not. Okay, limit equals 5. That's our default. It should create a semantic search instance, load the movies, and then call the search method. Okay, load or create embeddings, and then search with the query and the limit. You know, I don't really like this list comprehension, so I'm going to break it out here. So let's call the result this, and then we can say res.append, and then we'll append the dictionary, and we'll make this a list, and then we can just return the result. I think that's a little bit more readable. Okay, so we search for the query and the limit, and so then we have search results, boom, 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 load movies and load/create the embeddings. Load or create embeddings, movies, self documents. Oh, okay. Gotcha. Yeah, I need the documents in here. So we can say movies equals load movies because we already have that. And then this goes in here. So that should load or create the embeddings. Then we can do the search, just like here. And then we can print the results in this format, hopefully. So let's try that for in search results because I'm this. Okay, so it looks like there is the number. So let's enumerate to get an index for that. So it's index and then result. Okay, so we have print index, a period, space, and then this looks like the title. Result title, is that in there? Yep, result. Oh, this is not quite going to work. Score, title, and description. Yeah, so I need this to work. Score, title, and description. Okay, that should work better. Sweet. Okay, so we have the score, we have the title, and then it looks like we do parentheses, score, colon, score, or res score. And then it looks like we have a res of description. There's some sort of truncation. I don't know what it is exactly. Let's just start with 100 and we'll go from there. Okay, let's start working through any bugs that we created, which I'm sure there's something. Oh, I didn't even add it to the CLI, did I? Okay, let's add to the CLI. So we should be able to now take this search, import it. It should be a CLI called a search command. Great. So this could be the search parser. So we want the query string argument, and a limit argument. Sweet. So a limit argument. This will be a number of results to return. And then the query is the user query to search based on search for a relevant movie. This can be an integer. All right. I'm not sure I did all of those completely properly. We want this to default to 5. Okay, we had those instructions. We did want it to be an int. We have the limit, so we should be good there. Oh, dash limit. Okay, that should work. So now we have case search, and we can do search with args.query. And is that how that works? I don't know that I did the syntax right. Okay, well, let's just give it a shot. Well, let me just try it running it like this first. All right, let's see what we got. Okay, no key error for description, line 66 in Semantic Search Pi. Okay, line 66. Okay, so we indexed into description. So this has got to be the full description. Perfect. Let's try this again. Okay, this appears to be the right shape. This might be rounding a bit too much. They have it limited to, okay, to 4 decimals. So let's see if we can do that. Forget if that's exactly how I do it, but let's see if that's right. Oh, cool. Okay, so that seems to be spitting out kind of the right stuff. So let's see if we can run it. 4094. Bear, great bear, bear for punishment. So the bear for punishment, the great bear, bear. Okay, so we're doing pretty good. I'm going to go ahead and just skip ahead to the submission. Okay, very nice. We passed. All right, lesson 15, locality sensitive hashing. So what you saw is the way we calculated the distance is we looped through and we compared every single vector when a user queries, and it's pretty slow. Now, if you've got 500 documents, just do the loop. Don't like over optimize and do all this. It's probably not slow enough to matter. If you're doing something at enterprise scale, however, it can be a big difference. It can be very slow. So LSH is a way of grouping similar vectors into buckets. And so it's basically this way for hashing. You can only look at ones in the same bucket, and it's a lot faster. Now, it is a trade-off. It does speed things up. It can miss some similar vectors. In most cases, this is good enough that you're not going to have any issues, but it is a trade-off. And so you should only use it when computation speed is better than perfect accuracy. And so you should try and see what your latency is and only use it if your latency is unacceptable. And again, at most scales, for most projects, for the most data sets you're trying to retrieve against, it's not an issue because the calculations are pretty fast. And the most expensive part of the operation is actually creating the embeddings, but that's all cached. That's a one-time operation. Yeah, what's the main trade-off when using locality-sensitive hashing for semantic search? Speeds up search, but can miss similar vectors. Perfect. Okay. It reduces memory usage, but makes searches take longer. Searches do not take longer. Improves accuracy, but requires more memory. It does not improve accuracy. Guarantees finding. It doesn't guarantee anything. Okay, so let's move on. Vector databases. Okay, so I kind of talked about this before, actually. You have something like a SQL database, which has rows and columns. You have queries with where clauses. You should take the SQL course. A vector database works in kind of the same way, but it's optimized because you have these like really high dimensional vectors. And, theoretically, you could have a SQL table where you have 400 columns, each containing a number. In practice, that doesn't work. It's optimized for the very, very high dimensional vectors. It has built-in optimized similarity search. It does like this like nearest neighbors type thing. And it works really well for this kind of semantic search. You pretty much almost always want to use one. There's very simple ones like LanceDB, and there's other ones. If you're already using Postgres, there's an extension for that. There's one for a SQLite extension if you're using that. So there's lots of options, and there's lots of ways to speed it up. Go ahead and check out these if you need it. But again, I would encourage you not to worry about implementing some fancy optimization until you know you need it, because these comparisons do happen quite quick. Yeah, Weaviate's another. Why would you use a vector database instead of just storing embeddings in a NumPy array for a production RAG system? When you store in a NumPy array, there's a few problems. First, you're saving it on disk. And so if your data set gets too large, that can eat up storage cost. Second, persistent storage becomes very difficult in database backups because you then have to somehow replicate that to other systems, especially if you do like horizontal scaling. Now you have to replicate this local file to every system that you do. Then you also have the problem of you have to load the entire thing into memory in order to do it, and you can't optimize the indexes. And so loading your entire data set into memory for queries is often not feasible. There's a combination of performance issues, memory issues, and other issues just for redundancy and backups. We'll see if I covered what Boots wanted me to cover. Oh, distributed architecture. Yep. Okay, great. All right. That's a wrap. That's chapter 4. All right, chapter 5 on chunking. Okay, so far we've gotten queries, we've gotten documents, and we've created an embedding. And that works pretty well unless the document is super big. You can think of like an extreme case. What if you want to search across a book? How do you break the book up? Our embeddings, I think we're using a model that has 384 numbers in it. It's an array of 384 numbers. That's probably sufficient to encode the understanding of embedded, that one word. It's also probably sufficient to embed the meaning of this entire paragraph. Like, what is this paragraph about? It's probably not enough to embed the entire meaning of this lesson, for example. And it's certainly not enough to embed like the entire meaning of like a research academic paper or a legal filing or brief or something. And so you need some way to break it up so that you can search for chunks, search for it in bits, embed it into small bits. It's also important because sometimes what you're searching for is lots of different movies where returning one movie is what you want. But there's also other times where I want to search a book. And just saying like, hey, the answers in this book is not always the most helpful. You want to know what chapter or what paragraph or what section or what answers the question. And it's not always straightforward. So we need some way to break it up, and that's what chunking is. So the problem's here. Embedding tries to capture too many topics at once. We can't encode information that are dense. This comes back to there's a limit to what you can fit into one embedding. Effectively, when there's too many specific concepts get averaged out and you start getting irrelevant matches. We're going to start with fixed size chunking, and then we're going to kind of build into there and a whole bunch of other approaches. So really what fixed size chunking is about is we're going to say, hey, we're going to pick 50 words or something, and we're going to split it at 50 words. So every chunk is going to be about the same length. It's very easy to understand. It's easy to implement. It's fast to run. We're very in control of the tokens. There's some downsides, which we'll talk about later, but let's implement this. So what do we want to do? We want to implement a chunk command that accepts a required positional argument for chunk size, and then split the text into words on white space, create chunks by grouping in words together into a string where in is the chunk size, and then print the results in the following format. So let's create this as a function in our semantic search.py. We're going to call this fixed size chunking because that's what we're doing. We know we need some text to be in there. We know we need the chunk size, and we know we wanted the default chunk size to be 200. So we'll start there. Okay, so the first thing we need to do is we need to split our text into words. So we have this. So now we've got how many words. We can do our chunking. We are going to return a list of chunks. And to get these, we need to iterate through. So really what we need is the first chunk is going to be words 0 to 200. So that's the chunk size. The next one, we need words 200 to 400, etc. So we need something like this. So we know we're going to need a loop. We're going to need to loop through our words. So we know we need to start at 0. We know we can't go above the number of words we have. And we know we want to jump by the step size by chunk size. Yeah, so instead of going 0, 1, 2, 3, it'll go 0, then whatever the chunk size is, it will jump by that. So we've got this. So now in each one, we need to append, and we need to take the words, and we need a slice of the words. So we're going to start wherever our I is. It starts at 0. And we're going to go up to that plus the chunk size. Now the question is, this is going to give us, because we split this into a list, so then this slice is going to also be a list. So do we want to return a list, or do we want to put it back into a text? And I think we want to put it back into text so we can join. So we split it into words, we get a list, and then we go through and we get chunks, and then we can return our chunks. Okay, so that works. And let's make a function that does this for our thing. So we go text, chunk size. So this is like our API that returns data. And then we can go and say our chunks are equal to fixed size chunking. And I think there's like some sort of print. Let's see, positional required argument for the chunk, whatever. We haven't done the CLI command. Split in the text into words on white space. We did that. Create chunks by grouping in words together to into a single string. Okay, so that answers our question. Print the results in the following format, showing the total number of characters and the content of each. Okay, so we need to say print chunking length text characters for chunk and chunks, because we need to loop through this. We need the index location so we can enumerate. And so I guess we print our index and then our chunk. And I think that should do it, right? Results. Okay, and then I guess we just need to add the chunk that has the text and then the chunk size. So let's do it. All right. So let's add the chunk. This should call whatever this function is, chunk text, which means we need to import chunk text. And then we need to add a parser here. It's going to take 2 arguments. So we can call this the chunk parser. We wanted chunk, we wanted dash chunk and text. And the chunk was supposed to default to 200, I believe. Okay, and let's fix all the help text here. Chunk a document. The text is document to be chunked. And then this is the number of words in each fixed size chunk. Okay, so we split into white space. We got the chunks. We go through and we append the words together. And then we print. Okay, I think we got everything. So let's go ahead and start to fix all the bugs. Unrecognized arguments. What did I miss? This needs to be chunk size, and this needs to be text. Let's try again. Unrecognized arguments, chunk size. I put it in the wrong one. Chunk size. Okay, let's try this yet again. Chunk text missing one requirement argument. Okay. args.text. args.chunk size. All right, like 4th time's the charm, something like that. So I ran this, and what it's supposed to give is 70 characters. This is a test text. Okay, so this should be 1, not 0, with more than 10 words to see how chunking works. Okay, so this is good. I just got the wrong index locations here, so I can go ahead and fix that. So I could add it here. I'm just going to do this. I think that'll work fine. Yeah, I think that looks good. Okay, let's go ahead and try running and testing this. I'll just YOLO submit, and we'll see how it goes. All right, test pass. All right, we did it. We did our first chunking, so this is exciting. All right, chunk overlap. A lot of times what comes before is relevant. If you think about chunking this up with the wrong way, you could say in the climactic scene, the bear attack was terrifying, the stunning and innovating special effects. And so it's like, this chunk here doesn't tell us anything. You know, in here, it says the bear attack was, and it's like, okay, well, this, I guess it says there's a bear attack, but it doesn't say if it's like, is it a good climactic, a bad, is this positive, or is it disappointing? Was it exciting? Was it, what is it? So here he says terrifying, so great. But in this chunk, if we embed this separately, and we said like, oh, well, let's see, like bear attack. Well, this chunk doesn't know anything about a bear attack, and so it's not relevant at all. But we do want to know that the bear attack was terrifying. And then we see the stunning and innovative special effects. It's like, okay, well, we don't know anything about what it led to. And we see record-breaking sales. Well, okay, we don't know anything about what led to that. And so we're like, if you search for something like what led to record-breaking sales, it's like, well, this is the only chunk that matches, but it doesn't actually answer the question, even though it's just a few sentences. And then you could solve this in a lot of ways. The simplest and the first, that's actually surprisingly effective, is you can have overlap. And so in the climactic scene, the bear attack was, and you see that instead of starting at terrifying, it actually repeats bear attack was. And so this chunk has the last words of the previous chunk. You know, this chunk has the last words of the previous chunk. And so you see special effects led to record-breaking sales. And so we have this, a lot more context and a lot more of this overlap. So you can test it. In general, 20% overlap works in a lot of use cases. So that's a starting point. But, you know, try it and see what works. Try a little bit more, try a little bit less. The more overlap you have, the more computationally expensive, but it's typically worth it in this case. So we're going to implement it. Add an overlap parameter on the chunk command. When the overlap is greater than 0, each previous chunk should show the last overlap words. Previous chunks are in the same format, so that means I shouldn't have to do anything. Okay, let's go ahead and give this a shot. So we have our semantic search here. If we want overlap, we can't jump based on chunk. So for example, if we want to go 0 to 200, the next chunk can't start at 200. It needs to start at like 190 or something, whatever, based on the overlap. So this step size parameter needs to change. So let's figure out what that should be. And it should jump by the chunk size minus the overlap, I think, which means we need an overlap parameter. Does it give us a default value? Print the chunks in the same format, the last overlap words. Okay, it doesn't say a default. So let's just put it here for now. Okay, so we have the step size. We want this. This is still good, but there's always an edge case with these chunks, which is what if you end up and the last chunk only has overlap? So what if you have something like, we'll just make a really stupid example, C, and we say, let's do A, B, we'll do a chunk size of 3 and an overlap of, let's see, C, D of 1. So we say, okay, A, B, C. So the next chunk starts at C, goes C, D, E. So the next chunk, the last chunk, should be E, because we'll have one overlap with the last. Now, we don't actually want this chunk, though, because this chunk doesn't help us. This is a standalone, but it's already encoded here. So this last edge case, we actually don't want to include. So chunk 1 is these 3. We have one overlap, which means it starts with the last token. Chunk 2 is these 3. We have one overlap, meaning the next chunk should start here, but it hits the end. That extra is already encoded. We want to get rid of it. So let's go ahead and account for this. So let's go with, we'll pull this out and we'll get chunk words. If the length of that is, so like if we go back to this example, the length of this is 1 and the overlap is 1, so we don't want it. So if the length of those words is less than or equal to the overlap, then we just want to break out of it. We don't want it append after all. We could change this to greater than an append in here, but I think this is okay. We chunks that append words, return the chunks. This should all stay the same as far as I know. Let's give that a shot. Let's just YOLO submit it here. I'm feeling confident. I've been on fire here. Oh, no. I should not have done that. Oh, no. Okay. That's what I get for skipping my tests. Okay. So what we need to do, args.overlap. We need to include the argument here. And we need, where is this? Okay. A dash overlap parameter. Okay. Here we go. Dash overlap. Don't have a default, so that's okay. Let's try this again. Okay, small little typo. Args.overlap. I see. Okay, this should be a comma, not a period. All right, so this is exactly why you should not just submit, and you should do that. Okay, let's actually do it properly and run this. We have another error. Chunk text takes 1 to 2 positional arguments, but 3 was given. Okay, args check overlap chunk size. So chunk text, I see. So here, I got it. We got to pass in our overlap. This needs to be here, and this needs to be passed down to fixed size chunking. Overlap, I don't know, like 7th time's the charm. Let's try this again. We should see this. This is a text. Test with 2 chunks. Great. Passed. Chunking 36 characters. Baratech was very terrifying. Good. 0 overlap means no shared words. Good. Okay, so I think we're in better shape now. So let's go ahead and submit now. All right. Very good. We now have fixed chunking with overlap. Oh, new challenge available. Semantic Search Basics interview. I don't know what this is, but let's click on it. Sure, I'll accept the challenge. Great. Okay. Imagine you're building a search feature for a site where users often type short, vague queries like cheap places to stay or how to fix my screen. How would you explain the difference between using a semantic search system on embeddings and traditional BM25 based terms? The kind of research users. Okay, so for BM25, it's going to match on keywords. So if you look for cheap places to stay, it'll return descriptions of things that have the word cheap, have stay in them. So it might look for those that are advertising themselves as cheap. How to fix my screen would look for fix and screen specifically. A semantic search based on embeddings is going to be a little bit more thorough. So for example, if you have a very short article on how to fix a screen, BM25 would work great, but like repair a cracked phone, for example, which would typically do for the screen, wouldn't come up. And so the semantic search system is going to return probably a wider variety, and the BM25 is really going to be dependent on the exact words matching. So you'd probably in this case want a semantic search or a hybrid search, which we haven't talked about yet. Cool. Hey, I liked that one. I'm going to do that. Service exposure plan. Okay. Oh, I'm jumping into the training grounds now. Okay. How'd you design okay, this is not about semantic search. I'm going to go back to my semantic search, I think. So that's kind of a new training grounds feature. That's super awesome. Okay, so semantic chunking. We often don't actually want to split on a word boundary, like in the middle of a sentence. TED explores themes of friendship. We probably don't want broken up and growing up. We want that in there. We would much rather have a slightly longer chunk that breaks on sentences or breaks on paragraphs or section or whatever. A lot of times, chunking on the semantics of the structure is really helpful because the author of whatever this document is wrote that, hopefully intentionally and carefully, and already organized it. Rather than trying to have an arbitrary rule to how to chunk it in a meaningful way that works with every kind of thing, semantic chunking says, hey, you know what? When this was written, the author of this piece, this document, organized it in a specific way, and let's take advantage of that. They know this document best. Let's try and break it into a sentence or paragraph or whatever. And so we're going to implement this now. And the thing is, you can do overlap and semantic chunking. This isn't an either or, and it really helps quite a bit. And so what we're going to do is a semantic chunk. We're going to have a max chunk size defaulting to 4. We're going to have an overlap argument, and we're going to, instead of splitting based on white space, to get into words, we're going to split based on regular expression. So let's break down what this does. Okay, can you explain, this is a great use of AI, by the way. Can you explain this regex step by step? All right, so R, raw string. The square brackets mean any one character from the set, period, exclamation point, or question mark. It matches one punctuation character. So this could be something you could look at, like we looked at string.punctuation before. You could try and be a little bit, if you wanted to match on every punctuation, but you could look at that list and see if there's others that you'd want to include. But this is good. A positive look behind. It says the match must be immediately preceded by X, but doesn't include X. This saying whatever we match next must come right after a period, exclamation point, or question. We don't capture the punctuation as the match. And then that means any white space character, spaces, tabs, new line, and one or more. So one or more white space characters in a row works. So matches a run of white space characters that come right after a sentence ending punctuation mark without including the punctuation in the match because of the book behind. So yeah, that's kind of what it does. So let's go ahead and implement this. We can make a semantic chunking function. We know we need the text, the max chunk size, which I forget what the default was we wanted, and we know we need the overlap, which I think was defaulted to 0. Default to 0, that defaults to 4. So we're good there. We got the boilerplate out of the way. All right, so we need to do the split. We're going to copy this. We don't need to recreate it. So we can do re.split. We actually do need to import re. This is the standard library for regex. Here we get the pattern and then the string. So let's do pattern. And then our string, our text. And so we can put that in. Let's follow the similar pattern for what we did. This is I guess instead of words, it's sentences. Theory. We want to give chunks, and we probably still want the same kind of step size that we had before. Let's see. So step size equals max chunk size minus our overlap. And so we still want to go through for I in range 0 to the length of sentences with our step size. So all this is kind of the same. We're just doing it at a bigger size here. Okay, so we need chunk sentences, and that's going to be equal to our sentences, which is I to I plus the max chunk size, if length of the chunk sentences, so it's the same thing here, is less than or equal to the overlap, then we're done. Otherwise, we want to append the sentence, and so we'll just join that back up. Chunk sentences. And then we do the same thing where we return the chunks, I think. So there's probably some logic here that could be, borrowed and refactored to have a more general chunking thing, since most of this is the same other than this regex, but let's just leave it here a little bit more verbose for now. So this is semantic chunking, and then we probably need to add it to the CLI. So here we go, semantically chunking. So let's do chunk text semantically, and this needs all the same arguments: text, max chunk size, and overlap. So this defaults through, and we need to go chunks is equal to our, what was that function called? Semantic chunking, where we pass all that through. We could probably borrow a lot of this stuff here. Okay, print chunking chunk characters, enumerate through the chunks. That's there. We're going to need to add it to the CLI, so let's go ahead and do that now. Let me see what it was supposed to be called. Semantic chunk. Okay, case is semantic chunk, and we should just need to call it with args.text, args overlap, args.chunk size. Did I put them in a different order this time? Chunk size overlap, chunk size overlap. Wait, chunk text is text overlap chunk size, text overlap chunk size, text overlap chunk size. Okay, I'm going to reorder these just so that they're in the same order, just for a little bit of consistency. Overlap chunk size. Okay, so then we need pretty much all of this. Semantic chunk. So this is the document to be chunked. Number of sentences in each fixed size and number of sentences. So this can default to, I think, a 4, and this was a default of 0. Let's see how we doing. Let's go ahead and use this run command, actually, because that does a nice thing. I don't have to bounce back and forth because it prints out what I was supposed to have gotten. It's not supposed to get that. Okay, I see. Max chunk size. This is supposed to be max chunk size. So this needs to be max. No, this one needs to be max chunk size. Perfect. Okay, semantically chunking 43 characters, sentence 1, sentence 2. So this works, but this was not right. So I missed some print I was supposed to do. Semantically chunking. So, okay, let's fix that. See, I learned from last time. I'm actually checking before I go, oh, this is not good. Let's fix that while we're at it. Okay, let's fix that. So this should be actually overlap and then max chunk size. Okay, cool. Let's give it another go. All right. Semantically chunking 40. So we're good there. We're good here. We're good. Okay, good there. Okay, here's a good test. First sentence, second sentence, third sentence, fourth. So that's great. Okay, I think we're in good shape. So let's go ahead and try to do this. We passed, so that's pretty awesome. So now we can chunk based on sentences and with overlap. So we're doing pretty good here. Okay, chunked semantic embeddings. We were able to chunk we were able to make embeddings. So let's make embeddings based on the chunks. So this is going to be similar to the embeddings created for full documents, but a little bit trickier because we need to map chunks back to the original documents. Meaning if we have a chunk that's the middle third of the document, we need to know that that chunk actually maps to a particular document. We didn't need to worry about that before because the chunk was the document, because it was all, there was no chunking. But now we just need to keep track of that. So let's go ahead and make a new chunked semantic search class that can handle this. So right under the semantic search, let's go ahead and do this. I think it's in mode. Control KZ. Command key. Well, that didn't quite help. I wanted to get rid of the stuff at the top. Okay, that's fine. Chunked semantic search. Okay, we got our class. We're initializing it. There's the model name. We've got the setup. So what does it want us to do? So what we're going to do here is we need a build chunk embeddings document method. So let's just get the structure out here. So that needs to build the chunked embeddings. Okay. We have, oh, this is a doozy of one. Okay. Load or create embeddings. Okay. So we got that function. Okay. So I rate these two and then that should be easy. Okay. So let's read through. Populate self from the input documents. Okay. So let's try and think through this. So build chunk embeddings. So we need documents just like before. And I'm just remembering back. We had documents, we had embeddings, and we had documents map and all that. So let's build off of what we had there before. We had a document map, which was a dictionary, and we can populate that for doc in documents. We can document map of the ID to the actual document. And this can be a little bit more compressed chunked semantic search. Okay, there we go. There's our document map. So we have our document map. We are going to need to have all of our chunks, and we're going to need to track for the chunks all of the metadata, because we're going to need to map a chunk back to the particular document ID, because there's going to be, each document could have one chunk or three chunks or five chunks. We don't know. They're going to be different lengths. They're going to have different number of chunks. We need to go through all of our documents. And what are we going to need to do? Good. We did that. Create an empty list of strings to hold all the chunks. We did that. Empty list of dictionaries to hold the metadata. We did that. For each document, if the description text is empty, skip it. Use your semantic chunking function to split the description into 4 sentence chunks with 1 overlap. Okay, description text is empty. So I'm going to say if it's that, then I'm just going to continue. We need to do our semantic chunking function on our description. Use your semantic chunking function to split into 4 sentence chunks with 1 overlap. Okay, 1 overlap 4. I'm just going to max chunk size. I'm going to call these out just so I don't get confused. Add each chunk to the all chunks list. All chunks, check. Okay, and then for each chunk, add a dictionary chunk metadata with the movie index, the chunk index, and the total chunks. So for chunk in chunks, we want to go chunk. We want to add to the metadata dot append, and we're going to add a dictionary. And the dictionary has the movie index, the chunk index, and total chunks. Okay, so the total chunks is the length of chunks. Right. This could probably be calculated up here, so it's not recalculated every time. I'm not going to worry about that just yet. The movie index is going to be the document and then the ID, I believe. Oh, no. We already have the index. And then the chunk index. Okay, so we need that. So let's go chunk index. Okay, so this is the movie index. I'm going to change this to be a MIDX for movie index. This can be chunk index. And this is going to check the length of chunks. I don't actually need this. So I actually can just do for chunk index in range the length of chunks. Okay, because I don't actually need the full chunk in here because I've already got them here. Okay, so that's done. Use the model encode the entire list of all chunks and save the results in there. Okay, so we go self.model.encode all chunks and save the into the self.chunk embeddings. Did I initialize that? Yes. Oh, that was part of the stuff that I was copied over. Save the chunk metadata and the self-chunk metadata. Great. Cool. Save it to this file and save the JSON to that file. Chunk embedding. Okay, cool. Import JSON. Cool. So we dump this in there. So we need with open cache chunk embeddings numpy file. And I'm going to go ahead and just add it up here while I'm at it. Self.chunk metadata, because we've done this a couple of times, so I know I'm going to need it. because I'm also going to need to do a load, not just a save. So I don't want to duplicate it. Chunk embeddings. Yeah, that's how I did it there. Okay, so chunk embeddings and chunk embeddings path. So this is embeddings and this can be metadata. Cool. Okay, so with open self dot chunk metadata as F, but I need this in a write. I'm not sure if this is right. Do I need to write it or do I write bytes? I'm thinking probably this. I don't really know, to be honest. We'll see. NumPy save for this one. And NumPy save for the file name. Okay, so this is self.embeddings path. And then I put in the self.chunk embeddings. Wait, chunk embeddings path. Okay. Okay, so we've got these. We're saving them. We're saving those. I think we're in good shape here. Return the chunk embeddings list. Okay, that's good. So this is the return self.chunk embeddings. Wait, return the chunk embeddings list. I don't know if it's a NumPy array or embeddings list. It's actually a list, but that's okay. Okay. Load or create chunk embeddings. Populate self documents and self document map. So we did that already. I'm probably going to need all this actually. I'm probably going to need all this actually is my guess. So let's just start there. If the cache chunk and files exist, then we're going to load them. Okay, so we go self embeddings.exists and self.chunk metadata path.exists. So this should be chunk. So if both of those are true, then we're going to load the embeddings. Self.chunk embeddings equals, I think it was mp.load. And that was going to be the embeddings path. And the self.chunk metadata would be, we're going to open our self.chunk metadata embeddings path in a read-only mode this time. Gosh, sorry about that. And then we're going to use json.loads on load metadata JSON and extract chunks into chunk metadata. Okay, return self.chunk embeddings. Return.chunk embeddings. Okay, so we covered that happy with us. Otherwise, return the result of rebuilding. So then we return self.build chunk embeddings with the documents. Okay, all right, cool. So let's embed the chunks. So the chunks don't really need anything because we're gonna load our movies because that's what's gonna go into CSS or front-end developers now. No, I'm just kidding. We'll do chunk semantic search, and then we're going to load or create chunk embeddings with our movies. Load and initialize this, load or build, print info about the embeddings in this format. Okay. Length of our embeddings. Okay. So we need to save our embeddings here. Yeah, I'm pretty sure there's like 0 chance there's no bugs. So we will work through them. Embed chunks. Okay. Let's do our embed chunks and we can run our embed chunks. So that should do that. I do, however, need a parser for this. I'm just going to keep putting them at the bottom so they're easy for me to find. This is going to be embed chunks. Create embeddings for semantic chunks. Okay, go make yourself a nice soy latte. Okay, that would be great, but I don't have the ingredients. Wish I did. I guess I could make y'all watch me brew a cup of coffee or something, but I won't do that. Okay, so this is going to take a little while. So let's see. Semantic search takes 1 positional argument, but 2 were given. Embed chunks, chunked semantic search, model name. Okay, so let's go take a look, see what's going on here. Embed chunks, this chunked semantic search is created. This passes in the model name. Oh, this doesn't take a model name, so I'm just going to get rid of it because I kind of defaulted that, kind of hard coded it. Yeah, having it as an argument to change out the model is probably a good idea, but that's okay. Okay. Expected string, bytes, or path like object, not list. So self.chunk metadata. Okay, so line 89 of this. There's a way to do this. How do I do that? I will figure that out later. Line 89. So this is the chunk metadata path. Okay, while I'm doing that, I'm going to look up how do I jump to line number in the VS Code thing. And then, okay, P42. Okay, there we go. Ah, that'll be nice. All right, next bug. A byte slide object is required, not a string. Okay, so this is in bytes. Okay, so let's take a look at this. So this is the json.dump. So I think I did not need the bytes. That makes sense because I'm giving it string stuff. Okay, the JSON object must be a string bytes. Okay, so JSON.loads. Okay, so JSON loads. All right, my nemesis here, opening files. Oh, wait, chunk metadata. Why is this a NumPy format? Oh, chunk metadata path. Okay. All right, let's read the stack trace here. So we have JSON.load. So let's get rid of these because these are NumPy. I actually think I screwed something else up. So I'm going to get rid of those caches. Let's go look at where we saved them. Chunk metadata path. So this is actually, the chunk metadata should be a JSON, not a NumPy file. Chunk embeddings, chunk metadata. Okay. And then when we build these, we're going to write it. So let's try and recreate them. Okay, cool. Chunk embeddings, we should not be able to read that. This, we should. Okay. This is looking good. Okay, so we generated 5,000 chunked embeddings. Is this right? No. I'm going to get rid of this. Okay. All right. So let's see what went wrong here. Generated length embeddings of chunked embeddings. So let's take a look at that print statement while this is running, because I know that's right. Embed chunks. Load or create chunk embeddings for movies. Okay, so this is the length of the chunk embeddings. So I guess I need to flatten this out. Let me take a look. So load the embeddings into self chunk embeddings. Let me go further up here. Add each chunk to the all chunks list. Okay, so that's where I went wrong here. So when I did the all chunks, I did this. So what I could do, what do I want to do? I believe I can do that. Let's try this again. Now let's go over here. Let's clear our cache for a second. Because I think what I have is I have a list of 5,000, but that inside those, each document has a separate, list of each of their chunks. And so I think what I needed to do is just flatten it out. Let's take a look. What do we have left in chunking and semantic chunking? So we've chunked semantic search. Okay. And then as some edge cases stuff and then some more advanced things. Okay. All right. We now have the right number of embeddings. Let's go ahead and test it. That's interesting. 72,909, but here I'm getting 5,000 chunked embeddings. Why is that the case? Okay, so I run it once and I get the right number. Second time I don't. Okay, so there's some sort of issue with loading them. So let's take a quick look here. So what happens? When it runs the first time, it does this build chunk embeddings. What does it happen? When it does the first time, we do load or create chunk embeddings. Okay. And so the first time it goes through here, it creates the documents, it creates the map. If the path exists, which it doesn't, it does this. Otherwise, it build chunk embeddings. So this works. If it does, if these do exist, it loads the embeddings. And so somehow here, it's not quite right. Print the length of chunk embeddings. So this should be, so if I say, so I'm going to say here, loading. Let's see here. Why is this giving me grief? That's why. Okay. All right. So this is loading. And when we dump it, we can say saving. So it's definitely, okay. So these should be the same. I'm going to reset the cache. Try this again. There's some small stupid detail I'm getting wrong. Okay. So let's embed the chunks and we'll wait. So we saved that many chunked embeddings, and we loaded a different number. So that does confirm the issue. Chunk embeddings path. Now that should work. Okay. Yep. Perfect. Okay. We can remove our print statements. We can run our test. That, I think, was the issue. Okay. All tests passed. All right. We are good to go. We've implemented chunked semantic search. Okay, chunked semantic search. So we have embeddings for our document chunks. We can create embeddings for a query. We did that previously. So now we can measure the cosine similarity between the query and each chunk. The mechanics are kind of similar to what we did for regular semantic search without the chunking. The difference is that you've got multiple chunks per document, and so you need to be careful about tracking the indexes. In some cases, like for movie searching, what we're doing, you want to return the movie. If I search for a movie, I don't want 2 paragraphs from a script that are related to my search term. I want to know what is the actual movie and what's the general thing, the movie about. And other things, if you're doing like a question answering thing and your data set is a whole bunch of textbooks, you might just want a chunk of the textbook. You don't want here's a textbook to read. Really depends on what you're working on. So we'll need to aggregate up to the actual movie. And so let's build it. We're going to have the search chunks method. We're going to generate an embedding of the query, populate an empty list to store chunk score dictionaries, and then go through each chunk embedding and give the cosine similarity and all that. So let's go ahead and start building this. I'm going to put this at the bottom here. The first thing is we need to generate an embedding for a query. Then we need our chunk scores. And we're going to need to go through for each chunk embedding. We need to go through each chunk embedding. So we have that in for chunk embedding in self.chunk embeddings. And if you remember, we created a metadata as well. So I'm going to enumerate through here so that I can get, you know what, I'm just going to actually do this, range length of the embeddings. And then what I'll do is I'll get my chunk embedding through self.chunk embeddings of the index, and I will get my metadata from self.chunk metadata. I have to index into chunks or IDX. So why did I have to index into chunks? If we look at our chunk metadata here, it's under chunks. So this should have the movie index, the chunk index, etc. So let's give this a shot. So then I know I need to be careful of the indexes. So I'm going to say movie index and chunk index is going to be my metadata movie index and then my metadata chunk index. And we can just go ahead and check movie index, chunk index. Okay, great. So I need the similarities, and I had my cosine similarity function from before between my query embedding and my chunk embedding. And so my chunk scores, we can append to that a dictionary. Let's see what they told us to store, but I think it's probably the movie index, the chunk index, and the score. Chunk index, the movie index, and the score. Great. So we go movie index, chunk index, score. So we can do the similarity here. We can do our chunk index here, and we can do our movie index here. Why did I do this? Like I could have put this inline here just because from experience, I know that when I'm tracking all these indexes, it's really, really easy to get confused. Yeah, I just thought it was worth it. So I got that. Cosine similarity, append a dictionary with these. You'll need to use self-chunk metadata to map back to this. Okay, create an empty dictionary that moves movie indices to their scores. Each chunk score, if the movie index is not, okay, so now we need to aggregate up. We can say movie scores. That's going to be a dictionary. And I'm actually going to make it a default dictionary. And the reason for this is I don't want to have to do like a check to initialize it. And so now I can go through each chunk embedding. And actually, I don't think I actually need two loops here. I don't even know I need the chunk scores, but that's fine. So movie scores, and we're going to say the movie index is going to be equal to the maximum of the prior movie index and the cosine similarity score. So this is going to say, hey, if this isn't there before, this movie scores will be 0. And it'll just take the largest one. I think that's what I'm supposed to do. Sort the movie scores by score in descending order. So we can take movie scores. So dot items is going to turn things into a tuple. For example, we can do 1, 2, 3, 4. That's a dictionary. And if I do dot items, I get a couple of tuples. So now I have something that I can sort. So I can say sorted movie scores. Movie scores, the key is the index and the value is the actual score. So I could say key equals lambda x, do an anonymous function. And the key is going to be the first value or the second value, I guess, index 1. And we want it, instead of ascending, we want it descending, just like we did in the others. Is that right? Return a new list. Okay, so we could say movie scores sorted. Sure. So we've got our movie scores sorted. Filter down to the top limit of movies and format the results using a dictionary like this. Okay. For movie score in movies, in movie scores sorted up to the limit. Let's just put create a result, and we're going to append to it this dictionary. How do we get this? So movie scores, what do we have here? We have the movie index and the scores. So we have the movie index, which means we can say, okay, so this is going to be the movie index and then the score. So that takes care of this. We've been rounding to 4. I'm going to keep it there. It looks like I should have created a variable. So it's not a magic number at some point, but it's okay. Metadata, self.chunk Yeah, I don't know what this is right now, so I'm gonna leave this empty for now. I don't think I need it. I don't see why I would, but so the document, I guess that's probably the description. We have our self.document map, which we can index in with our movie index. So that gives us the document. And so then we can check the document ID, we can get the title, and we can get the description, I think. I'm kind of making sure, so I'm just going to print out the keys just so I can see what they are. And I think that will do it. So we probably just return that now and limit the movie description to the first 100 characters. So yeah, that's what document is. Return the final list of results. Okay, so that seems good. So now I assume we're going to add it to our CLI. We need a new search chunked command, and it needs query and limit. So let's go ahead and build that. Query and limit. Well, let's just set a default there. And so then we need to do, what do we need to do? Chunked semantic search. We'll need to initialize that for sure. We will need to load or create our chunk embeddings. We will need to search chunks with the query and the limit. Okay, so we got this chunked semantic search instance. Yes, that creates the movies, so we can load the movies in. Load or create chunk embeddings. Get the results using the search chunks method. Get the results using the search chunk methods with the given query and limit arguments, and then print in the following format. So print this. So we get results, and the result has result title, result score, and result document. For whatever reason, it's called document instead of description, but that's okay. That is the content of the document. So then we can say, so let's call this results. For res in results, we can print this, and we need to enumerate so that we have this index to print. I think we probably want to print that so it doesn't start at 0. Okay, so I think this might give us what we need. So let's go ahead and add it to our CLI. And if you remember right, we need a query and a term. So it's going to be very similar to our previous search term probably, except, yeah, very similar, but we need a limit as well. So do we have a limit? Oh, no. This is our keyword search. This is not the right file at all. We need our semantic search CLI. So it's very similar to this one, but we want this search chunked here. I guess we don't need that, so we can toss it. So now we can add our search chunked here, and we can change this to search chunked. We can change this to search chunked parser. That's going to be the query and the limit. Default to 5, search chunked, and then call our search chunked with args.query and args.limit. What do you think the chances are I did all that without any bugs? I'm going to go for slim to none. Let's try running it, see what happens. Wait, really? ID, title, description. Oh, that was that print statement I was curious about. So let's find that. Okay, superhero action movie. What are the supposed responses? Kick-Ass, The Incredibles, and Logan. Okay, so that does not look optimistic. So let's go ahead and let's first try and rebuild our cache in case there's some issue there. We're changing a bunch of things. So let's just toss that. We'll go to our semantic search CLI. There should be some sort of build command here. Probably verify embeddings and semantic search. Okay, so let's go ahead and do those. I'll do verify embeddings. Let's try that again. That should fix that. Cache movie embeddings. Embed query. Oh, so let's do embed text. Okay, so semantic chunk. Okay, so chunk text semantic. So what are this? We need to do the embed chunks. Okay, so let's try and run the embed chunks. You know, actually, the search chunk should just work, right? So let's just try that. Search chunked. So this should, and can I actually give a loading bar here? That's what I really want. Search chunked. Load or create chunk embeddings. And where's the encode function? I need to go to search chunks. I need to go to the build chunk embeddings for the encode. And I want to do the show progress bar of true. I'm going to try this. That might help. Okay. Oh, that's a beauty. That is so much better. All right. Now I don't have to wonder if it's working or not. So while we're doing this, what was this again? So, okay. So we should see Kick-Ass, The Incredibles, and Logan. Boom. No file or dictionary. So, okay. So I'm confused here because I thought search chunked should load or create the chunk embeddings, but it says it can't find them. So I deleted the cache and that's not there. So why did this not work? So that's interesting. So load or create chunk embeddings. It would have gone through here it would say they don't exist. So it built the chunk embeddings. So when it builds the chunk embeddings, it'll go here. Then it should have saved to the chunk embeddings path. It did not. np save self chunk embeddings path. np.save. So I guess there's that issue. And I think this was this one on line 90, right? Line 90, yeah. Self.chunk embeddings path dot make dir exist okay is true. So let's just do this. Embeddings, let's do the metadata. Well, I shouldn't need them both. Dot make dir. What does that do here? Parents equals true, exists okay equals true. Will this cover it? Okay, let's give this another shot. Here, what I'm going to do is I'm just going to break out of this loop early to make it go very fast. And I'm actually going to so this is the semantic chunking. And you know what? Let me break out of this loop early. So that should make it run really fast and I can at least test that piece. So this is something that you'll need to get good at and be conscious of when you're doing AI stuff that can take a long time is like, how can you test the bug quickly? So this needs to be chunkenbeddings.parent. Will that work? Chunkenbeddings.numpy. So I don't need this. Okay, so we have this directory. So I think this will actually work now. I think the cache directory I created. Okay, so it is creating the cache now. So this directory needs to exist, and I think that's a problem, but I'm going to make sure that everything else is working before addressing that. So I'm going to get rid of this break. I'm going to go ahead and get rid of these chunks, these cached files, and then I'm going to rerun it and let it process. Make sure that I'm actually doing the right thing, and then I can make that more robust. Now we wait. This cache directory is actually not needed. This is not the right place, so let's remove that. So while we do this, let's peek ahead. Chunked edge cases. Okay, so edge cases are endless in chunking. Chunking is one of those things that you just need to continue to iterate and manually inspect a lot, like over and over and over again. You're going to find all kinds of weird stuff in documents. There's going to be like markdown tables or ASCII tables. There's going to be tables in PDFs or that were copied from Google Sheets. There's going to be paragraphs that are multiple pages. So if you're doing on paragraph chunking, it can be a problem. There might be page numbers like headers or footers appears in every single page. And so it keeps getting in there. That's kind of like garbage that you're indexing. Image and alt text can get mixed into like unrelated stuff as well. Yeah, PDFs are like column layouts, weird spacing issues, you're missing line breaks, special characters, code blocks. There's endless. Like you really need to like continue looking to really get it done. So yeah, this is a good example of a document that's more actually fairly realistic-ish where you might easily chunk and like be embedding this 2023 movie and reviews incorporated, which is probably not what you want to return based off of, or this page number, or you might index plot summary, like just the titles, but like really you'd want plot summary and this first column embedded together and the second column. But other times you might want rows chunked together. So it'd be very, very broken. We're just going to fix a few of the edge cases. Not going to fix them all, but we're going to make a few improvements in that next lesson. So that's going to be super cool. Okay, we got Kick-Ass. We're getting there. What do we have? We had Kick-Ass, Incredibles, Logan. I saw all three of those. I should check the other one. I'm going to go ahead and submit. I think we got the major bug fixed and we passed. That is perfect. All right, so we're on to the chunked edge cases. There are, as I mentioned, endless edge cases for column layouts, weird spacing with PDFs, massive paragraphs, headers and footers, images, tables, people copying and pasting ASCII art or from Google Sheets or from Excel or from, headers and footers. You might be embedding a copyright notice that's on every page or a page number, a 1 of 3 on every single page, which you don't want to do. For tables, maybe you want to embed row-wise because the row is all related to each other. But what do you do about like the headers? Just embedding plot summary and special effects doesn't seem helpful. You might want to embed the header, the column, the name of the column with each row or embed column wise. So there's all kinds of different options where, you might end up chunking very badly. Like movie review, TED page 1 of 3, TED is could be a chunk. Getting rid of a lot of that stuff requires manual review, manually review more of them, manually even more. There's so many different edge cases. You just have to like look at them and fix them for your data. So let's do a few. Improve our search command. Strip leading and trailing white space from input text. So we're going to run this semantic chunk command. Okay. And then it's going to run the semantic chunk. Okay, good. Strip leading and tailing. If there's nothing left to returning empty list. Okay, so here in our chunk embeddings, what are we going to do here? We're actually going to take strip leading and trailing white space before using the regex to split on sentences. So let's do this. So we go text is equal to text dot strip. If there's nothing left after stripping, return an empty list. If there's not a text, return the empty list. After splitting sentences, if there's only one sentence and it doesn't end with a punctuation, treat the whole text as one sentence. Okay. So if there's only one sentence, so we can say if the length of sentences is equal to 1, if there's only one sentence and it doesn't end with a punctuation mark, treat the whole text as one sentence. I'm not sure that makes sense. Does it make sense? Whole text is one sentence. Wouldn't it do that already? Okay, so sentences, if it's one, there's only one of them. Sentences 0 ends with a string or tuple of strings to try. So this is boom, this period or question mark. Was that the right 3? Treat the whole text as one sentence. Not sure what to do about that, so I'm going to leave that for now. Strip leading and trailing white space from each sentence before appending it to the chunks list. So let's go sentences equals sentences. We'll strip that for S in sentences. Strip the leading and trailing white space from each sentence before appending it to the chunk list. So we just could take care of that. Use only chunks that still have stuff. So that takes care of that. Test your improvements using semantic with edge cases like. So let's go ahead and see if let's just run a bunch of them with the command. Okay, so that worked. Okay, that worked. It did not contain that. Contained one leading and trailing spaces. Okay, that seemed to work. Expected standard out to contain all of 1. A hero rises, the world needs saving. That seemed to work. Okay, well, let's see. I'm a little worried because there was that one that I didn't quite understand. Yeah, so, okay. So I'm going to go ahead and say, so I think this might have been an edge case that I just handled by the way I did it. I didn't handle it any different. Yeah, I think I handled that edge case already. All right, lesson 7 is on Colbert. It is based on the BERT models, which is a transformer model. It's pronounced Colbert. I don't know if it's named after the comedian or if people just liked how the French pronunciation is, but that is how it's pronounced. This semantic chunking with overlap works really well in most situations. Researchers created a more effective one. In Colbert, each word gets its own embedding. So we're saying, hey, here's 4 sentences, create an embedding of 384. I think we're using numbers to represent that chunk. In Colbert, every single one of those gets its own embedding. And so you can imagine how much data that is. In regular chunking, all of this gets one embedding. In Colbert, you get Ted gets an embedding, comedy gets an embedding, John gets an embedding, responsibilities. They all get an embedding and they're all related based on what's around it. So you don't embed comedy as a generic embedding. It's comedy in the context of everything around it. And this is why it's largely called multi-vector. There's 2 things. There's late interaction. There's multi-vector. It's kind of the terms that are thrown around. And the multi-vector is because a chunk here has 1 vector, and now you have a lot more because every single one has them. How do you even make this work if you have that much more data? Well, part of it is more computationally expensive. But the other part is you use something called quantization. And what quantization is you take a number and you find efficient ways to represent it. One form of quantization is to say, we have a 32-bit number, floating point 32. You can say, let's use floating point 16. It's less accurate, but we use less memory. So that's one way. This does a pretty extreme quantization. It's called product quantization. And the idea is that if we're embedding a data set of movies like we are, there's going to be a lot of movies that have, and a lot of tokens in those movies that have very, very similar embeddings. So rather than store them all, we're going to kind of refactor to save the common numbers. And how do we do that? Well, we do clustering. So what we see here is basically you end up having groups of clusters. And so you say, hey, you know what? Maybe this is a bunch of comedy movies are in here, maybe a bunch of things related to very serious topics. These are words related to very adventurous things. These are all very similar. And so rather than storing all of the values for all of them, you say, okay, all these are super similar. Let's store very precisely what the center is. And now all we need to store for each number is how far from the center it is. And in reality, it's so close, you often only store whether it's bigger or smaller than the average. And so by doing this, you can really compress it down. There's a lot of details I'm skimming over there, but that's the idea, is you have this way of having numbers and making them super, super tiny by a technique called quantization so that you can have lots of embeddings. What's the difference between regular and Colbert? It does not use less storage. It is definitely not easier to implement. It is not faster. It creates one embedding per word, while regular chunking creates one embedding per chunk. That's it. When would you choose advanced chunking? Okay, so late chunking is another approach which creates an embedding for an entire document, so it has like a really big one, and then uses that to create chunks. And so it's a middle ground between the Colbert approach and what we've been doing. So what we do is we break a document into chunks, and then we create separate embeddings. What late chunking does is it says, let's create a really big embedding that's super detailed, and then we'll chunk. And so we're late chunking. We're chunking after the embedding process. And this is a very relatively new thing. I'm going to self-plug myself here. And so if you look at an article here on late chunking, and this walks through all the details, start to finish, of how late chunking works and what some of the problems are that it solves. And really what it solves is, here you see this, the problem is if you embed this chunk now, this its population, nowhere in here to say what its is referring to. You need to see, oh, it's Berlin. The city references Berlin, it references Berlin. This is okay. But in here, its and the city, it needs to be aware of what happened all the way up here, because this is where it said what particular city. Again, Brandenburg Gate stands as this most iconic symbol. It's what, and so you need to kind of like trace back. And late chunking is a way of embedding the entire document with a very, very big context window, and then chunking after the fact to try and capture that. It's not as accurate as Colbert. It's a little bit of a middle ground. So when should you use advanced chunking methods like Colbert or late chunking? You should not always use the most advanced methods. Yeah, when you already tried regular chunking, and higher search accuracy is worth increased cost, complexity, etc. I might also add to this, you can use something like Mixspread. They have a search API, and they're very good at this multi-vector stuff. So if you think, hey, maybe this complicated chunking and this advanced stuff is going to be helpful for my use case, try putting some of it into an API that does it and see if you see a big improvement. If you do, then you might want to invest in building it yourself or using more of it or lots of things. But see if you can kind of vet the idea out before you invest a ton. Okay, we're on to chapter 6, lesson 1. So this is talking about hybrid search. We built keyword search and we built semantic search, and we talked a little bit of that, which is better depends. In many cases, you want to search for some sort of exact match. It may be because you know specific words, or maybe you know a quote from the movie, in which case a keyword search is going to do really well. Sometimes you just have themes, like I want family friendly, or that action movie that happened around Christmas time where the married couple gets back together or something, or survival movie or family friendly. So there's lots of ones that work really well for keyword. There's lots that work really well for semantic. However, they each have some blind spots. In keyword search, film versus movie, uplifting versus feel good, a river bank versus a financial bank, these all have problems and blind spots that it doesn't handle very well. And semantic search has others. So if you have new slang, if you have like a specific terminology, it's going to have a problem. You might guess that hybrid search is a solution that lets you take a hybrid of the two to do it. So which would be best when a user queries for an exact title like The Room? Semantic search, because it understands the meaning of the title. No, a good search engine will always return The Room. Okay, that might be true, but somehow I don't think that's it's the best movie ever produced. I don't think that's what they're looking for. Keyword search, because it can find the exact string matches efficiently. That's the one. Perfect. Hybrid search. So keywords better in some, semantics better in the other. So let's use both. Let's do a hybrid. And so we know that different search methods perform different ways. And so we might want to think about which gives better results and why, and run a few queries. So we're going to start by getting some code, getting the boilerplate stubs out, just like we did in the previous ones, and then we'll run a few queries and look at the differences. This is partially a learning exercise here, but you should do this when you're actually implementing it on your data set. Think of some actual queries, because depending on your data set, you might want mostly keyword search with a little bit of influence from semantic. You might want mostly semantic with a little bit of influence from keyword search, or 50-50. It really depends on your data set. And so looking at results is important. So let's do the stubbing out, and then we'll take a look at that. Hybrid search CLI.py. So let's go ahead and create that. Hybrid search CLI.py. Perfect. And then the hybrid search logic, and it's going to import our earlier keyword and semantic. So we'll see. So let's create this hybrid search.py. So we've done that. Let's see what it's doing here. It's importing our inverted index. It's importing our chunked semantic search. This is the inverted index is from our keyword search, if you remember. Here it's using the os.path. That's perfectly fine. I tend to use the pathlib, but there's nothing wrong with this approach. So I'm gonna leave it, and it will build it if there's no index. We have a BM25 search, and it looks like we're gonna implement a weighted and an RF search, which we'll talk about, what that is later. Cool. And we've got our chunked semantic search, so we are in good shape. This has got everything that we need. Yeah, feel free to refactor at this point. It's a good exercise. I think my code's doing okay. I think there's been a few places where I might want to remove some duplication, but I think overall I'm doing okay. So let's go ahead and try running some of these. All right, Gods Among Men. Okay, so we get God of War, Eternal Darkness, cool. Gods Among Mortal. Okay, let's try it with keyword search. So here's where I need to rebuild, because I deleted my cache. So let's go and take a look, and let's figure out what we need to do. And actually, we just put this in the commands we need to do, I believe. Let's go look at our keyword search CLI, figure out what we need to do. So I think we need to do our build. So let's do our uv run keyword search CLI, and we'll do our build command. Let's see what else we got. We got BM25 search, bunch of these. Yeah, I think the build is what we need. Very nice. Let's try this again. So now we get Mortal Kombat, Hercules. So is this a better result than we got before? Like Mortal Kombat is definitely the case. Here we have God of War, Eternal Darkness. So I think actually they show different results, and they're both pretty good. I like God of War showing up, but Hercules and Mortal Kombat were really great. So keyword search did pretty good there. Let's see, semantic search chunked here. And let's just go ahead and run the BM25 search as well. So here's an interesting thing. I don't see the Revenant in here. And what I know about the Revenant is the Revenant definitely has bears in it, and it has Leonardo DiCaprio. So here, the keyword search definitely wins. The number one thing was a bear movie with Leonardo DiCaprio in it, and the semantic search, it wasn't even in the top 5. Yeah, keyword search definitely won there. So, all right, so that's pretty cool. We did that. We've got the boilerplate. We've thought about this a little bit. Let's go ahead and try running this, make sure that we've got all of our stuff done properly. That seems to work okay. So let's go ahead and implement this. All right, perfect. We can move on to the next lesson where we can actually start implementing the details of how to combine these. All right, so hybrid search, score normalization. This is super important, and this is something that is a huge source of bugs. And the thing is that if you don't normalize this, in many cases, you won't actually get an error. You'll just get kind of bad results. And then you'll be trying to tweak some hyperparameters to fix the balance, and that will make things improve slightly, but it'll still be wrong, and so you'll just always get slightly wrong results. Normalization is a very important topic. It might be one of the biggest sources of bugs that I've seen. So what's the problem? Well, the problem is when we saw here, we see, okay, the Revenant score of 9.46, that's the number one. Legends of the Fall 0.4735. So the top score of each, if we just combine them without doing anything, this is 9.46. So this is like 20 times or something more important if you were just going to go with raw score. So what the normalization is going to do is it's going to say, it's not that this is 20 times more important. These are just two completely different algorithms that are creating different scales. And so we want to have them on the same scale. So we can say, maybe this is the best one, so it should get a score of 1. And this is the best one, so it should also get a score of 1. And so now we say, okay, the best semantic result and the best keyword result both would get roughly the same value, and vice versa. So they're on the same scale, so we can combine them and get kind of intuitive results. So let's do it. So for each score, we want to calculate its normalized value. So we take the score minus the minimum score divided by the max over the minimum. And so what we end up doing is, you'll see with this small array, we end up with the biggest value being 1, the smallest value being 0, and these other falling in between. And it doesn't matter if you've got numbers from 0 to a billion or 0 to 10 or 0 to 1, they'll all be normalized, and so then they'll all be on the similar scale. And so you end up with, nice things. And so when you have two of these, I can now compare them. We'll add a normalized CLI command to our hybrid search script. It accepts a list of scores and prints. If no scores are given, then we want to do nothing. If the minimum and the maximum scores are the same, we'll print a list of 1.0 values. Otherwise, we're going to print the new normalized scores using the min-max normalization above. And that's this min-max normalization. Okay, so let's give this a shot. I'm going to go over to our hybrid searching, and down here, I'm going to create this as a function. So we're going to do normalized scores. We said it needs to accept a list of scores. And so this is what we want. We want to return this normalization. And so we need to take the minimum score and the maximum score. We'll just stub these out for now. And then we need to do this for each score. Okay, so then we need to say it's the max minus the min. So we can call this the score, the range, which is going to be this max minus min. Very good. So once we have that, then we just want to return a new list where we're going to take score minus our min score divided by our score range for score and scores. So that's good. If we don't have, let's do some of the error handling now. If we don't have scores, then we want to just return the empty list. So if that's not there, we can take the minimum score with the minimum function and the maximum score with the max function. So we're good in that case. If the minimum score is equal to the maximum score, this means that they're all completely identical, and so we can just return all ones. Because it doesn't matter, there's no differentiation if they're all exactly the same. I think this will work, but I think we need to add it to our CLI. So let's take a look here. Okay, then print the following format to only print 4 decimal places. Okay, cool. So let's go ahead and add this normalize here. Okay, so we have our normalize command, norm parser dot add parser, and we're going to add our values, scores, called it. This is a type of, what can we do, list or something? Very nice. Is that a type? We will find out. Type is list. Let's put some help task. A list of scores to normalize. We can add this normalize, and we want to do our normalized scores, and we can call our normalized scores function we just created with our scores. That means we need to import our normalized scores function. And then there was a print here. You can use the nargs equals plus keyword argument for add argument to gather the command line arguments into a list. Okay, so look at that. So we want to print the following format. Okay, cool. So we want to say for normal score in norm scores, let's print this. That should do it, I think. Let's take a look at what this nargs is. Okay, so we can add, let's see, an argument parser, and it was saying there was a plus in here. Add argument bar nargs plus. Nargs equals plus. Okay, so that lets us take an initor, have a bunch, an initor for the accumulator. Okay, so then we can pass multiple of them to it. So that's cool. Parsing args of A and B. Okay. So that seems like exactly what we want. So let's change this. So we want a type float because we are going to pass decimals, not necessarily whole numbers. And we can use this nargs plus. Okay, let's give that a shot here. See what happens. And we'll work through the bugs if we have them. Cannot have multiple subparser arguments. Hybrid search CLI, add subparsers. Cannot have multiple subparser arguments. Line 8 in main. Oh, gotcha. So this should be a subparsers. And so then this is add subparsers. And this is add, what is that again? Add argument. Okay, let's try this again. Okay, let's see here. Add, oh, no attribute add subparsers, you meant add parser. Yeah, I think I did. Add parsers. I do think that's what I meant. So let's try it again. Add parser, missing one required positional argument of name. I think that's what I wanted to do. Okay, great. So we've got this. We got 18, 18, 1, 5, 18, 18. What was the expected results? Okay, that looks pretty good. Let's go ahead and try and submit. See if we got everything. All right, we have successfully normalized. So this is great progress. On to lesson 4, weighted combination. We got our normalized scores. And the whole idea that we did that, if you remember, was we created normalized scores so that we can combine them, that they're on the same scale. Now that they're on the same scale, we can and we should combine them. And the way we're going to do that is we're going to use this hybrid score type function. And you can see it's a weighted average. We take the BM25 score plus the semantic score. And the reason we're taking a weighted average is because of this alpha. So if alpha is 0.5 here, we take 50% of the BM25 score plus 50% of the semantic score, because 1 minus 0.5. If alpha was 0.3, we would take 30% BM25, 70% semantic score. And all this works because we've normalized them, so they're on the same scale. Which one you want to work well? It depends. Like, you want to do it for the queries based on your application and try a few things. If you're trying to optimize a retrieval for lawyers or for medical professionals, that's going to be very different than a movie website. And so you need to, go through it. So let's start the assignment. So we're going to build a hybrid search with a configurable alpha. We want a weighted search command to our hybrid search script. So let's start with that. So we have query alpha and limit. Let's just get that boilerplate set up so that we can test it. So we have a weighted search. We're probably going to do some sort of weighted search. Let's just do a pass right now. Let's just do the arguments. I don't know exactly what it's going to be. We're going to need a parser here. We'll do WS for weighted search. And this is going to be weighted search. No, we're going to need a query. I think that query is going to be a type string. And we said we needed a limit and an alpha. Okay. Percent of weight for BM25 and the limit number of results to return. And this query is the user query to find relevant docs for. Let's fix that real quick. Okay, and the weighted search is a hybrid search with weighted average, a combination. Good. All right, so we have this. Let's build out the core hybrid search functionality because we added that to the CLI. All right, so what we need to do is we have this weighted search that's not implemented. So we're going to do that. Check, 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 check. All right, very good. So weighted search method. We're going to call the BM25 and the chunk semantic search method. So let's do that. Self.bm25 search. And that takes in a query and a limit. But we're going to grab the top limit times 5,000 here. So we can say BM25 results, just spell it out. And then we can say semantic results, self.semantic search. What is this here? Self.semantic search. And we need a search command, search chunks. And that also takes in a query and a limit. There we go. So why are we doing this limit times 500? So if we have 10,000 documents, I don't think we have, I think we have 5,000. Let's just use real numbers. So we could have 5,000 BM25 scores and then 5,000 semantic scores to get down to 5 hybrid scores, because that's our limit. Now, in reality, the top 5 are probably going to be something like number 1 BM25, and maybe it ranks 6th for semantic. You might have a number 3 BM25 plus a number, a 10th place semantic. Maybe you have a number, the second BM25 has a 7th place semantic search, something like this, or an 11th place semantic. Whatever the case may be, what you're probably not going to have is a top results that's something like number 1 BM25 plus 5,000th place for semantic search. So rather than scoring and combining every single one, you can save some combination by saying, look, I'm only going to grab the first 2,500 here, and I'm only going to grab the first 2,500. It's 5 times 500. And this is the case. Now, where could this go wrong? If you do get these cases where you have some of the top few results that you're returning are super strong on one, but are like way far down the list, like this one BM25 and 2,600 most relevant semantic. Like if this was generally one of your top few, this would be a miss. That's pretty rare. It's probably not going to happen. You can always check for that edge case, but you can. By doing this, we're cutting like half of the computation, cutting the computation in half. And so, typically it's worth it. Weighted search, call BM25, call this. That's 500 times the limit. Combine the results with both. So this results combination is going to be big. So we can just say combined results equals combine results. And we'll pass in the BM25 and the semantic results. And let's, return that. So we'll do this here. So we want a third score hybrid for each document. Okay, so let's go ahead and take care of this. What are all the things we need? We know we need to be able to calculate the hybrid score, and we got that as a weighted average. So we can take a BM25 score, and we can take a semantic score, and we need the alpha, which we're going to default to 0.5. And so we can say, take our formula, which is alpha times BM25 score plus 1 minus alpha times semantic score, and that'll give us our weighted average. Now, if we wanted to be safe, we could double check that alpha is a number between 0 and 1, but we will leave it for like this for now. So we have our hybrid score. The next thing we need is we need to combine our, what would you call this? Combine our results. Let's call it search results, just so we're a little clearer. So we can combine our search results. So to do this, we need to get the hybrid score. We get the normalized score. Okay, so we need BM25 norm. We need a semantic norm. So how do we get those? We need to take these results. What are in these results? Okay, so this is doc ID, title, and score. And we did this right, then this should be a similar format. Search chunks. This is ID instead of doc title. Okay, so we have ID, title, and score, document and score, but this is ID instead of document. So that's a little inconsistency. That might be something we can refactor later. All right, so that's something we need to handle. So let's create a normalized search results function, which can take in some results, and it will return normalized results. Both of them had a score. We have the score attribute. So that's what we need to normalize, because we want to use this for both semantic and BM25. So we can do, we get the score. We can normalize our scores with the function we wrote for R and our results. Okay, so this gives us that. What does this take in? Normalize scores. No, this, because we need the min and the max. So this takes the min and the max over all the scores. So if I break it up like this, that doesn't work. So that's scores. So let's do norm scores. Okay, and so then we need to do another loop for our result and results. We can say our score. So this results is a list. So we take let's put it in normalized score. So we might want that. We want to take the result, get a normalized score, and this should be from the norm scores, but not the whole thing. So we need some sort of index. Okay, so now this should go through and add that. I think this will work. So we'll go through all the results. Let's see. Okay, we get the scores. We normalize all the scores. We then go through all the results, and for each item and result, we're going to add a normalized score with our normalized scores based on that index. So then we can turn the results back. Okay, so we got this. So we need to combine BM25 results and semantic results. So now we can use our function to get that. Okay, so now we have normalized results. So how do we combine them now? We have the normalized scores. We know we need to use the hybrid scoring, create a dictionary mapping of document IDs to the document themselves, and return the results. Return the results here. Okay, so we need to combine these two somehow. So let's iterate. So we can go through here, this BM25 norm. So we can say for our norm and our BM25 norm. So we can go through each of these, and each of these has a key. The doc ID is going to be, so this is for the BM25, was it doc ID or is it just regular ID? We're going to need to do this twice. So I'm going to create this as a function. We're going to do this no, let's just do the loop. I think that's going to get confusing. Okay, so for BM25 norm, we're going to say document ID indexes on document ID. Okay, we go That's the document ID. So we are going to create a dictionary mapping. Let's do our combined norm. So for each of these, I'm going to say combined norm of doc ID is equal to, and we need a dictionary mapping at a third score to each document. Calculate this using the hybrid score function. So we can do norm, which should be a dictionary, I believe. And we can then say, let's add, in addition to this, let's add a hybrid score, which is going to be equal to the hybrid score. It's not quite what we want. No. Okay. This is going to be equal to the doc ID. Let's just be explicit about this. We need the BM25 score, which is going to be and we call that normalized score, right? So this is the BM25 score. We can say the semantic score right now is nothing, so we don't have it. So this is the core bits we need to create a hybrid score once we have it. We'll just call it 0 for now instead of none. That'll make the math a little bit easier later. So create a dictionary IDs, add a third score, the hybrid score to each document, calculate this using hybrid score function above. We can't do that quite yet. Return the results sorted by the hybrid score in descending order. Okay, so we have this. We have doc ID. I believe we have a title and a description. So let's just go ahead and pass that through. We have norm title, and then description is norm description. I don't think we really need to pass this through. We could just look it back up, but I think it's nice just to not have to do that lookup later, since we're going to need it shortly. Okay, so now we need to go through the semantic norms, and we can take the doc ID, but we remember that the doc ID was actually just the ID here. And we can say in our combined norm dash doc ID, so we're going to do this, and we can say the semantic score, we're going to override that with our normalized score. Okay, so the problem here, so what if the BM25 didn't exist? So then we could do if the doc ID is not in our combined norm, then we'd want to say combined norm doc ID is going to be equal to basically all this stuff, except the BM25 score is 0 because we don't have that, title and description. So that seems to work well. So I don't love this duplication here. I'm going to go ahead. Let's see here. Yeah. So we've got this combined scores. So we have this combined norm doc ID. So now we have, for each doc ID, we have this dictionary that's got semantic and normalized score. And so I guess we need to go through for key values in our combined norm items. So we can go through all of those. We can say, let's take the combined norm key, whatever key we're on, and let's add a hybrid score, which is equal to our hybrid score function and our value of a BM25 score and our value of semantic score. Cool. So I've got that. Add a third score, hybrid score for each document using the hybrid score function. Document IDs to the documents themselves and their keywords, descending order. Okay, so we've done the descending order quite a few times. So we need to say, okay, so we take our combined norms dot items again, and we can say sorted, and we want the key to be, what do we want the key to be? We can just do values because we actually have the document ID in here. So we can say the key equals lambda x where of x of 0, and we could say reversed equals true because we want it descending, not ascending. And then we can return those results. So I think that seems pretty decent. So let's hook this up. We have our combined search results. We called it in combined search results. Yep, we called that there. This is used. Okay, so I think we're probably pretty good. Let's go ahead and hook this up into our CLI. I think we already did that actually. Okay. Oh, we kind of did. So let's implement our weighted. Let's make a command for this like we've done on all the others, where we're going to say weighted search, and we're going to take a query and a limit, query an alpha, and we're going to say we need to initialize our hybrid search, and then we need to do our weighted search, which takes in query an alpha and a limit, where it'll default alpha to 0.5 and the limit to 5. Okay, good. So now we should be able to import that. We should be able to call it. But what do we actually need to print out here? We actually need to print this out. So let's do that. Okay, so what do we got here? So we need to say results, and we need to go through all of our results. So for result in results limit, we need the index. Okay, so we got the index. And so now we need to print the index plus 1, because it starts at 0, space, and then our result title. we print the hybrid score. And so this should be the results / hybrid score. And we need BM25 result. Okay, I'm feeling lazy here. Let's save myself like 10 characters. Result BM25 score, and then semantic sim score. And then it looks like we print the result with the description. And let's just limit that to like 100. Let's take a look, see how that looks first, and fix all the bugs that we ran into along the way. So let's run this one first. We should see Paddington, Country Bears, Legends of the Fall. Badly formed help string. See if I can see where that is. I don't know if that's the issue. Okay, weighted search requiring missing one query. Okay. So we need to do args.query, args.alpha, and then args.limit. And we also need to set the default here to be 0.5. And I think we need to set the default here to be equal to 5. So let's just set all those defaults there. Perfect. Hybrid search init missing one positional argument. Documents. Okay. Hybrid search. Right. It says hybrid search here. Makes sense. So we need documents passed in. So let's, from lib.searchutils, let's import our movies. Cool. Let's work our way through the next bug. Slice indices must be integers or none or have an index method. Okay, so BM25 search, query and limit. Slice must be integers. That's interesting. So why would that not be? Okay, so self BM alpha limit, args.limit. Oh, gotcha. This should be an integer. Alpha needs to be a float. I gotcha. Let's see here. What do we got now? Normalize search results. Weighted search. Combine the search results. We normalize the results. We take the min of the scores. Dict and dict. Okay, so let's take a look and see what is going on there. So the min of here. So these normalized scores, wherever this score is being passed, it's not being passed a list. It's being passed a dictionary. R score, R in results. Oh, this should be normalized search results, not scores. All right, let's go again. Key error description. This is in line 62. Let's trace this down here. Norm, the description. So this is coming from our normalized search results. Normalized search results is bringing in some results. So what's getting passed to combined search results? The BM25 results are being passed. Okay, so let's keep tracing this back and see why description isn't there, because description is not here. Okay, can I add it? So let's try and add it. So we have the self.docmap. We already got it here. Description. So we have this problem with the keyword search. I bet we're going to have it with the semantic search next. Okay, we're on to the next. Sorted. So we say combine norm.values key lambda x x0. Okay, what is this? So let's see here. Let's see what a dictionary does with dot values. 1. Not subscriptable. Okay. Sure, I can do that. Okay. Let's see if casting it to a list solves our problem. Key error. So let me think about this. So what could be causing this? So what is combined norm values? I guess that's what we need to determine. Because what we looked here, we did dot values. We were able to get it. Combined norm. Oh, because if I look, combined norm, we index in, we're getting the keys, but then the values are actually these things. Yeah. So we actually want it to be sorted based on the hybrid score. So the key is not a tuple. It's actually indexed in. Okay. Round, I don't know, 9. We got Paddington, Legends of the Fall, Country Bears. Was that what we were expecting? Paddington. Oh, yes, it was. Let's go ahead and see if we pass. All right. All tests passed. That's great. All right, so we're going to be moving on to the next. All right, lesson 5, reciprocal rank fusion. Trying to combine the results of different search algorithms can get pretty messy pretty quickly. Keyword search might return results like document A equals 15, document B equals 8, document C equals 6, and then semantic search returns document A equals 0.8, document B equals 0.3, and document C equals 0.2. The scores are in completely different ranges and distributions, so how do we combine them? Reciprocal rank fusion is a way of combining results that kicks the idea of scores to the curb and just uses the ordered ranking of results in each input set. That's often all we care about anyway. Rather than comparing document A equals 15 versus document B equals 8, we just say document A is first and document B is second. Then, with the rankings in mind, we use the RRF formula, 1 over K plus rank. The rank is the position of the document in the results, and the K parameter is chosen to fine-tune the performance of the search. It controls how weight is distributed across ranks. A low K value like 1 gives higher scores to top documents. First place gets 0.5, second place gets 0.33, third place gets 0.25, and fourth place gets 0.2. A high K value like 100 flattens out the scores significantly. First place gets 0.0099, second place gets 0.0098, third place gets 0.0097, fourth place gets 0.0096. For most use cases, 60 tends to be a good default K value. But the point is, reciprocal rank fusion is a great way to get normalized scores and combined rankings across multiple result sets, even if they have completely different score distributions. So this is an alternative to the normalization where we put everything on the same scale. We're still putting everything on the same scale, but instead of assigning numbers between 0 and 1 to normalize with min-max normalization, we're actually just going to give them ranks, first, second, third. We're just going to say first is best, second is there. And so it doesn't really matter whether the difference between document A and document B for first and second. It doesn't matter if they're 0.1 apart or 0.9 apart. We just care about the ordinal ranking. And this often works better because we don't really have to worry about kind of skewed distributions and unusual stuff that happens. Instead of putting them in here, we use this reciprocal rank fusion and put in the rank. There is a K parameter, as you'll see here. There is a K parameter, and the larger it is, you can see the larger the denominator, the lower the denominator. So what does that do? Lower K values give more weight to the high, and higher K values give more rank to the gradual. So I think in this video here, I think I talked about this. And so you'll see, instead of combining them with normalization, we just give ranks. And you'll see that the scores might be close, they might not. And we end up with this kind of ranks for each document. There's the K plus rank. And you'll see this is exactly how it works. First place gets 0.5, 0.33, third place gets 0.25, etc. Really solves a lot of problems with the normalization of these numbers. It's a really good go-to. So we're going to add the reciprocal rank fusion search. It's going to take a query, a K, and a limit. So K is the parameter instead of alpha. And we're going to implement this search method. So we're still going to need to do almost all the same things, but use the reciprocal rank fusion instead of that weighted search to combine. So let's go ahead and start implementing. We can do this weighted search. We need all the same stuff pretty much. So query limits, combine search results. Oh, this weighted search, interesting. This combine search results. Hang on, let's look at this last lesson here. Where did we call our hybrid score? Okay, so here's what we need to do. I'm just gonna fix this other one here. Hybrid score, and we're gonna pass in our alpha. This is gonna take our alpha. This hybrid score has an alpha already, and that means this is going to also take our alpha. It's going to pass it all the way down. Okay, so that just fixed a little bug. So here we're going to do the same thing, but we are going to pass through this to do reciprocal rank fusion to combine the results and return this. So let's implement our reciprocal rank fusion, combine results. And again, it's going to work in a very similar way with a slightly different parameter. So we still need to get our search results here. We want them, we don't actually really need to normalize them. So we get scores, normalized scores. The reason is because the ranking isn't changed. So let's see. So let's just go ahead. We got these BM25 semantic results. Okay, so we don't need to normalize them. But what we do need to do is we need a reciprocal rank fusion scores. And I'm just going to call it scores inside this dictionary for simplicity. And all this combination stuff here, where we went through them all, we pretty much need to do the same thing. And so we can say for result in BM25 results, we can get a rank from this because we can enumerate through. So if we do this, we can start of 1. So we can start at 1. We need the doc ID. And if you remember, let's see here, we get the doc ID from the result. And we're going to follow the same pattern as before, where we scores and we want to put in the doc ID, and we want that equal to some sort of dictionary. And so the document ID, both these scores, the title and the description seems to make sense to me. Doc ID, semantic source, these all need to be the result. And then, so instead of BM25 score, we need BM25. We need the ranks of these. We have the rank for BM25 because that's what we're going through. Assuming this is in order. I think these are in order. Let's double check. Yeah, okay, so we do sort them. So we're in good shape there. Okay, so we have the rank. We do not have the semantic rank yet. We also need to calculate, let's create our reciprocal rank fusion score so we can do that. I think it's like rank K, and then we're going to return 1 over the rank plus K. Let me just double check I got all that right. 1 over K plus rank. Perfect. And then we sum the reciprocal rank fusion scores for each document. So we can do the BM25 rank, and we can do the BM25 score, which would be, what would it be? It would be the reciprocal rank fusion score with the rank passed in and K. And K comes from this argument. And so then the semantic score, we don't have yet. So we're going to need to fill that in. Okay, so I think we followed a similar pattern. We got this, we went through, we added all this, added a dictionary. So that's great. So we can probably follow the same pattern here where we do the same thing. We're going to append some value to it. In this case, probably 2 values, both the rank and the score, and we'll create it if it doesn't exist. Okay, so let's do that. For rank result, in semantic results, we need the enumerate. Start equals 1, enumerate. We're going to take the doc ID, which is the result ID, I believe, because I think for semantic results, so we just stored it as ID. Might be a source of confusion at some point. Okay, so if doc ID is not in the combined thing, is not in scores, then we want to say scores doc ID, and we're going to initialize some default one, which in this case we'll just do just like so. We'll say doc ID, BM25 rank and score can be none for now. And we can then say the scores are for the doc ID. We can then add in the semantic rank, which is going to be equal to the rank here from our loop. And we can do the semantic score, which is going to be equal to our RF score with our rank and our K. So that seems good. I think we followed the same pattern. Perfect. And then we're going to need to combine them. So with this reciprocal rank fusion, we're going to just sum them up. To create a hybrid raken, we can sum the RF scores for each document across both result sets. So let's read through these. So we haven't done this, but we said implement the missing RF search method, call this 500 times, give the 500 times limit, a dictionary mapping and their semantic ranks. For each document, calculate the RF score using RF function and add that score to each document as well. If a document shows up in both searches, sum its RF scores, return the results sorted. Okay, so what we can do here, let's create a small function. So final rank. And we can see, BM25, result 1 and result 2, because it doesn't really matter because we're adding. And so we can say if result 1 and result 2, if those are both something, then we can return the reciprocal rank fusion score of R1 plus the reciprocal rank fusion score of R2. So let's do RRF final score, better name. All right. So then we can go through our 4 scores and scores. Keys we can go through for each document ID. We can just do a final score here because we don't have a real one. We'll do the final score, RRF score. So we can define the RF score using this final score, and we can pass in our, that's not good. So doc ID. So we can say scores doc ID. Okay, so we look in the scores dictionary, we grab the doc ID, we grab the reciprocal rank fusion score, and we're going to set that to be scores doc ID BM25 score. Is that the right thing? And semantic score is the other. Actually, we can just do rank and then semantic rank. Because what this final one takes is it actually takes in the results and it will calculate the reciprocal rank fusion here. There's a little bit of duplication here. So we don't actually need to calculate here. So if those both exist, we're calculating a reciprocal rank fusion score a few extra times because we calculate it for the BM25, then we calculate it, here for the semantic, and then inside this function, we're calculating it again for each. Let's make sure we have the right answer before we, look to optimize. Okay, so we've gone through, we've updated those. So now we probably need to sort them, I guess. We can do this in descending order. And I would say, if one of these isn't there, I'm just going to return 0 if it's not in one or the other. So let's do that. And then, so we need to sort these. Combine the search results. So we can do what we did down here below. So we got the hybrid scores, sort them. Yeah, I really didn't need to do this. Oh, that could have been a better way to do this. Because if I am indexing to get the values, so I could do the kv.items thing again. But that's okay. This works. Okay, so this is scores. This is RRF score. And so this is all the results. I think we're good. All right, let's add this to the CLI. This is pretty exciting here. What did we add here? We have this weighted search. So let's give whatever print statements we need for the testing. So RRF score, rank. So it's very similar to this one. So I'm just going to copy this as a starting point. Okay, so this should be RRF score. This can be BM25 rank. We can have this as semantic rank. This is our weighted search. This should be RRF search. It's going to enumerate through all our results up to limit. It's going to do this. We can fix this, at least in this case. Take the hybrid score. Let's make sure we got it. This should be RRF score, of course. BM25 rank and semantic rank. And then the description. So let's import this into the CLI and let's give it a shot. So case, that's not what I want. This, of course, needs to be updated too. Okay. RRF search, I think is what it wants. And I should be able to pretty much do args.query, args.k, args.limit, the order. Args.k is their default value I was supposed to set. Probably. Default to 60. Okay, great. So it's going to be k. I need to RRF search. I'm going to go ahead and, okay, so that's in there. I need to go ahead and copy all this and we can do our reciprocal rank fusion parser. Okay. And now I just got to update this. Reciprocal rank fusion search, a hybrid search with reciprocal rank fusion combination. This needs to be a k value, which instead of a float is actually an integer typically with a default of 60. K hyperparam for reciprocal rank fusion. And let's grab a query and let's start working through any bugs now that we've got kind of the right shape. RRF final score is missing a positional argument. It's fair. Where's this called? Okay, let's try this again. Now it's got that argument. All right, so we have, what are we supposed to get? Anjali, the spy next door, and Kung Pao. Enter the fist. Okay, it looks like we're in good shape. So let's go ahead and try and submit. So this is really just focusing on the rank to combine. And this is, a really good way to combine scores without having to really worry about, the distributions and all that for normalization. All right, great. All right, great. We've done keyword search, we've done semantic search, we've done chunking, we've combined those into a hybrid search with weighted average and then a reciprocal rank fusion. That's kind of a core part of retrieval. So let's talk about LLMs next. With LLMs, we can enhance lots of parts of the search process. We often think of let's retrieve a bunch of results and then put it into an LLM, which is retrieval augmented generation. And here, we're going to actually enhance the retrieval process by using LLMs. So in this case, search has a problem. Users aren't expert query crafters, and even when they are, they may not be putting a lot of effort into it. And so they may look for funny British bear, or they might say the bear movie with the guy from Titanic. And there's specific answers for these. And an LLM can help quite a bit to fill in a lot of context. And so a user can enter a query. Before the search is performed, we can insert this LLM step where the LLM can fix typos, which helps with keyword search. It can expand on the meaning. It can break apart complex queries. You can add some missing context, and these results can be returned. They do not replace search engines entirely. There are many cases where they can be helpful and they can be used instead of a search engine, but that is not all use cases, not even close. By processing the query before the search to fix typos, it can absolutely do that by implementing a blockchain-based neural network. If you see blockchain, it's probably the wrong answer in general. by generating TikTok slop videos of a personified watermelon and equals smaller watermelon balls. So I think I'm going to go with by processing the query here. So perfect. So we're going to use Gemini. The reason we're using Gemini is because it has a free plan. You are not going to watch me create the in file with my secret API key because you don't get access to my API keys. But then we're going to use the .env library to load your code. You can also use UV to load an in file in your runner, but we're going to use .env, which is really great. We're going to use the Google's GenAI Python library to call Gemini. And so here are the steps. So you go to Google AI Studio to create one. You click on Create API Key. There's some docs here. So we're going to do this. Add the .env file to your git ignore. You don't want to push your .env to GitHub. This is actually like in a public repo. You don't want to do it because then your keys are public. In a private repo, you also don't want to push it into a private repo there. It's a shockingly common practice in a lot of AI organizations to store your secrets in a private GitHub wiki or .env file to GitHub, but I'm going to say I don't think you should do that. So store it somewhere more secure. Make sure you've got all this installed. You can use UV add. We're going to create a test Gemini Py file. We're going to do all this. Okay, so let's go ahead and do this. So let's go test Gemini Py file, and then we're going to import that test Gemini.py. Import all this. All right, so we're going to UV add our python.env. And let's see here, we need to do the same for Google-GenAI. Add Google-GenAI. So that's adding to our PyProject tomple in UV. So we're good in those cases. Created these, created this. Use the client models generate content method, and we're going to use this. Okay, and we're going to hard code this prompt. Okay, let's do it. So we'll say prompt is equal to here. Let's go generate content. We already have, let's create this prompt inside here. A lot of times, if you have a really big prompt, what I tend to do, instead of storing it in a string, I'll create a markdown file or an XML file if that's the format you're using, and I'll put it in this text file and then you'll load it in. It's a little bit nicer than just having it all in Python, which is actually very common to do. So cool, we need these two. I'm gonna move all the information I need over. All right, so we need our model name. We're going to use our client.models method. Let's take a look at it. So we need a model and we need the contents. Okay, that's good. So we go model and then contents. We're going to put as equal to our prompt. Very good. The generate content method returns a response object, the .text property. Oh, I hate these docs. Okay, let's just go here. Okay, so here the response.text gives us that text output. So that's good. And we want to print the text response, print the number of tokens consumed using a prompt token count. Okay, run submit CLI test. Okay, so let's print our response.text. So we have a response. Print our response.prompt token count, and we'll print our response.candidates token count. Let's see if that works. And what does it need to do? Okay, so it's expecting prompt tokens and response tokens. So we can do this, response tokens. All right, very good. Okay, so we got that. We got prompt and response tokens. I think we're in good shape. If name equals main, let's generate content. So now we got the script. Let's try running our test Gemini and see if we get a response. No such file or directory. CLI. Here we go. Response.prompt token count. Okay. No usage object. Okay. So what is it here? So let's go take a look at what is actually returned. The response has a usage metadata. Generate content response dictionary. Okay. It's a message dictionary. So let's take a look here. Validators. Okay, yes. So it returns. So it's got the text property. That's what we're using. So we have usage metadata. That might be what we want. And we thought it was the prompt token count. So let's try that again. Cool. So this should be usage metadata. Oh, .usage metadata. Yeah, okay. I don't know how I read that wrong. But yes, this is completely correct. All right. And I got prompt tokens of 19 and response tokens. Okay, that's great. Let's see what our response is, make sure it makes sense. Boot Dev excels as a RAG learning platform because it provides a practical, hands-on approach to real-world projects. You build an actual RAG application. That is absolutely true. And yeah, this would be a great portfolio project. Okay, great. Let's submit it and give this a shot here. Before I go on, I'm going to get rid of this here. And I passed. So this is great. This is really great. Okay, so let's start using the LLM to help our system. The typos can be extremely annoying if you're really waiting on keyword search. So Paddington could rank very low in keyword search, even if it's very obvious what the user wanted. And this is not just simple typos in movies. If you're doing something in a medical or legal domain, you don't want, just because they typed in the term slightly wrong for a very hard spelling thing, for it not to work. And so LLMs are very good at spelling. And so we can use it to fix it. And this is a great example of where a typical spell checker might not catch that. That's a bright red carpet, but it's not actually a spelling error. It's an error because that's a real word. And so an LLM can catch and fix a lot of these very, very easily for you. So prompt engineering. A lot of times people think, prompt engineering's kind of funny or a joke or not there, but there's like useful tips. A lot of them really do come down to being very clear about what you're writing. So if we look here, and OpenAI's got one, everyone's got one, but this is one. You can look at this and you can read through lots of stuff. So for example, be clear and direct. There's a whole page on how do you do this, and here's some examples of how to be clear. So reading through these and getting an idea of what that means here. Using examples. Why do you use examples? Adding good examples in, wrapping them in example tags is helpful because models have seen a lot of that. Syntax, different models are trained in a little bit different ways. And there's information about long context and giving Claude roles, system prompts. So reading through some of this is actually pretty helpful. I will say the most important thing, though, is try and write a reasonable prompt and then see what the results you get and run it on a lot of real things and then tweak the prompt a bit and do that a few times and you'll be doing pretty good. There's a lot of times where I see a prompt that someone's written for a system that's not working very well, and it's very clear that nobody's ever actually read it. Like they used a model to create the prompt, or it was like a dummy prompt, and they never went back and looked at it again. Most of it is look at the results, think about how you might be more clear, how the prompt might have been, contributed to it, and just try and improve it and do that. All right, add query enhancement support to this. So we're going to add an enhanced argument to our hybrid search, RRF search. For now, it can either be spell or not spelled at all. You can add explicit choices like this. So here's a choice. Let's do this. We do not need this test Gemini. We have successfully tested it. Hybrid search. Let's, we want the CLI for now. So we need to go in here. Gave us everything we need. I'm going to go ahead and flatten this a bit. I am really zoomed in for you guys. Make it nice and easy to read. So I'm going to save some vertical space. Okay, so we have the choice of spell here, and we'll want to add in args.enhance. If spell isn't supplied, we'll run it as normal. But if it is, we'll provide a query to Gemini. So we will use a system prompt. If the query was enhanced, we'll print it in this format. Okay, so run the enhanced query. Okay, let's do this. So we know how to run it because we do have this test Gemini.py. So this is this generate content. Let's clean this up a little bit. So we have our prompt. Great. We need all this. We need all this. We don't need that. Okay, so let's go ahead and let's create a llm.py that will handle this. And in here, we can say from lib.llm import generate content. And what do we need to do here? We actually want to return the response text instead. Okay, but actually let's do correct spelling. And what I'm going to do, I'm going to create a prompts directory. I'm just going to say spelling.md. I'm going to put this in here. Not going to make it an F string here. And in here, in my llm.py, I'm going to I want my prompt, and we're going to say with open, and I want to open the CLI. Let's go into our search utilities. So we have some project root. We have the data path. So what I want is I'm going to make a prompt path here. And this is going to be here, project root /lib/CLI lib /prompts. And I'm going to import that. Okay, from lib.searchutils import my prompt path. And so then we're going to open prompt path / spelling.md. So that's good in read-only mode as f. And so then we can say prompt equals f.read. And this is going to be the query. So what I can say is prompt, correct spelling on a query. We can take the prompt and the query. And what I can do here is say prompt is equal to prompt. And we can format that, I think, with query equals query. Okay, so let's try this. We correct the spelling of this. So we can generate content and we can say pass in our prompt. And we can pass in the query. And let's try returning that. Okay, so I probably should have read the instructions. So let's see if that's actually what I was supposed to do. Return, if spell isn't supplied, return it as normal. But if it is, provide the query to Google. And if it was enhanced, print in this format. Okay, so let's try and figure this out here. So RRF search. So we can say the method is args.spell. So we can say if args.spell. So let's actually say match args.enhance. In the case of spell, well, let's print the enhanced query. I don't need to do this again. I can just say spell. I'll want to fix that later. And let's do args.query to, you know what? I'm not sure that I need this. Let me just try this again. Okay, yeah, let's take this back. Let's go into this hybrid search. Let's see what we're doing here. Reciprocal rank fusion here. Okay, so this clearly needs our enhance argument because it's going to get passed. Okay. So let's say match on enhance. So this is where we want to do this. And then if it's spell, what do we want to do? We want to use our correct spelling with our query. So we can say new query equals, and then we want to do that printing of that we were supposed to print. So then we can say, let's print the enhanced query with the method, which in this case is spell. I don't love this. Like, I feel like this can be better, but that's okay. I'm just going to go with this for now. So this is query. And then this is new query. And then I don't think we need this anymore. So I'm just going to go query is equal to new query. So we'll print them both out and then we'll just use the new query. And then this should really happen afterwards. Okay. Printed that, spell isn't supplied, run RF search as normal. But if it is, ask it to give with correct spelling. Okay, so let's give it a shot. Okay, let's see. British Bear. Let's see if it fixes that. I use Google and Gemini quite a lot, so I just have global environment variables set. Okay, description. Okay, so what is going on here? Args query, args limit, args enhance. So we go in here to query K and limit. See, description, line 103. So what's going on here? Did I introduce a bug somewhere? This is result description. Rank and enumerate semantic results. Semantic results comes from semantic results here, which comes from search chunks. And does this have, and this is returning the document. Oh, okay. So let's just do a little bit of a hacky fix and we'll duplicate it for now. This document might be used somewhere else. I'm gonna just duplicate it, see if that fixes our problem quickly. Okay, it does. So we can see British Bear is fixed to British Bear. So that worked. That was great. Seems like we've got good results. And what if I run it without anything? Does it still work? It does. Okay. Let me unset this. So I think we're in good shape here. Let's try and submit. Awesome. All tests passed. That's all I could hope for here. Okay. Chapter 7, lesson 3 is done. Okay, we did spell correction. That's one example. Query rewriting is another. This happens to be really, really commonly helpful. You know, scary bear movie from a few years ago, movie about a bear in London with marmalade. There's all kinds of stuff where you can get more specific, concise queries. Some of it is for quality, but some of it's for consistency of your results. And so you can have them all shaped to be like Google style queries. So like whether someone puts in whatever format people do, you can rewrite it. So you can say like, hey, if somebody asks a question, rewrite it in the query. Here's the format of the queries. And so you can give a more predictable experience sometimes by helping users adhere to kind of a style guide for your search queries and have less edge cases. And so let's go ahead and implement this. We're going to do a query rewriter. Add to the enhance method. And this is really very similar to what we did before. We're adding another argument. Let's jump into it. I'm going to add a new prompt here. I'm going to call it rewrite.md. We can put this in here. Don't need this. So there's the original. Perfect. I can go into llm.py. I can just create a new one here for my query. This goes to rewrite.md. Cool. See here. This is great. I need to go in here where I added this in, and we need a new thing here. So we can say new query equals rewrite query. We can add that in here. What do we want to call this? We want to call it rewrite. So that was good. Print this out again if we need it. So here's what we're doing here. Don't love this duplication. Can I move this into here? Can I move this? So this query here, prompt query. We can say our enhance. You know what? I'm going to leave it. I think it's okay. We'll just do this. So we do have a duplicate pattern here. So we could probably just get rid of the match statement. But for now, let's make sure we have things working. So we have query equals new query. Then we need to go over to our CLI, and we can make this be able to be a rewrite. So let's see if that's all we needed. Bear movie that gives me the lulls. Let's see how it rewrites it. Comedy bear movie, funny slapstick animals. Okay, that sounds pretty good. It does have the string it was looking for. I think we're good to submit. Very nice. Okay, very good. All right, query expansion. One more way, and this is really powerful, and it's often overlooked, is you can enhance and expand the query before it goes into the semantic search. Sometimes users are very specific. They might search for grizzly, but want other kinds of bears, or they want related terms, or they might want to do stuff. And as I consult, a lot of companies overlook query expansion, and it's a powerful tool. So for example, especially if you're heavy on keyword search, if you have funny, you can add on comedy, humorous, amusing. In most cases, all these are very related here. You can broaden it. You say, hey, if someone's looking for a bear about grizzlies, maybe they want bear or animal movies too. Or, for family, you can say, hey, let's look at family and kids and children animated movies. And you can also do programmatic expansion. So this isn't just limited to LLMs. So if you have a genre you're looking for, you can expand out programmatically for subgenres or very related things. So, I had a client that was doing this for medical students. And one thing that you can do is if you have a particular topic for an exam, you can create a one-time mapping of, hey, these are the kinds of topics that are typically covered at the same time in a medical class. And so you can look and explore at kind of clever ways to enhance your prompt and expand out. Okay, so let's add a new string choice to the enhance argument, spell, rewrite, or expand. Here is the prompt. So we've got doing kind of the same pattern as before. Let's get her done. So we have expand. So we have the prompt. Got the same thing here. We've got the rewrite. We've got the expand. Okay, that should take care of what we need. So then we need to go into our hybrid search, add this here. Again, we're kind of doing some duplicated logic here. Okay, so rewrite, expand, query, new write, expand, query, expand, query. Let's make sure I'm calling this all right. Yep, expand was the correct name. We can import this. We can go over to our CLI and add in expand as an option here. Cool. Let's see if we did it all right. We'll take a chance. All right, we passed. That's great. It is actually bugging me a bit that this is duplicated so many times. So let's see what we can do here. We can fix it here, or we can fix it upstream. Let's maybe fix it here. So what we can do is we can say, let's refactor this out. This is the core pattern. The only thing that changes is here. So we can say augment prompt. Then we can take a query and a type. We can move all of this in. And if this is the type, then we're in good shape. And so then this becomes, correct spelling becomes augment prompt for spelling. So that becomes augment prompt for spelling. And this becomes it for rewrite. And this becomes it for expand. Now we can leave it like this, or we can just call the augment prompt directly in our hybrid search. So I can get rid of all of these, and let's just do augment prompt. So then all of these can just augment the prompt. So we can say new query. So we can say if enhance. We can augment the prompt query and whatever the enhance method is. Say new query Then we can print this with whatever the enhance is. And we can do this. And that means we can delete all of this. That's a nice little reduction there. Let's make sure we still pass. Okay, we still passed. Great. Okay, we just got done with LLMs, so we're on to re-ranking. Re-ranking can be done with LLMs or with something called a cross-encoder, which we'll look at. This really solves a big quality problem that we have. So if you think about what we've done, we've encoded and created embeddings or inverted indexes and all that stuff for our semantic stuff based on the document. So we have a movie description, and then we encode it. And then later we ask a question. We say like, hey, is which one answers the query? And there's a disconnect there. And if you think about it like intuitively, that's not necessarily the most efficient way. For example, you could give me a book and say, read it. And then afterwards, ask me questions about the book. And I might be able to answer the questions. What would be better, however, is if you said, hey, read the book. Here's the question I want answered. Answer the question when you find it in the book. And then I know what I'm looking for. I have that context. And that's what re-ranking basically does. The first step, we're trying to do a very, very fast search. And it is fast because we've cached almost all of it, which is embeddings. Now, re-ranking is much more accurate, but it's slower. And it's because we cannot cache creating, the embeddings in advance. We can't cache anything in advance because what we're doing is we're going to give it both the query and the document together and say, okay, here's the query. Is this relevant in the context of this document? And then you're going to do that over and over again. And so you don't have anything cached. And so it's really slow. So why is this useful? Well, because we can use all the fast search stuff, the BM25 and the semantic search, where we have the cached embeddings and the inverted index that does a cache. We can do that really fast. And then we can re-rank. So we're ranking a second time. Maybe we want the top 5 results. And so we might do a really fast search and find the top 100 movies and then use a really slow approach of re-ranking, or a much slower approach to on those just the 100 to get the top 5. And so we can do a really fast cut and then we can re-rank for just to get the top 5. Because the fast search may not be perfect, but it'll generally give you a really good slice. So this is how it works. You have a user query. You use this fast search to narrow the search space. This is the keyword and semantic or the hybrid search, all the stuff we're talked about here. And then we do a slow search on the best results to get even better results. This is called re-ranking. And then we have our retrieved document. So this re-ranking step is what we're doing. So we rank and then we rank again. So we re-rank. And again, it covers the query and the full documents together rather than as separate things. Okay, what's the main advantages? It uses less storage. No. The hot new thing in LinkedIn influencers are talking about, oh man, I wish LinkedIn influencers would talk about this instead of the crap they do talk about. That would be great. Okay, re-ranking is faster than vector search. No, it's much slower. And re-ranking considers the query and the full documents together to determine relevance. That's it. All right, great. Very nice. Now that we know what it is, let's do it. We can go through and we can use an LLM. They're slow and expensive to run on large data sets, but they have a lot of built-in knowledge and reasoning and short-term memory. And so we can use this for re-ranking. And this is a fairly common approach because, it works pretty well in most situations. Now, we have 5,000 movies and you might actually have 100,000 movies. You wouldn't want to do an LLM call for all 10,000 movies. That would be very expensive and very slow. So what you might do is you might, do a really fast search for the top, 20 and then re-rank to get the best top 3 or something like that. So you're only calling the LLM for 20 queries. And you can do that in parallel or whatever. So let's do this. We're going to add a new optional argument for re-rank method to the RF search command. So let's go ahead and just start with that. So let's do this. For now, it can either be individual or not supplied at all. Sweet. We'll add more options later. So let's give some help text. Re-rank method. Cool. So we're going to do the RF search as normal and then gather 5 times as many results as the limit. So like if we had 5, we'll do 25. And then we'll do the re-rank method of individual there. Okay. If the individual re-rank method is provided after doing the initial Search, run results on LLM prompts, asking the LLMs to provide a new score for each document. Okay, here's a system prompt we can use. So first, let's go ahead and add to our prompt, individual re-rank. Okay, so we need a title in here, some sort of document or description. I'll just say description. So we got a query, we need title and description. What is it saying, telling the LLM to do? Rate how well it matches a search query. We consider direct relevance to the query. So again, it's got both. The user intent, what they're looking for, content appropriateness, rate 0 to 10, 10 is a perfect match. Give me only the number in your response, no other text or explanation. So you can do 0 to 10, you can do 1 to 5, you can do a lot of things here. And then we have this telling it to give it a score. There's all kinds of stuff in here. You could give examples of matches. You could give it more information. So like if you have a specific thing, you could say, based on your target audience, you could inject information about their preferences. Like they tend to enjoy comedy movies. They tend to whatever. So if you have information, you could inject that in here to give it more information. But we're going to start with this. To avoid hitting a rate limit, sleep for 3 seconds. I think I have a paid key, so I'm not going to worry about that. But, you know, on the free tier, you probably need it. Sort the results by the new score. Print the results after truncating to the limit. So let's go ahead. We have this in the CLI. We're going to need to pass to the CLI our args.rerank method. So I don't need that anymore, I don't think. I'm going to do, let's just create a new rerank.py. It's probably going to have a lot in common here. So let me go ahead and take all of this. And so we can say individual re-rank. We have the prompt. We're going to need to have our documents. So some sort of movie documents to re-rank. And we're going to need the query. And so we first need the prompt. So we can open prompt path / individual re-rank.md. And then we can make this the file contents. What we need to do is we now need to re-rank these. We need a few things based on what was in the prompt. The query, the title, and the description. Let me close some old files. Okay, so we need query, title, and description. And let's say for doc and documents, we're going to need to go through each one because we're doing this one at a time. We'll do something smarter later. Let's get the query is passed in, so I don't really need that. Let me give a temporary prompt, which would be prompt.format. And we're going to say query equals query, title equals title, description equals description. So we can say doc title, probably just move that here actually. And I can probably just do doc and description and move that here as well. Okay, so that's great. So I'm here, I'm formatting this a little bit so I can read it better. So we've got a prompt. How did we call this? I think we used a generate here. So we took the prompt. This is our response. This is how we get a text. Okay, so this goes through. We're going to use the prompt on this model, get a response. Okay, and what we might want to do is we might want to say for this document, let's take re-rank response and let's bet that equal to, let's try and cast response.text to an int. You know, for good measure, let's just print this. Okay, and then we can return all our documents back. Okay, so I think that should work. Doc and documents. I'm not sure that's gonna work. Let's see, let's not do this in place. Okay. So this is going to be a list of documents. And for here, what I want to do actually, let's do response results.append. And we can put all the document stuff back in there. And then we can also add a re-rank response. So we can add this in here. So let's do that. I think that'll be cleaner. Let's just print the response text and then the results just to make sure we're getting what we expect. Okay. This now needs to take in the prompt. Great. We are, I think, in good shape. So then we need to call this after our reciprocal rank fusion. That's in hybrid search. So this needs to add our re-rank method. I think that's what we called it. Reciprocal rank fusion. And we said if there is a re-rank method, we do 5 times as many results as the limit specified if the re-rank method is individual. So we need limit equals limit times 5. So we could say actually limit times 5 if there's a re-rank method, else 5. I think Lane might not like me doing that. So I'll do a little better. I'll still do the ternary, but I will do rank limit. Let's do RRF limit. That's a little better. Okay. If the individual re-rank method is provided after doing the search, run the results through the series of LLM prompts, one per document, and use this. Okay, so now we have from lib.re-rank, import individual re-rank. Good, let's fix that, re-rank, great. And we saw we can do that because we can say, so there's the results. We can say re-rank results is equal to that, which takes in the query and the previous results. We do need to do the score descending, present the results after limit, preserving the RF score. So reciprocal rank fusion, do we need to re-ranking? Okay, so we need to add this to the print as well. So we can say here, if re-rank method, we can get the re-rank results. We can say re-ranking top limit results using individual methods. Is that, I think that's supposed to be the limit here. Doesn't say exactly, but I think so. So we rank here. Let's call this just final results. So then we can say, oh, okay, so let's add into the individual rank. Let's just sort them here. And this is actually a bug. This should be results. And we can then do results equals sorted results, where the key is equal to something, lambda x, and then we can say x re-rank response. 10 is a perfect match. Okay, so yes, descending is correct. Reversed equals true. And we can return that. And then I think everything should just work. So let's see if that is true. Let's run a command. Okay, so I'm printing a lot of stuff. I'm gonna get rid of this. It seems like stuff is there. Could add some progress bar in here. No, that's a lot slower, but you can see how much slower this makes it, the process. And sometimes that's good. And sometimes, you know, people want really fast results and it doesn't have to be great. Like if you're, I don't know, searching for cat photos, you just want cute cat photos. It's not really that important that the most absolute cute cat photos are at the top. You know, you just want some that are good. People to scroll through. For other things, maybe users are okay waiting a little bit in order to get better results. So it all depends. So let's see, we have this bug here. Let's see what's in response text. So what I'm thinking happened is one of the times the LLM ran this, you know, it didn't give out a number or something that could be cast. Yeah, we got none there. Okay, so let's clean the response text. So we could call this response.text. So this will say if this is none, it'll make it the empty string. We can also strip it. So if it's none there, if it strips it there, we could still get other strings where this fails, but I'm not seeing that. I'm only really seeing a non-response. So let's see if this solves it for us, or if we need to get a little bit more robust. And these are things you might have to tweak the prompt with. There's libraries like Instructor that kind of helps with it. You know, they're all just basically prompting tricks. There's not actually guarantees. You can work on the prompt. You can build more robust stuff in, doing a bunch of them and seeing what all the variants of outputs are. Usually illuminates a path for you. So I'm curious. Okay, so what is this? So let's say print. Let's clean the response text. Let's look at the response text, the raw response text. And let's look at the query. I guess the query will be the same every time. Let's look at the description. Maybe there's something wonky there. I don't really want to see all of them. Wait, invalid literal for int with base 10. I see. Okay, so I do have it. So I don't think I need this actually. So let's just say we clean this. Let's try going clean response text 0 if clean response text is this, else int clean response text. And let's just say if we can't, let's print the doc title. Give ourselves a little bit of logging here, and we'll just set clean response text to be equal to 0 in that case, and then we'll append that. Because in this case, yeah, I think 0 is probably fine. I should probably do like a value error here, but I think it's okay. It's just trying to cast one thing. Yeah, so these all seem okay to cast to. So I'm saying family movie about bears in the wood, Lake Dead, Jackass. These don't seem like family-friendly movies here. This is a horror slasher. Okay, so it's saying it's basically not relevant at all. Serious Skin. So these seem to make sense. Okay, so let's do this. Let's see if we can make this better. 10 equals perfect match. 0. 10 equals perfect match. 0 equals not relevant. No other text or information. Every movie must have a number, even if it's not relevant at all. Check one more here. Psychological tragedy film. Yeah, I think that's probably not the best for kids. So it seems okay. So let's see if we can tweak the prompt. We're prompt engineers now. Let's see what we got here. Oh, you know what? This final results isn't even being used. Let this run for a bit. Got stuck here. I wonder if there's some sort of encoding issue that's happening. Maybe I do need a sleep here. Let me try this. So why would this be taking so long? Let's think about this. We're doing this. It's going to remake much individual. Doing this. There's no enhancement method, so shouldn't be running this. Let's add some. I'm going to add some logging in here. Prints enhancing. Now let's see what's going on here. Because this really should be. Let's do print doc title. It's interrupted on results dot append. So this actually shouldn't need a casting anymore. That shouldn't cause any issues. Okay, so maybe I was just too impatient. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The limit is 3. Oh, so it should be 15. Okay, yeah, I just needed to keep going. So this is why progress bars or printing things as you go is helpful. So you don't kill the process waiting for it multiple times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 6. This shouldn't be right. Limit times 5 if there's a re-rank method. Well, we said limit is 3. Okay, so let's figure out what's going on here. Let's print the limit and then the RRF limit. We're going to do the RRF search and then let's print the length of results. So why are we doing too many here? 3 and 15, 5,000. Oh, okay, great. I was trying to process them on all 5,000. So that's cool. Question is why? Let's look at this results here. Did I put this in wrong? Okay, query K RRF limit. So let's take a look. Let's go to the RRF search. Limit is 10. RRF search combine results. Ah, cool. Limit. That should work a lot better. Okay, great. Now that should work. I just needed to, I had a bug in my RRF. It was grabbing too many, so it was re-ranking too many. That's why it was so slow. So now this should all work well. Now that that's figured out, I should be able to remove these. Can remove that there. I can remove this here. I think the rest, oh, I can move this here. 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so a couple more, then we should be good. Okay. All right, very nice. So we've got this now. Now we fixed that bug. Should see the Berenstein Bears Christmas from this. And we see we got it. Okay, let's see if we got the right answer. So it'll take a little while longer. But I think we're in good shape now. This taking so long is why we would want to do this in a batch. That's what we'll do next, is to try and speed this up. And there's actually 2 ways of speeding this up. One is we're going to do LLMs in a full batch. And then the other is we can use something called a cross encoder, which is basically a classifier, which can work very quickly as well. And so that's a second option that's faster and it's something you can fine tune and it's cheaper. So we'll be looking at both of those throughout this chapter. All tests passed. Okay, this is great. All right, re-ranking. We're going to do LLM batch re-ranking now. So we saw how slow it was doing one at a time. Doing them individually is straightforward. Now we're going to do them in a batch. So we can do it a little bit more efficiently, a lot faster, a lot cheaper. Because with the LLM calls, we're putting in the query and then the documents, over and over and over again. We could then try and do it in parallel and do a whole bunch of parallel stuff. And then you've got a whole bunch of complication there. So we can do this in a batch. So we're going to add a new method to re-rank. So there can be a batch, 5 times as many results as the limit. That's great. Then we're going to have another prompt. What you'll see is we're going to return them in order of relevance and a valid JSON list, nothing else. So let's go ahead and put these into our prompts. Batch re-rank. We got the query and the doc list string. Okay, great. Let's go into our re-rank and we want, okay, I don't think we actually even needed that. That wasn't the problem, but that's okay. We pretty much need the same thing, I think. But we're gonna do this in a batch. Parse the JSON, sort the results, print the results. So what we can do is we can kind of steal a lot of this as a starting point. So we don't have to rewrite it. We don't need to iterate through because we're going to do one big old prompt. We don't necessarily need this yet. We are going to need to generate a prompt and a response. And we are going to want to do the batch re-rank prompt. So we're going to need to do something with documents. So let's look at this prompt, what it's doing. This is the movies, the doc list string. So we're going to need to populate that in. So let's format query that is equal to, and we'll do this doc list string. And so that means we need to figure out what this is and what it should be. Probably going to be the description, but let's just double check this, see what we say here. Add to the CLI. Let's start just checking off the list. Look at the list, check it twice. Hybrid search. Here we want individual or batch. So that should be all I need to do there. So it says again, which means I already did it. The batch re-rank is provided after doing it, run it to a single prompt. It should include all the documents and the query and ask for a comma separated JSON. Okay, parse the JSON using here. So what we need, so doc title, doc description for doc in documents. So let's do doc title. Let's use XML tags here. I'm going to do title, put the doc title in there. And what I'm going to do, so let's go here. Let's go movie title equals title. Then we'll put the description in there, and then we will close the movie. We can put another new line for Azure. So let's do this. And so now we could put this in here. Format dot. So this is like movie template. Maybe not the best name, but that's okay. And then we can say, let's just make this a real loop. I'm trying too hard to make it a comprehension. That's never a good sign. Okay, so we can say doc list string equals this. And so we can say for doc and documents, doc list string, and we can append our mtemp dot format title equals doc title. And then we can say description equals doc description. Okay, then we're good, I think. So then we can put this in here. We can get a response. We can try to response parsed. So we can do JSON.loads on our response text. I'm going to go ahead and print the response text first, just so I can see what's coming out. And we can bring in our JSON library, standard library. Okay, parse to get there. Okay, I did this. Sort the results by using the new rank in descending order. So we can go through and we can say, for doc and documents, we do that. We got this response parsed. And so then I can say, for doc in the documents, so we want the results to be results.append. And we're going to do the same thing we did again, where we do ** doc. And we want the re-rank score. And that can be from our response parsed, and we can do the index location, which means we need to enumerate through them. Response text parsed, enumerate through them. I'm going to cast an int just to make sure we're good there. So then once we have that, then we can take our results and we can sort them. So we can say sorted results, lambda x, this should be the key. And we can say x, whatever I called this, re-rank score, and we can say reverse to equals true. And then we can return our results, I think. Okay, and then I think I can go in here. So this should actually be called batch re-rank. So then I think we should be able to go into this hybrid search function. Here it is. So now we can say case re-rank method, or match re-rank method, I should say. So we can match on the re-rank method, and we can say if it's individual, then we're doing this. If it's batch, then we're doing this. We can print this out. And if it's nothing, then yeah, we can just pass. We don't have to do anything. So I think we can do that. So let's give this a shot. Let's see what we got. I'm going to learn from my mistakes. No, I'm not. I'm not going to add printing. We'll just roll the dice, and then we'll debug it if we have an issue. JSON decode error. What do we got? Okay. So what do we got? JSON. Okay. Let's see what we did. Return only the IDs in order of relevance. Okay, I see. It thought when I created this prompt that the title were the IDs. So let's add this in. let's do ID equals index. And I'm just going to put the title directly in here. I think that's fine. We can do this index here and we can enumerate to give it that. Okay, so we can try this again. Because yeah, what it did is I think it saw the title and it's like, oh, I need to give a list of IDs. These must be the IDs. That's what you gave me. So I need to give it that context. And now it seemed to work. So we got a whole bunch of numbers in there. What was the expected response? We were searching for family movie about Bear in the Woods. We're looking for Berenstain Bears. We did not see that. Let's see here. Care Bears. I mean, it's doing very unpredictable. Okay, so we have the movie IDs here. So what is this doing? It's going through the documents and it's giving the index based on that. Here, we're going through the documents and we're giving it a re-rank score based on the parsed response index. What is this? So this is the tricky thing about this. Let me see here. I love the Berenstain Bears. So that's relevant. Let's just see if this gives us the result. Because if it does, then we've just got some weirdness. If it still doesn't rank it, I'd be very suspicious. So I am very suspicious. Now, okay, let's take a look here. So let's do this. Let's print out the prompt before we send it. And let's just take an actual look at the prompt. Okay, so it had trouble parsing it. So we can improve the robustness of this a little bit. Let's just clean that up a little bit. I think that should solve that piece of inconsistency. So the prompt's coming back with that in it, and it's not able to cast that because it's got that extra fenced block syntax in there. So we could just strip that off, move that. Okay, let's see here. Here is the ranked list of movie IDs. Okay, so yeah, we're having some problems here with the prompt. So let's go back to our query here. IDX of 75 is most relevant. So remember, only IDs JSON.loads, so nothing but the list. Let's try again. We're doing some real prompt engineering now. Great. Okay, so we got it. It did still put this in, but we stripped that off, so that's okay. We see the movie ID 14 here. Okay, so what do we got here? Did we even have, and we were supposed to have Berenstain, right? Berenstain Bears. So this is ID 1. Oh, this is interesting. 14, ID 1, ID 0, 1. Okay. So for whatever reason, this is not ranking them super highly using the individual method. Is that just a bug in mine here? Let's look at the hybrid search. Using the batch method. And let me make sure this prompt is coming up properly. And let's just try one more time just to make sure. Because if it still doesn't put this up here, then we got some issues with the IDs somehow. I'm looking at that. Let's see here. Whoa, actually, it did put 1 first. Okay, so something is definitely wrong with the ID. Okay. Yeah, so this is something that's definitely wrong with ours. So we got this back. We can get rid of this prompt. Let's look at if Berenstain is in the doc title. Let's just print the ID here. So then we know the ID of this one. We are printing the response text. So that's great. Let's print the response parsed. And then let's start there. Okay, so this is here. We definitely got it. Okay, so Berenstain Bears is 1. We have this JSON is giving us 1. We parsed it as 1. And then we get this as the bear. Okay, so what is going on here? So we're enumerating through our documents. So this ID, IDX and enumerate documents, and response parsed. Ooh, okay. So this is going to be the re-rank score. Oh, yeah. So we're going to go through the documents. Okay, so this should be, we want to find wherever the index is. Okay, so this is, okay, so number 1. So this is going to be 0. So let's say we get to 1. So IDX is going to be 1. I see my mistake. So IDX is 1. It's going to say let me just put this back to what it was so we can explain. So IDX is 1. This document, IDX, is the Berenstein Bears. This is just going to look at the first position in response parsed, not necessarily there. So what we need to do is we need to find where it's at in the list. So if I have 1, 3, 5, 2, I want to index to find, say, the 5th item. So that says it's in the 2nd position. Or index to find the 1st item. That means it's in the 0th position. So what I need to do is I need to take this response parsed, and I think if I do this, it's not going to say this in the list. So I might get an error. I might need some error handling there. But what I want to do is I actually want to do the index location of the index of the document. And I think that's going to give us better luck. I might get a bug if the doesn't return it. But now we're doing it properly. So now we get 1 first. Okay, we got this. So what is going on here? Bear here. So we have the response parsed. So we get to 1, that should be 0. Oh, and then we don't want reversed because this is first, and we want it. We want that to be good. So that's perfect. Last bug, I hope. All right, good. We're good. So that was the problem for this last one, is that we were reversing the order. So we were putting the largest numbers last, but in this case, which is the largest numbers first, which is what we wanted in most cases before this, but not this one. So, okay, we have solved this problem. So we can clean up some of these print statements here. And then we can submit, I think. All right, perfect. We passed. So we are in good shape. All right, lesson 4, we're on cross encoders. So this is another approach to re-ranking, and it's kind of like using a classifier. So we used what was called a bi-encoder, which is embedding queries and documents separately, and then using cosine similarity to get a relevance score. That's what our semantic search did. Cross encoder embeds the query and the documents together as a single input. So in a sense, like we were doing the LLM re-ranking, where we put the query and the documents all in the same prompt, we do that with a cross encoder as well. And so its embeddings that it encodes are more accurate. The output is the score. We don't need to compute it. And they see that full context and all the interactions. So it's much, much more powerful. But again, we cannot pre-cache the embeddings because they're created with the user query as context. They're a lot faster and cheaper than LLMs. You know, it doesn't have all the capabilities of an LLM. And these cross encoders are trained to do just this one thing, which is, you know, re-rank it. Take a query and document pair, output a relevance score, like a regression model. Okay. The second major advantage is that they can be fine-tuned. So if you have a specific domain and you have a big data set and you build them up, you can fine-tune to make it better and better on your specific data. Maybe that's your internal company data set that's not publicly available somewhere. Maybe it's product questions that are specific to your exact products. And so that's pretty helpful. Not going to do the fine-tuning, but no, that's an option. Cohere API has a good re-ranker. So you can, if you want to just like get a re-ranker going quick, that's a good option. I think there's several other re-rankers, APIs, and those typically use cross-encoders. Let's implement it. We're going to implement a cross-encoder re-ranker. So we can now add the cross-encoder to the re-rank method. Again, 5 times as many results, so we don't need to change anything there. So we can find our hybrid search CLI somewhere, and we can add in this last method. So we've got cross-encoder now. And we can go ahead and we can go into, let's put this in our re-ranker file. So let's create a new one called cross encoder re-rank. This is, again, needs the query and the documents. Boom, boom. And if this is provided, we're going to do this after the RRF search, just like the others. And we're going to create a new list of pairs where the first element is the query and the second element is the document. So as you see here, we can say for doc and documents, we can append. We have a list, it could be a tuple, a query, and then title and document together. And so this is what's going to get cross-encoded together. From sentence transformers, that's what we used before. We're going to use the cross-encoder, and then we're going to create a cross-encoder instance. And this is a particular model we're going to use that works very nicely locally. From sentence transformers, import cross-encoder. Oh, I see. RAG search engine. Okay, so I'm up a directory here. So let me do this. I can fix my environment quickly. Okay, so let's fix this. Okay, so now we're back. We're back on track. So we can go into our re-ranker. We got rid of our squigglies. We have our cross encoder. Can then create our cross encoder using this particular model. There's lots of options. This is a tiny one. There are better ones that are larger, but take up more memory and more compute and are slower. So it's a trade-off. Use the cross encoder to compute scores. So this is the .predict. We're going to sort them and print the results after truncating to the limit. Let's take a look. Cross encoder, predict the pairs, sort the results by the new scores in descending order. So what we need is we need to go results. We can say for documents, we can say results is equal to, or results.append. We can keep the document there, and then we can put cross encoder score or something like that. I'm not quite sure if that's exactly right or if I need to like index into a value, but let's give that a shot. And we need cross encoder score. Okay, so I'm going to go ahead and print some of them just so when we run it, I can see if it's the format I expected. And again, we can sort our results. Sorted then the results with the key of, we can say X is our cross encoder score. We want descending order. We screwed that up last time. Reverse equals true. And then we can return our results. So now over in our hybrid search, we need to add our printing in. And we need to add in this last case statement, which is for cross encoder. So let's import our cross encoder re-rank. Let's call our cross encoder re-rank with our query and our results. And we need to do some printing, re-ranking top 25 results using the cross encoder method. Can't do that. Okay, that's fine. I guess I could put an extra if statement in, but we've come so far using the cross encoder method. Okay, and then we need to add this cross encoder score in here. So we if re-rank method, I'm just going to go ahead and print that here, cross encoder score, and we can do our cross encoder score. Is that what I called it? Guess we'll find out. Okay, so we've got that in there. We can check our CLI script. I think that's got that in there. Let's just go ahead and run it and start working through some bugs if we have any. It might be a little slow because it might have to download the model first. Oh, nope, super fast, even with downloading the model. Okay, we're ranking top 25 results using cross encoder. Okay, I see. So we need to fix this because we seem to have it in the right order. But unfortunately here, so this should be limiting it to the top 5, I think. For some reason, it's not. Cross encoder results rank. Let's see here, print. Let's just do this times 5. That gives us a nice little break. Interesting. So the method is cross encoder. Oh, because we have limit of 25. Okay, so it changed the number on it. So that's okay. So what is it looking for? It's looking for Care Bears, a bear for punishment, and the Country Bears. Care Bears, a bear for punishment. Country Bears, one of them. Country Bears, okay. And a bear for punishment. Okay, so we're in good shape. We got them all. Yes, we passed. So we'll move to the next. All right, we're now into chapter 9. This is on evaluation. That's important because you need a predictable experience. You need to know how well your retrieval is doing, how well your app works to deploy to production. It's very similar to having a testing framework in a lot of ways, but you have a lot of stochastic results. So you don't get consistent results all the time with LLM models. You can sometimes with retrieval models, but it's a little bit of a different flavor. It's looking at metrics. It's kind of like halfway between unit tests and business metrics, kind of. A big thing is manual evaluation. I think that, Lane's throwing shade about things coming back to vibes. I actually think vibes are hugely important in everything. I don't think it's just AI. I think that if you're building a CLI tool, it should feel good. You should have some like vibe over whether it feels nice to use, whether it looks good, whether it's intuitive, things that are hard to quantify. If you're building a website, you want it to have good vibes, feel right, feel like it's engaging and sucks you in. And in AI, you want the same thing. So I think it's everywhere. So there, Lane. Okay. So you want to use it as a user would. You want to try searching things, seeing if they come back. It's really hard to completely automate how well something is, because how do you define, like, what metric can I use to say if this is good writing or not? Or to say, is this appropriate for this lesson? It's really hard to do because, the text isn't always consistent. The documents might be updated. You don't have a hard rule. That's why you're doing a model to predict some sort of predictive model. That's why you're using that to do retrieval, because you can't, code it in. And so a really good starting point is just to look. Try to search for it. And you'll be surprised how often these issues actually happen, or issues like it. You search, if a user searches for dinosaur and you get 10 results for The Land Before Time, each 1 through 10, and Jurassic Park at 11, you could say the search is working, but that's still not a good experience. And as you look, you want to say, like, did I get enough information to even know whether the movies were relevant? Should I have returned fewer results because the last few weren't relevant? Should I return more? Is this actually useful to me? And that's pretty important stuff. So what is the primary point of manually testing and looking at your search results? To understand the usefulness and gaps in search and practice, which is something no metric can fully capture. Absolutely right. Prove to our friends, family, and coworkers that we can still provide value and can't be replaced by AI. We're lazy and want to avoid having to implement automated evaluation metrics. I'm going to go with the first one. The second one's definitely not the case. We're lazy and want to avoid having to implement automated evaluation metrics. Honestly, if I had to pick one for somebody to do, which was either create automated evaluation metrics or look at the results of the system that they've built and use it as a user would, I would vote for that one. That one is almost more important, and it's done a lot less often. There are so many times where I use an AI tool, and you guys might have had this experience as well, where you're like, there's no way anybody actually has used this because it just doesn't work. I wish more people would look at them before doing the automated evals. Because then when you do the automated evals, you actually know what to measure because you know what's working and what's all not working. Okay, so I'm off my high horse now. We are going to look at the golden data set. So a golden data set is just your data set of movies, but ones where you have spent a lot of time curating it to where you have real user questions and known correct answers. You might have had, for movies, you might have looked through them and like Googled and read or watched all the movies, something like that. If it's a legal data set, you may have hired an attorney or had an attorney look through and really study and come up with correct answers. But they're ones that you're pretty sure these are correct. You have the correct answer. You have a realistic question. It's representative. And it's very useful because then you can have consistent evaluation. You can automate your testing. You can have a baseline comparison between different models. You have a test. I kind of mentioned this. You really, really need a domain expert. This is one that I've seen a lot. If you're building a legal case study search engine, you need a lawyer or a legal expert. This is super important because there are a lot of legal AI startups where they may have someone, but the majority of the developers, the majority of the decisions, the prompts being written, how it's evaluated, how the user experience is built, are all decisions being made completely by developers. And there's a line where, is this a good response? You need to be able to say that, like, I can't test this. If I look at this result, I can say, hey, yeah, that legal response looks right. But that doesn't actually mean anything without a legal expert, somebody who knows what they're talking about. And so it's really important to get someone who is a domain expert. Sometimes it's easy. Sometimes for movies, you can become a domain expert very easily. For medical, for legal, for other domains, it can be very hard. It's helpful to learn a little bit if you're really diving in, but you need someone that knows enough to be confident in the correct matches. In practice, it's almost certainly not going to be perfect, and you're never going to score 100% on evaluations. If you see you have 100% accuracy, be suspicious. I've seen many cases. Sorry, I'm going on a lot of rants on this evaluation things. If you see that, you should be super suspicious because it means one of two things. Either you have some sort of bug in your evaluation set, or your data set's not representative of real world usage. The third option is your problem is a very easy problem to solve. It may be that it's not really commercially useful because anybody else could have done it too. Most commercially viable retrieval systems or LLM systems are not going to have perfect accuracy. They're not going to be. And if you do, you can probably build it another way or build it very easily. What I would caution against is seeing 100% accuracy and then jumping on social media to talk about how you have 100% accuracy, because that's happened several times and they usually just get dunked on. So here we go. Copy and paste the golden data set into our data, and then we'll run it. Okay, so what is this? So let's look at our golden data set. This is a very simple example, but the idea is we have a query and we have a relevant document. This is what we want to make sure is there. When we say talking teddy bear comedy, we want to make sure these are here. When we say children's animated bear adventure, these are the relevant documents. And so we can measure how well it does on movies. Superhero saves the world. Here's a bunch. Let's take it and put it into our data. Dataset.json. And this is just going to check and make sure it's there. So we'll just go ahead and submit. Great. All right, let's move on. Okay, so here we have metrics of precision. Precision is about how many are actually relevant. So if you return 10 movies, but only top 7 are relevant, your precision is 70%. Higher precision is less junk in the results. Okay, so this is pretty important because if you typically want the end of your system to evaluate for precision. Often, like, you want stage 1 for recall and stage 2 for precision. Now, there's some exceptions for that. Like in medical, often you prioritize recall higher, just because telling a patient that they're healthy if they're actually sick is like the kind of the worst case scenario. So you really go for recall, but precision is really important. And you can then measure precision at K, just typically what you do, where you can look at different checkpoints based on like how relevant are these top documents. And so, for example, you might say, I want really high precision at 3 because I want something, or at least 2 somethings in those top 3 must be relevant. And then maybe you say, hey, top 5 can be pretty good. Top 10, it's okay if that falls. Beyond that, I don't really care about precision. And so you can do precision at 3, precision at 5, precision at 10, things like that. And this will give you an automated test to run. And so it's super helpful for making sure your system is going to work as expected in production. So we're going to create this evaluation CLI.py script. CLI.py. So we've got that. We can see we've already got the limit. I'm going to create some things for us to in our library here so that we'll be able to create the actual logic. So let's see. So we load the data set. We need to do that. We could put this in the search utils, where we load the movies. We're not going to reuse and load the golden data set in lots of places outside of evaluation. So I think I'm just going to do it here. Import JSON. So from source utils, we can import our data path, and then we can open our data path / our golden data set.json. That's F. And we can say our test, what is it called in our golden data set? Let's take a look. Test cases. That's what that's called. Test cases is going to be equal to json.load of our file, and we can just index straight into our test cases. So we get the test cases as a list. We probably just don't want to load it all the time. So let's do a function for this, load test cases, and then we can just return our test cases. Okay, so we've got our data. We've got it loaded. For each test case, we need to run RRF search. Cool. So let's go ahead and import from our library.hybrid search, import our hybrid search class. So we can evaluate, which is what we want to do. We can get our test cases. So we've got all of those. Might want this limit here. We will actually need our movies because we are going to be searching that data set. So then we need our semantic search or our hybrid search. So then we need hybrid search. Let's go take a look at this class. What do I need? Okay, so it takes in documents. And then we can just use the RRF search directly. Okay, so it's taken our documents, and we can do our RRF search entirely. And we'll want to go for test case in test cases. So we're going to want to go through each one, run our RRF results, which is going to be equal to, so that's our test case is going to be, so let's say query is going to be our test case query. Let's double check that in our data query, and then relevant documents. Okay. Expected is test case relevant documents. So this is our query and this is our expected results. So from here, we're going to type in a query and we can go from there. We're going to default probably the K is equal to 60. That's what is, most common. We'll pass our limit through. Okay. Limit equals limit. All right. So before we get too much further, let's go look at our instructions. For each test, we're going to run the RRF search. The K parameter should be 60. Good. And top K should be this. I think that's a little confusing. This top case should be a limit, I think, but we'll work on that. Okay, we got it correct though. Based on the formula above, the percentage of titles in the results that are found in the golden data set. Calculate precision for each test case. Okay, and we can see is the precision or how many are relevant. Okay, print the results in this format. Precision, retrieved, relevant. Precision, retrieved, relevant. Okay, so let's go ahead and try this. Okay, so we've got this, got our results, we got our limit. So now we need to say, and if we look at our golden data set, looks like we've got titles. So for RRF result, in RRF results, see, so we have relevant count, and I can say, so the relevant count, we're going to add if RRF result title is in the expected results. We will add to that. So then we can say, just like our formula says here, we can say, how many were relevant out of the total we returned. And so we can say how many were relevant over the total returned, which should be the limit, and we can return that. Or we can say this is the precision. Okay, so let's see how we have to print it. K equals 6. So we're going to start with printing K equals the limit. And yeah, K is a hyperparameter in reciprocal rank fusion, but you also say precision at K or recall at K. So it's a little confusing that it's there, but that's how it's used. So that's what we'll do. And then we need the query, the precision at the limit, the retrieved, and the relevant. Okay, so let's go ahead and get these printed out. So we can print our query, and then we print precision at limit, colon, and we're going to put in our precision here. And then we can print retrieved, and we can put so let's get our retrieved here in a nice format. So retrieved equals RRF. So let's do R title for R in RRF results. And we can do space. We can join all those together. So this should be the retrieved. And then now I can print the relevant, which is our kind of expected case here. Boom, there, and there. Okay, so that seems to be what we need. I'm sure I'm missing something, but let's add this to the evaluation CLI, and then we'll give it a go. From lib.evaluation, import evaluate, and we can just do limit directly because we already got that. Okay, let's give this a shot and see how this goes. No module named search utils. I can actually just add this on here rather than having both import lines. See, let's look at our search utils. I see. So this is the data path. Oh, so I need to actually use the project root for this. So I need to go project root data. There we go. That was just going into movies/JSON/golden data set. So I thought that was a directory path, but it's really the path to the data set. Okay, so we've got K equals 3. That's good. We got the query. We have the precision. We have the retrieved. The relevance not quite in the right format, but I think we're in pretty good shape here. So let's just fix that one formatting issue. And we'll just do the same thing we did with the other. Join that together, and I think that should fix it. We should see, let's see, Dinosaur Park should be 333. Let's see if we get the right answer here. The evaluations can take some time because you're running, on lots of queries back to back. 1666. Okay, so I need to round to 4 decimal places, basically. Let's get that fixed. 4F. Let's try that again. Okay, great. I think we're in good shape. So I'm going to go ahead and stop this so we don't wait. And let's try giving it a run, seeing how we do. So this is pretty cool because now we can actually see how good our search is. And that's really kind of the first step to being able to improve it. You first get like a reasonable starting point, and then you're going to have evaluations. You're going to look, you're going to do the vibes checks. You're also going to have automated tests, and you'll keep kind of hill climbing to that. We passed, so this is perfect. We can move on to the next lesson. All right, recall. So we just did precision, was about of what we've returned, how many are relevant. So how much garbage do they have to sift through, the user have to sift through. Recall is looking at it from a different angle. All the relevant answers that are in the data set, how much have I shown to the user? How complete are the results? So I mentioned before, this is really important for, for medical. You want to make sure to include all relevant information about their health. In other cases, it's not as important. The cat picture analogy, if your goal is to retrieve cat pictures and you returned 10 cute cat pictures, but really there's 1,000 in your data set, it's not a big deal that you didn't include all of them. You included several of them. Precision matters, not so much recall. There's lots of examples of cases that are important. In fraud, for example, precision is very important. Recall is not necessarily as important in many cases. You don't want to accidentally accuse someone of fraud that didn't. I mean, it happens, but you'd rather be very sure that who you're flagging as fraudulent is fraudulent. If it's just a case where you're like, hey, I'm just going to freeze the card to be safe, you might care about recall. If it's like, we're going to shut down their account and fine them a huge amount of money and it's very harmful, then precision matters more. How much of what's relevant did you find? Relevant recall is a simple formula, which is relevant retrieved over total relevant. And so if you search for family-friendly bear movies, there might be 8 of them in the entire data set. Your search only returns 5. 4 are there. You can say, I retrieved 4 relevant ones out of the 8 total. You found half the relevant movies. Recall's about thoroughness. Pipeline performance is a big deal. We've seen how to create these where you can have 2 stages. You have, maybe it's a keyword search or a semantic search or a hybrid search as stage 1, and then you have a re-ranking step, which is much more accurate. If things fall off in stage 1 in the fast hybrid search step, then your re-ranker can't possibly fix it. When you have these 2-stage steps, pipelines, you want stage 1 to almost always be prioritizing recall. You have to get the relevant results in there so that the re-ranker can focus on precision, usually. And again, sometimes it's thoroughness. This thoroughness is super duper critical. Sometimes the precision is more important. Missing important information can have big consequences. Precision recall. Yes, higher recall often means lower precision. You can increase your recall by just returning more documents, even if that hurts precision. And so this is often a trade-off. You need to find the right balance for your use case. And this is often thought of or often treated as a technical question. But honestly, it's almost more of a product question. It's almost more of a product management question than a development question. And so my recommendation would be to kind of get familiar and think about how it could affect the user experience, and then maybe try and raise some of these questions with, whoever's responsible for that, because it has big impacts on the customer experience. Okay, so let's go. Update the evaluation script to also print recall at K, and we use the formula above, and we're just going to add recall in there. Okay, let's do this. So we're going to add recall in here. Recall at, I'm going to sell this recall. Okay, we've got the print statement done. Like, it's half the battle, right? I feel like there's 3 things for me to do. Print the results. I use the formula. We need the relevant retrieved over the total relevant. So how do we get the relevant retrieved? Well, we have the relevant retrieved here. So our recall is the relevant count divided by the total relevant. So that should be the length of our relevant documents. Let's check this out. Let's see if this works. It feels like it was too easy. But I'm on chapter 8. This is a marathon, so maybe I missed something. Okay, recall at 5 is 1. Cute British bear marmalade is 0.2. Recall is 1. Okay, so it might be okay. So I'm going to go ahead and try and submit. I'll just kill this so we don't have to wait for it. One thing that's really helpful when you're, actually building this and trying to get better at it, and you're trying to figure out, I think a lot of times people see a recall score. I know they see a low precision or low recall and they want to improve it. And so they're like, oh, well, let's try running our reciprocal rank fusion with a value of k, and we'll do like k equals 10, k equals 20, k equals 30, 40, 50, 60, 70, 80. Run a whole bunch of these ablation studies, and then pick the one with the highest metric, and then move on to the next. And then they just say like, oh, well, I'm going to try 5 different embedding models, and then we'll pick the one that's highest. That's a great way to overfit, which is not good. You want your system to make sense to you. So just like you would want to understand, failed step 2. Okay. Just like you would want to understand what all your code is doing, you want to understand what's going on with your model. Your failures in your precision and recall are almost like your stack trace. When you get a bug, you want to look at your stack trace, understand what the stack trace is saying, what the error is, use that to understand what the problem is to fix, rather than you get an error and you kind of start randomly fixing stuff. You want to understand what the problem is being caused so that you can correlate it. In the same way, if you're doing this and you say, okay, I retrieved, they won't believe me, that's marked as not relevant. So why did it retrieve this? Well, what would you do with this? Well, you'd go look at the movie description, look at the document, be like, is it even make sense? Is this like totally off base? Does it kind of make sense? Could I see it? Maybe it should be relevant. And you do this over and over and over again. And on the other side too, like, hey, this said it was relevant, but it wasn't retrieved. Why might it be? And if you keep looking at these, you start to notice patterns. And you start to notice like, oh, my pipeline doesn't seem to work for movies where it's the side character that is here. It's focusing too much on the main characters. Or, hey, it seems like it doesn't retrieve any of these movies, and they all have this weird formatting. I need to clean my data, or etc. And so by looking at them a lot, you start to notice patterns, and then you start coming up with ways to improve it. So now let's take a look. What failed? Failed step 2. So let's run step 2. 7143 was expected for car racing. Recall at 10, 7142. Okay, so let's think about this. What did we do wrong with our recall? And are the other ones? Okay, so we have, what do you have? So we go through, we get this relevant count. We go through here by seeing if the title in our relevant documents. So this is how many relevant we retrieved. Never mind. This is precision recall. And then we do the length of the limit of the experiments of how many are here. So how many were relevant? Let me see here. Okay, so what am I actually getting here? Is my recall actually correct? Car racing. Okay, so we have, how many relevant do we have? 1, 2, 3, 4, 5, 6, 7. So I have 7 that are relevant. How many are retrieved? 1, 2, 3, 4. Oh, how many are relevant that were retrieved? That's what I need. Okay, so I got 1. I know this is a little painful. Sorry. 2, 3, 4. So we received 4 out of the 7, and we said, what did we say? Recall is here. Okay, so yeah, that's not right. Okay, so what are these numbers? So let's print our relevant count and our length of our expected results and figure out which one was wrong. And then let's just make this quick. So if test case title is not equal to, let's do query, not equal to car racing. Let's just continue. So we'll just skip all those and let's just debug this one. Oh, right. I had this. Okay, so we have, what do we have here? So we have precision is here. So I feel like I'm just getting different results. Hot Wheels, highways, 35 world race. That's 1, 2, this is 3, 4. Okay, so I've got 4 out of 7. What would 5 out of 7 give me? That would give me 7143. Okay, so I think what's happening here is that I'm saying the Fast and the Furious is a match. This Fast and Furious is not a match, and this is being counted as a match. So I'm being a little bit too stringent here. Which one is right? I'm not sure, but let's match this. So if the result title, so if that's in there, if this, we could say, yeah, you know, I feel like this match is a little off. I'm not sure if they're getting a result different with the reciprocal rank fusion or here. So let's just test this out. So if we saw this in here, then I think we would pass. In this case that's clearly relevant. The Fast and the Furious, Need for Speed. All right, I'm gonna file a ticket for this. I think we might have a small little bug here. Well, we will get that fixed. Boom, this is how you file a bug. So we have 4 relevant retrieved out of 7 total relevant. I suspect that Fast and Furious should be is being counted. Cool, we'll get that fixed. All right, great. Okay, F1 score. So we got precision and recall. We talked about how those are often a trade-off. We talked about in some cases precision is better, in some cases recall is better, but in some cases you want some sort of balance. That's what the F1 score does. It balances them both when they're both equally important. You can think of it as doing an average, but it's a special average because we want to punish it from optimizing whichever one's easiest for this task. So for example, here, obviously if precision and recall are both 100%, the mean's 100%, the F1 score is 100%. If they match 50-50, they'll both be 50%. However, what you'll see here is if precision is very good, precision's a 90% precision, but recall is really suffering at 30% precision. A regular mean will split the difference and say you've got a 60%, but the F1 score, the harmonic mean, is going to say 45%. So it's punished because of the disparity between these two. So it's not just a true mean. You can see this again. You know, if you have 75-25 split, a regular mean would give you 50%, smack dab in the middle. The F1 score is going to be, you know, worse. And if you have 100% precision with 0 recall, which isn't really possible, but if you had that, you would see the F1 score would be 0 if one of these is 0. It forces you to improve. So in some cases, precision is more important. In some cases, recall is more. In many cases, they both are. And you want to optimize to a single metric. And what I would really think about, the best way to think about these is what is the harm in the kind of error? So what is the harm in a user having, so if you want to return 10 results to the user. Okay, so like how much harm if you return 6 results that are relevant versus 7 results? So you missed 1 result. Like what's the harm to the user? Or 6 to 4 relevant ones. What's the harm? Like, okay, they spend a little bit of time searching through stuff that's not relevant. Maybe it's, you know, garbage stuff. And part of this is like, maybe it's like not a big deal because they skim and they go relevant, nope, relevant. Okay, this one's relevant. Click on that. Nope. If that's all it is, it's probably okay. But sometimes when you return results, it's not immediately obvious whether it's relevant or not. And so you might say, okay, is this one relevant? And they might have to spend 15 or 20 minutes or 30 minutes reading a research paper or reading a document to know whether it's actually relevant or not. And then they might go to the second one and spend 20 or 30 minutes. And at that point, precision is less of it costs them 10 or 20 seconds and more of like it could cost them hours. What's the harm if your precision drops? This is the same thing on recall. Okay, so what if there are relevant results that aren't returned? In some cases, hey, you know, as long as I've got good precision, as long as I've got a few really good documents, I don't need every document. In many cases, that's the case. Like precision is more important. In some cases, if I'm saying, here are the symptoms, give me documents of diseases that are related to the symptoms, it can be a pretty big deal if it doesn't return documents related to those symptoms. So recall could be, what's the harm of precision? Well, the harm of precision is wasted doctor time because they have to read extra information and look through extra diagnoses that aren't relevant. What's the harm for bad recall? Well, it could be that the doctor doesn't consider a diagnosis that's relevant to the patient, tests for everything else, determines that the patient is healthy and doesn't have any diagnosis and sends a sick patient home, or a patient who has a disease home, telling them that they're healthy. That's a much bigger harm. So recall's super critical there. And there are cases where you want a balance of both, where there's not this extreme. So I think thinking about like what's the harm in each helps determine what's more important. Could be time. It could be more serious of a harm. It could be not a big deal at all. So we're going to update the evaluation script to also print F1 scores. So we're going to do print the F1 score, and we're going to add the F1 formula, which we see here. So let's jump over and let's find where we were. So we need precision, recall. Let's print our F1 score. And we have precision here. We calculated recall here. So we can calculate our F1 here. Let's make sure that we precision times recall, precision plus recall, F1 score. Okay, so we got all that. Okay, great. So then we'll see. We saw there was I think a little bit of a bug in the test for the last lesson. So this may, be a trickle down effect. We'll get that fixed. 2576691176. So we need to change this to use our precision. I'm going to unset one of my environment variables here to get rid of that warning. So these were all good. Let's take a look at this next. We're looking for friendship transformation magic. 2566673636. So I think we're going to pass. All right, great. Go ahead and submit, and then I think we'll be good. So now we've got a really good evaluation and a way to compare these. What would you do from here? Well, you can store all these so you can have a description of what your experiments are, maybe store them in a SQLite data or a Postgres database, or even a CSV file so you can look back at them later. Have this as a final check before you deploy, even if you're doing like very simple things. If we know our precision for this query should be 0.25, have a check so that when you deploy, did one of these drop significantly? Did you introduce a bug that subtly affects your retrieval performance? Okay, great. We're done with F1 score. We can move on. Okay, error analysis. This is super important. When a search fails, you want to figure out why. Metrics only tell you what is wrong, not why it's wrong. And you need to know why it's wrong in order to fix or improve your system. There are some things that are just really obvious that you should fix. I mean, there's a lot of parallels to regular programming for this, where if you have a bug, you want to figure out what the problem is and why. So you would look at a stack trace and you would understand, oh, the stack trace is saying there's some sort of casting thing. Here's the line of code that's failing. Let's go to this line of code. And you're really trying to understand like why it's breaking, because that helps you understand how to fix it. And this is the same thing. Your metric dropping or not being good is like a stack trace. It's like an error. It tells you, hey, this is wrong. Then you need to do the analysis. The error analysis is like your stack trace to figure out why it's wrong. You don't want to just kind of randomly fix things. There are some things that are obvious, just like if you're coding, if something breaks and you see, oh, like I have an extra comma here, you don't always need to read the stack trace to catch very simple things. Or if you just notice some sort of bug in your code, you don't always need a stack trace to fix things. Some things are obvious, but most things aren't. So debugging the pipeline. So say it doesn't match. So we have user searches bear movie. They expect the revenant Paddington, and it only returns the revenant and it misses Paddington. We then want to say we have a system. Where's the problem? Is it pre-processing step? Maybe we're trying to strip out punctuation or exclamation points, or maybe we're doing something and we're accidentally deleting part or not loading the description in properly, or something like that. Is it we're rewriting the query? Maybe we have a query writing step, and for whatever reason, Paddington gets rewritten in a way that excludes Paddington. Maybe bear movie gets rewritten to bear movie intense horror scary, and our prompt needs to be clear, not to change the intent or something like that. So we could have a bug in our query writing. It could be that the keyword search terms, there's no matches. If there's no matches, maybe we need to improve our query writing to do an expansion. So is it the keyword search that's ranking low, or maybe the semantic search is ranking very low for some reason, and we might need to look at embeddings or fine tuning? Maybe it's ranking low on both. Maybe all of this is great and it's getting to the re-ranker step, and then the re-ranker is filtering it out, and you want to focus on the re-ranker. And so you can see that even the super simplified example here, if you don't know, if all you know is, hey, I'm missing Paddington, which is what the metric shows. It shows like, hey, our recall is 50%. If that's all we know, what do we do to fix it? And if you don't go through this process to figure out where it's failing and why, then you're just going to be randomly trying to change stuff. And, you'll make some things better and some things worse. And sometimes you'll get lucky and you'll have progress. But you need to be able to diagnose where something is falling off in the process. You often need to keep digging deeper. Like, eventually you'll start seeing patterns. Is this too ambiguous? Does it return random bare content? If you get this, is it too specific? Meaning, can you see what types of queries users enter that causes low recall or low precision or low F1 score? Maybe if they put in a really long query, it fails. Maybe if it's really short queries, it fails. So what do you need to do? And sometimes the fix is retrieval, and sometimes it's we need to phrase our interface in a way so that users know how to enter. Kind of keep going through and really debug and think critically, not just about what the metric failing is, but see if you can figure out and have a guess about why. Error analysis in this way is also called data science. Might not be the most popular take, but that's what data science is. Is you've got a metric and you're going to look through the data and create a hypothesis for what the problem is. You can say, here's my hypothesis is that like, hey, every time they have long queries, I seem to get no results. Therefore, my guess is that my embedding model doesn't handle long queries very well. Is that true or not? I don't know. We can try. We can run an experiment to see if we can improve it by changing embedding models. But it's not like we're going to go, look through the actual weights of the model to look at it. We might read some papers and some results about it. We might try other models that are supposed to handle it better. But that's the idea. That's what data science is. Yeah, and then you run experiments. So you could say, hey, it seems like the long queries don't match. I can run an experiment. I say like, hey, let me take a bunch of short user queries and just like make them really long and wordy, but we think it should return the same thing. Or if I've got really long queries that are failing, let me take this 1980s animated family-friendly bear adventure movie. Can I shorten this? Can I say family-friendly 1980s bear? Do I get the same results or better results or worse results? Is it all these animated adventure and movie, like are these extra words causing issues? Or do they both fail? Yeah, just experiment around. Why is Land Before Time not in the top 5? So let's go ahead and we need to answer, why did this happen? Did it rank poorly on semantic search, so hybrid search filtered out? Was it poor on keyword search? Did it make it to the re-ranking and it was relevant, but it is not quite in the top 5? Was it irrelevant? So the first one I could say is dinosaur. Okay, land, let's pretend like I don't know anything. It clearly looks like it's relevant to dinosaurs. Okay, so it's not that it's not relevant. So we can already rule that one out. Let's try and start from the beginning and figure it out. So Jurassic Park. Yep, it's definitely not in there. One way we could test, so you can think about how to test. It made it to the re-ranking and it was relevant, but the re-ranker not put it in top 5. So one thing we could do is we could rerun this exact same query and change the limit and take a limit of 5 and say like, hey, is it in the top 10? That might tell us where the problem is, that it's relevant, but just not quite in the top. That's fine in some cases, but in our case, we have no observability whatsoever. And so I think it's better to say, let's create some sort of logging or tracking for this. And then eventually you'd create like a debug flag. Our query was reciprocal rank fusion with cross encoder. So let's go ahead and let's just start here. Let's see, we got a hybrid search. Okay, we can, let's do RF parser. Let's add an argument here. I'm just going to make this debug thing here. You can think about how you might like to define it. So let's type is equal to string and help is equal to a piece of a title to track, something like this. So what I'm going to do is I'm going to say like dash debug land before time or something. And I want to see what's happening throughout the process. You can also implement tracing so that everything gets logged to a database. That's another great thing to do, but we can start simple here. And then let's just pass args.debug. All right, let's jump to our logic here. This is what's being run. And we need, say, debug is none by default. So let's say if debug, print debugging for movie containing debug. So we're going to debug for whatever we put in here. What was that going to be? We're going to debug land before time 10. Great. So that's going to be our query, is going to be dash dash debug here. So we've got that. Debugging for this movie. Great. We did a hybrid search. So we can say, oh, that just initializes it. If we enhance, we can say enhanced query for there. We can already see that. There's nothing extra to print there. We also aren't doing it there because this will print on every query that's submitted. The reciprocal rank fusion limit. Okay, so we do a reciprocal rank fusion search. So we can say print if debug. Let's add another debug flag in here. Print hybrid search. Let's just say debug hybrid search position for debug, whatever that debug thing is, and what position do we have here? So we need to go through, enumerate through the results. So let's do this. So for R and enumerate through the results, let's get the index. If results title is equal to debug, then we will break. So it'll tell us what ranking this is at because it'll enumerate through the results. This should be already sorted is IDX. And so we can say, so if the results is title, let's say found equals true, and we can break out. So we can say the index location, if it's found, else we can say it was not found, something like that. So now we should be able to see that. Cool. And we can say after this, we have this results again. So let's do the same thing. We can put another debug flag in here to say here, re-ranking. Let's try that again. Okay. So let's rerun this. This won't quite tell us everything we'd like, but let's see. So we're debugging for the movie Land Before Time. List indices must be results title equals debug. So this should be R. That means this should be R as well. So let's try that again. Set that, reset that. Found equals false and equals false. We can set these. Oh, that's not where I wanted it. So what do we see here? So it says it didn't make it before Land Before Time. Okay, so I've either got a bug or we'll do it. We'll just assume I don't have a bug and we'll just keep going down here. And let's add a debug flag here. Let's pass it down. So we can say if debug, then we can go through the combined results here. For R in combined results, put this in a debug flag here. For R in combined results, R title is equal to the debug. We'll just print R. Okay. So let's try this again. R is in combined results. Okay, so we are not seeing it here. So that must be some sort of issue. So R.title. So what are we seeing for debug? Let's just say RRF debug equals debug. Make sure we're finding that. Let's see. Okay, so what are we doing here? We're saying it's not found at all. I don't believe that's the case. It could be that it's filtered out of the top 500. I don't think that's the case. Let's go ahead and print combined results. Let's just print one. Let's see what the format is that we're seeing. Maybe we're indexing in wrong. So we get doc ID, BM25 rank, semantic rank title. So let's say if there's a debug, which there should be because I have RRF debug here, Land Before Time, do dot lower equals debug dot lower. Let's just clean all this just in case there's an issue there. So we're finding it here. Let's see. Okay, so we have doc ID here. So let me filter that out. Okay, so now that's, never mind. That's not quite what I was looking for. Okay, let's make sure this movie is actually in our data while we're doing this. Land Before Time XI. The Land Before Time XI. Okay, so this is, so it's not actually equal. I see. So this is why it's good to look at your data because this is not the full title. So an equals would not work. So I need to do if the debug lower string is in the title, then I think we'll have better luck. Let's just run it to make sure, and then we can fix it in the other places as well. Okay, I'm going to get rid of this extra print statement because it's making things hard to read. So we want to print, that's actually, hang on a second. This is actually finding it. Okay, the Land Before Time 2. Okay, so let's print this out now. So we want to say print phase 1 search for the title. Let's do that. And we can say R BM25 rank, and then R semantic rank to print both of those out. I don't think I necessarily need the score. We're doing reciprocal rank fusion. If we see something super odd, then we might want to look at it. So we've got that printed. That should clean things up quite a bit. A phase 1 search for it. BM25, so it's rank 7 and rank 12. That's pretty good. So it's definitely making it to the next place. So now we can go back and update this debugging here with what we learned about this. So we need to say if debug dot, and we'll just make it easy to use the debug flag. Small typos don't make it. Okay, so that works. I believe that should work. Let's try this again. Rank 7, hybrid search before land before time is 7. So that's really good. Re-ranking for top priority results. Re-ranking post for land before time is 19. So it's still pretty relevant. It's just not in the top 5. And it's hard to argue. We have The Good Dinosaur, Dawn of the Dinosaurs, When Dinosaurs Ruled the Earth, Dino Croc, Jurassic Park. Like, I don't see these and think, wow, Land Before Time definitely should be better than these. These are all like, yeah, really, dinosaurs, the whole point of these movies. I would say Land Before Time is more, I guess, like a friendship kids movie, but happens to have dinosaurs. I don't know. It's very dinosaur based. But like I see these and these look okay. Like I don't think this is actually a problem that it's ranked low. I still see a high precision. These all look super relevant. So, okay, so great. I'm going to say it made it to ranking. It was relevant, but the ranking did not put it top 5. There we go. And now I have a debug flag to use and continue improving on. And that debug might adjust over time to store into a database instead of just printing it. But yeah, we've got a nice way to figure out what the problem is and look into our failures. All right, LLM evaluation. So in addition to metrics that can run in an automated way, we saw that we can manually evaluate by adding some of observability or logging and actually looking at results and tracing them through the system. And we can look at the results and look at search quality. I did that just a second ago when I was looking at, okay, Land Before Time isn't in the top 5. Why is it? And I looked at the top 5 and I was like, yeah, those seem better responses. So I evaluated the search quality and said it's fine that it's not top 5. That's slow. It can be very expensive, especially if you're in a domain like a medical domain or a legal domain. The way to evaluate them well would be to have a lawyer or a doctor actually looking through them. That's really hard to find. And so a lot of people use law students and medical students to help supplement the legal team that's doing this. So it can be slow and expensive. And if you need someone to evaluate some new system, handing it off to a lawyer and having them send it back a week later, that's not a great iteration cycle. So what can you do? Well, you can do an LLM evaluation, which is LLM as a judge. Essentially, you create a prompt, and your goal is to get this prompt to evaluate the quality of the results and match what a human expert would do as much as possible. This query here is a very, very simple one where it just says, rate how relevant each result is to the query. That's great. You would actually then start improving this over time. We're not going to get into like a full-blown evaluations thing, but you might start to say, put in, details such as users of this app are looking for kid-friendly. Maybe you have a streaming, maybe it's a movie data set and we're doing a Netflix, but for kids. And you might add some details about what does relevant even mean? What is a good result? If you're trying to generate a summarization at the end or something, like what is a good summarization? How many responses should be given? Defining it very, very clearly is helpful. Articulate your quality standards. And honestly, doing that is a huge, massive benefit to that. Domain experts are critical. The best thing is to have domain experts create this prompt. Like what is good to them? What is the lawyer or the medical person? If a user asks a question, should it default to providing things related to pathology or related to illnesses, or should it be defaulting and providing information related to just how the systems work in the body? Should it be doing a mixture of those? All these are things to consider that are kind of design choices. LLM judge is not as good as a human expert, so why use them? Speed and scale, basically. Cost and development speed. You can iterate and you can get lots of LLM as a judge iterations a lot faster than waiting for human experts. This does not replace human experts, but it does give you a way to get something almost as good while being able to give yourself a sanity check as you go. So Start with experts, create the detailed prompts, validate on the samples, and then you check to see if the LLM agreed with the experts. And then you handle it for bulk evaluation, but you still have human experts, reviewing any surprising scores or just spot checking other things. So we're going to add an optional evaluate flag to our RRF search. And if the flag is provided, we're going to use an LLM to evaluate the results. So let's go ahead and add the evaluate flag. Boom. Can run the LLM as a judge on the results here. Let's do args.evaluate. If the flag is provided after running our reciprocal rank fusion and printing the results, it should score from 0 and 3. So we've got this prompt here. Let's put it in our prompts here. Great. It needs a query, and we're going to need the formatted results. All right. We can put this under our evaluation, I believe. So let's put this under our LLM since that's what it is. So this generates content by putting in, let's see if we can make this a little bit better. We can do a ** args, and this will just pass in. We can pass in any extra stuff into this generate content, and it will pass it prompt into the, put it into the prompt. So that just makes it a little more flexible. Not sure we even need these. This could be a match statement somewhere, but that's fine. Okay, LLM judge, and we have the query. And this is, what is this going to do? It's going to put the query into the prompt, but we also need something else. Expand query, augment the prompt with the query. This is reading here. Yeah, so we need to call our generate. I'm not going to use this augment prompt. I'm just going to use the generate prompt directly, generate content directly. Let's open the prompt path, and we're going to have LLM judge here. Read that, and this is going to take the prompt query, and then there's one other thing that needed to go in, and this is the formatted results, and so then we can return that. Okay, so let's add that into our reciprocal rank fusion. Augment prompt, and we're going to add LLM as judge. Oh, I don't even think any of these are needed. I already did that, so I think those are all old. Cool. So we have our LLM judge imported here, and what we need after we've printed these results. See, just give us guidance. How does it need it printed? Scale 1 to 3, do not get 1 to 3, return only scores. We're going to need to parse the JSON and match it up to each corresponding, and then put it at the end. Okay. So we need to do, we actually need, this is the results of it, and we need to parse it, json.loads results.text. And we did this in another place. I think it was for the LLM pre-processing or query writing thing. Not query writing. I forget what it was. What did we do that for? For the re-ranking. I see. Yeah. Okay. So we load this. Then we want to return the results, I think. So this should be a list. So now we wanted it printed. How do we want it printed? Right here at the end. Print a final evaluation. Okay, so this is the final evaluation at the end. So I'm going to go ahead and put it instead of not in the loop. I'm just going to loop through this again and say if there's evaluate, not in the weighted search though, in the RRF search. This function's getting a little big. If evaluate, we can go through and enumerate through here, but we can also add in our LLM judge, which is going to put in our query and our formatted results. Where are our formatted results here? So if evaluate formatted results is going to be a list. Let's just do this. We can say if evaluate formatted list results.append. We'll add to this. And what are we going to add? We're going to say result ID is equal to IDX. And then we can put our title and our description, and we can close out the result tag there. And I'm just going to truncate to 100. I think the model will be okay. I don't want to use that many tokens up, and it'll make it run faster so that we can make sure it's working before running on the full thing. So we're going to append all that, and then our formatted results, we can break on new line to join together our formatted results. And so then we can do a final loop to print out all of our evaluations here. I already started that down here. Sorry. We print out our index. We print out the title. We print out the LLM results.index for our IDX. Then we're going to do that over 3. Okay. Let's start here, and I'm sure there's going to be some sort of bug. Expected one argument. If evaluate, at the very least, I don't think this is the bug it's complaining about. but it is a bug. So let's fix it. Okay, dash dash evaluate expected at least one argument. So what it's complaining about here is I didn't do this right. So let's take a look and see what we can do better. Add argument. Yeah, let's look at the definition for this. So we're going to add the argument. No positional arguments are applied. The base class, typically actions are selected, must be things like store true or pinned cost to the action argument. However, for greater customization, so let's do this. So then I think we need to say the action is store true. Cool. I think this should work. Generate content takes 2 positional arguments, but 3 were given. This should be an R. We don't need that anymore. Generate content. So here I said star star args. I should have done star star quargs. These are actually going to have to be keyword arguments. And so let's fix that. In this case, formatted results equals formatted results. Okay, so JSON.loads, result.text, string object has no attribute text. So this is already a string. Why is that already a string? Because I'm returning response.text already. Okay, so I already did that, so I don't need that. LLM results, index X is not in list. Interesting. So what is in the list? Let's find out. Okay, yeah, this is different. I see. So when I look at this prompt, that was a dumb mistake here. I just said put them in order and do highly relevant. So this in the re-ranking, I was thinking back to the re-ranker for some reason. We had it put the index locations of the particular ones. In this case, we're just saying keep them in order. And so I overcomplicated it. So what we really need to do is we don't need to do any of this. We just need to say LLM results index over 3, I think. Let's give that a shot. List index. Oh, list index out of range. So 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 1, 2. Oh, I see. As I'm starting at 1. So I actually need to do this. Well, I can actually say, instead of starting at 1, I want it to start at 0. So I can do that. All right, one more bug down. Off by 1 errors. They're my favorite. Okay, so I've got all this. I've got this. I searched for, what did I search for? I searched for family movie about bears in the woods, Bugs Bunny, Berenstain Bears, Care Bears. These are all somewhat relevant. Monster in the Woods was rated as not relevant. I mean, that feels right. That feels right. Okay, so we've got an LLM as a judge, and maybe we agree or maybe we don't, but we want to improve them. So let's say highly relevant. Use this if it seems likely user would enjoy the movie based on query. Not relevant. Use this if has nothing to do with the query. Okay, let's see if we get slightly different results now. Bugs Bunny and the 3 Bears. So why don't we try this? I don't even know if Bugs Bunny and the 3 Bears is in the woods at all. So let's go into our LLM. We did truncate it earlier. So let's go ahead and untruncate. Pretty sure we truncated somewhere. Yeah, here we are. If we don't truncate, I wonder if we get the same results or different results. Okay, we got slightly different results. Paddington scored very highly. Okay, so this is our LLM as a judge, and we can kind of keep tweaking to say if we really think might want to look at this movie and say, hey, is this in the woods? Is it actually relevant? It's not really about. Is it about the bears, the Bugs Bunny? Like, do we want this? We might want to think about why the model might be not thinking it's relevant and include it, or maybe only a 1 out of 3 is relevant, and these are actually, results that we'd better want. So we'd want to think through that. Okay, so we have that. We should submit. Okay, very nice. We passed. We can go on to the next lesson. Ooh, new challenge available, designing chunking strategy. I'm doing it. I accept the challenge. Okay, you're building a semantic search system over long documents. The key building blocks you're allowed to assume: chunking, splitting long documents into smaller pieces, query embeddings, numeric vector representations, vector databases, databases that store embeddings and support similarity searches. Some things to think about but are not required to mention: how chunk size and overlap, whether chunks should follow natural boardings, how chunking might impact both recall and precision. You don't need to write code. Focus on the reasoning behind your chunking strategy and impact retrieval quality. Imagine you're designing a system where users search lists very long technical documents using query embeddings stored in a vector database. How would you choose and justify a chunking strategy for splitting the documents so that you have the most relevant chunks are returned for a typical natural language query? Well, I'm going to just say what I would do. So the first thing I would start with is a very simple, word-based or character-based chunking strategy, just to make sure that when I run it, I don't get an error and I'm successfully parsing and I'm getting some results. From there, I would look at some of the results and start coming up and figuring out why I'm not getting the results that I'd like, and that would tell me if chunking is the problem or something else. For these technical documents, what's likely going to be a good strategy is some sort of chunking based on the semantics of the document. Could be sentences, more likely paragraphs, and that would make sure that users get complete chunks and the paragraphs have complete thoughts of these technical concepts to a query. Now from there, I would want some amount of overlap. And so I want to play with that. Something like 30% overlap is a good starting point. And the reason for this is that there's information that comes before builds is important to what I'm talking about now. If you took my current sentence and you discarded everything that came before, you'd have no idea what I was talking about. Same idea with this technical content. You'd want a little bit of the prior context so you can understand what the core idea is, have that overlapping context. A lot of embedding models are good up to like 1,000 or 2,000 tokens. And so I'd have to be conscious of how big those are and look for edge cases such as sentences or paragraphs that are, massively long, and make sure it fits in the, size of the embedding queries. And really search for edge cases such as page numbers and headers and footers and things I don't want embedded. Then I would do more evaluation, and if that still isn't sufficient, then I would consider more complicated approaches such as late chunking or like a multi-vector cold-better approach. Okay, let's see if it liked it. Keep going. All right. You're thinking along lines starting simple, validating, and iterating. Exactly constraint-aware design. I call overlap how I think about trade-offs of chunk size itself in terms of what happens when chunks are too small or large. Okay, I need to spell that out more. How would you describe the effect on retrieval when chunks are made significantly smaller versus larger, purely in terms of the chunks to the vector search record current? Okay, a good way to think about trade-offs is to start thinking about the extremes. So if a chunk is too small, there's not relevant context to know what it's related to. A single sentence isn't enough information often to know the topic. And so you're going to get pretty bad recall and precision when you have not enough context and super, super small chunks. So you want complete thoughts and complete ideas inside the chunk, completely self-contained in the chunk when possible. Not always possible, but you want a complete thought and the complete idea inside the chunk. So the query can be matched up to a coherent thought. So you want the chunks as big as possible because that's going to give it all the complete relevant information in the document. However, embedding models have this limitation where if your chunk is too big, then it starts to kind of average out the concepts, it dilutes the meaning, it cannot accurately encode all the information there. And so you want nice, large-sized chunks that fit well within the context limit of embedding models, which again is often 1,500 or 2,000 tokens. Did it like it or not? I passed. Great. I liked that challenge. That was awesome. I really enjoyed that. Okay. Oh, I have more interviews. I could just keep going with this. Imagine you have a large collection of documents. How would you use these embeddings to rank documents, and what properties of cosine similarity make it reasonable? Okay, this will be the last challenge I do. Otherwise, I would completely derail this. So when I have these fixed size embedding vectors, I'm going to calculate a cosine similarity between the query embedding and the embedding for all documents that are in my stash, and then I'm going to sort them based on that similarity. Cosine similarity makes it a reasonable choice here because cosine similarity is looking at the difference in the angle between queries, and that's important because the model that we're using is trained to say a low cosine similarity or very high cosine similarity means the words are semantically similar. So the model is trained based on cosine similarity to say when these documents are close together, according to cosine similarity, then they have a semantic meaning. They mean the same thing. All right, good. I also liked that. These are awesome. Okay, I'm going to go back. And we'll continue our course. Okay, so we got done with our evaluations, and so now we're going to move on to augmented generation. So we've done retrieval. We've used LLMs to, help improve our retrieval results. We've done hybrid search, reciprocal rank fusion, chunking. Now we're going to feed it into an LLM to make it even better. Now, there's often a lot of talk about retrieval in influencer hype circles, and sometimes people say that RAG is dead. It's nonsense. All retrieval means, augmented generation means, you're going to retrieve relevant documents using some sort of search. It can be a semantic vector search. It can be an agentic search. It could be a SQL lookup. It could be grep. There's all kinds of ways to retrieve documents, but the idea is you're going to retrieve some sort of relevant documents. We're going to augment the LLM's context with those documents, put it into the prompt or the system prompt, and then you're going to generate responses based on the retrieved information. That's all it means. This gives us kind of the best of both worlds. We get accurate information from our search and a natural language response from LLMs. So this is, super critical. Context windows are getting bigger and bigger. However, the usable context window, when context windows get too large in LLMs, they start to degrade. Gemini has like a 2 million token context window, but in reality, if you get anywhere close to that, you see a much worse performance. This retrieval becomes important because you can't fit everything on the internet or every part of human knowledge into a prompt, and you're always going to have some private information, private code bases, information about the particular users that can help improve the experience. 100% of documents ever passed as input to context LLMs were retrieved to document and augment generation. This was a meme that a guy named Ben Clavier, who's a retrieval researcher, made. Yeah, it's completely true. Anytime you hear an LLM getting the right context, we're talking about RAG. So this RAG pipeline is the user enters a query, the search system retrieves relevant documents. That's what we've been working on. The LLM is going to process the query and the retrieved documents together and then do something. Maybe we're going to summarize. Maybe we're going to answer a question. Maybe we're going to take another step. We're going to do something with that information. Maybe we're going to do more searching. And then the generated response is returned to the user. So let's start and let's implement a RAG pipeline. So we're going to create a new CLI script. Here's the boilerplate to start with. And then we're going to have this RAG command. So we can see there's a RAG command here where we're going to do some RAG stuff. And then, so let's get the boilerplate done, and then we can focus on the next step. I'm going to just close all these files. I forget already what it was supposed to be called. Augmented Generation CLI. It's supposed to be in the CLI directory, so move it there. Oh, it is there? Great. Cool. Okay, so we've got the boilerplate there. Check. I'm going to need to load movies. Prompt the Gemini API with the query. Here's a prompt to use. I'm going to put this in our prompts. So this is our like a question answering. So we'll just say answer question .md. This is going to take in query and docs. Okay. Print the results and the generated answer in this format. So we need to do RRF search and then for the top 5 results, and then run this and then print in a particular format. Okay, so let's go ahead. We can look at our LLM.py. We could put a different thing. I feel like this, this is still LLM stuff, and it's very small. It's not like we have a ton of logic going on here. So let's go ahead and just add on here. So let's do answer question, and we need query and documents. So the query is the user query, and the documents are what we retrieved. And this is called answer question.md. And so we can then format this prompt.format, and we can say query equals query, document equals document. Okay, so these are going to be a list of documents. So we might want to do something else there, but let's start there. And we then need to generate the content. But the generate content, does that already do the formatting for me? Yes, it already does. So I actually don't need to do this again. I can just generate the content to get my results. And then I think I can just return the results. Okay, great. So print the results in this format. Okay, so we need to do this. Great. Okay, so now let's make a file for RAG, where what we're going to do is we're going to, from our lib.llm module, we're going to import our answer question. Clearly, I've got a typo there. Let's just fix that before that throws me off. From our hybrid search, we're going to import our hybrid search. From our search utils, we're going to import our load movies. And now we can say answer question. We can create a RAG functionality here. Let's see what this format we need is. We say RAG movies about dinosaurs here. Okay, so let's just maybe do a general RAG function that's going to take in the query. It's going to take in a type. So let's say, let's do a case on the type, or a match on the type, because I think we're going to have more. And if we have, what do we have here? Case rag, do rag stuff. Let me just take a quick peek ahead so I can see kind of what we're building to. Summarize. Oh, okay, so we don't need to build it all into one command. So I'm a little bit off base here. So let's just do rag. We don't need this type. It'll basically be the same thing. We will need to load our movies. We will need to initialize our hybrid search. I don't remember if this needs, okay, it takes in documents directly. Okay, so let's do that, movies. And then we need to do a reciprocal rank fusion search, and we'll pass in the query. I think it said limit is 5, and later we can pass in the debug flag if we'd like to, add that capability to track things. So we created the new CLI script. We load the movies, do an RF search for the top 5 results, prompt the Gemini API. We could also add re-ranking, but we'll leave it just as is. Prompt the Gemini API with the query and the search results. Okay, so then I need to do my answer question for my RF results, and then I can say RAG results. So I can answer questions with the query and the RRF results. Yeah, then we can do the printing stuff that we need to do here. So search results and RAG response. Okay, so search results just does the titles, so that should be pretty straightforward. We'll say for result and RRF results. We're going to print looks like the title, res title, and we need to print search results. Then we print these titles, and then we need to print the RAG response, print RAG response. So then we just print RAG results. Okay, so let's see how this works. We can go over to our augmented generation for our query. Oops. So we're doing some RAG stuff. Okay. You can say from lib.rag import rag. That's a little confusing, but that's, so be it. Okay. I think I might be missing something, but let's run it and see what happens. This is pretty cool. So we kind of got the whole pipeline set. Missing one required argument, k. Okay. We'll set that to what our default value has been. That's just 60. Good default. Generate content missing one positional argument. Prompt. Need to pass that in. Okay, great. Let's try again. All right, key error, docs. Boom, args doc. So we called the rag in our CLI script. That went to answer the question, which generated the content, which formatted this prompt. Prompt.format. Okay, so let's take a look at what this is. Answer question needs query and docs. And what are we passing in? We're getting query and, okay, there we go. I think that'll be better. Make sure I did this. Yeah, I did that in the right function. So we got the search results. That's good. Let's see what search results were being expected. Expecting Jurassic Park. We got Jurassic Park. Okay, let's read our RAG response so we can get an idea of if it's good or not. Movies about action dinosaurs. Okay, based on the documents, here are some action-packed movies featuring dinosaurs that you might enjoy on Hoopla. Jurassic Park, a classic. Okay, so this is sounding pretty good. A theme park filled with cloned dinosaurs that goes horribly wrong when the power grid fails, unleashing the prehistoric creatures. A sound of thunder. Time travel allows people to hunt dinosaurs, but when someone steps on a butterfly, the future is drastically altered. You know, it's interesting. You can take out dinosaurs, but no impact. But the butterfly, that's where the future is altered. Okay, the good dinosaur. So this seems pretty good. Great. So we have real full RAG. I think we're in good shape. So let's go ahead and try and submit. All right, we passed. This is really good. Okay, we'll move on to the next. Okay, great. So we did the first rag, we're answering a question. Now we've got LLM summarization. Sometimes we just want a summary of the results rather than an answer. Google's AI overview at the top of each search results is happening, but a good summary depends on the needs and the context. So you can summarize movies in lots of ways. So you could summarize focusing on the family-friendly content if it's a parent, if you're summarizing it to a college student or a math professor, you're going to summarize things in different ways. How concise versus verbose should your summary be? Yeah, what are the things? Should you focus on the details of what happens in the plot, or should you focus on the overarching storyline? You could focus on like a lot of the details of what happened between two friends, or you could say, hey, this is a story of friendship where they develop through trials and tribulations, and leave it at that. It requires a lot of taste to summarize. What you want in RAG often is you want to put multiple documents in to summarize multiple documents. So this can be for movies. Hey, summarize what's going on with all of these results. It could be that sometimes your multiple documents have conflicting information. Maybe you've got like a legal use case and you're like, hey, take a look at all these contracts. And it's like, hey, there's conflicts in these contracts. Or, hey, I retrieved everything related to expenses for a particular person. Hey, the expense and the receipts don't match up. And so being able to summarize across them is great. And documents often have biased perspectives. So say you look up news articles for what happened about a particular event. You often want to pull in multiple things because there's going to be bias to them. We're going to be able to return results and then a summary. And this summary is going to say, hey, here's Paddington. It's perfect for young children. What it is, Disney's Brother Bear provides beautiful animations and meaningful life lessons. Jungle Book features Level Baloo with catchy songs. We Bear Bears brings a modern cartoon series format. They're all G or PG with positive messages. And so this is great. And so maybe, you're a kid and you're like, oh, which one do I want? Well, Jungle Book features catchy songs. I don't want to listen to catchy songs for the next 6 years. So let's skip that one, whatever. It lets people, understand the idea much quicker than reading all the retrieved documents. So let's do it. We're going to add a summarize command to the CLI. It should accept query and limit that defaults to 5. We're going to load the movies, do a reciprocal rank fusion search, do the API. Okay, let's do it. So let's just start. Let's get this into our prompt repository, which is just a folder, but that makes us sound a lot fancier if we say prompt repository. So let's go with it. And we are sophisticated RAG AI engineers now. Okay, great. So we've got this information dense and concise with several pieces of information. So let's go. Let's create a function now for summarize documents. So this still needs query and documents. And honestly, we pretty much just need to do the exact same thing. So we could refactor this to remove some duplication here. Let's just do that quickly. So we're going to say query, documents, prompt, file path. Let's just put this over here. Let's not file path. Let's do file name because we got the prompt path already. Read it, generate content, query, documents, return the results. Okay, so this can then just do return the RAG, and it can just pass in query documents with the particular prompt here. Make sure the summarize document prompt calls it query and results. So I'm just going to call this docs just so it's consistent with this one. Makes me refactor a little bit. Then this one can just go query here, and we can call this summarization. So you can see it's basically the same thing. All right, let's go into our RAG here. We're going to import this. We created this RAG function. I'm going to call this question answering. I'm going to call this document summarization. And pretty much, again, we need pretty much all this stuff. And the only difference here is going to be this, I believe. Let's make sure the printing, the expected output matches. Search results LLM summary. So this will be LLM summary. And this is, again, you've seen how much duplication there is. So this is, again, something that you can choose to come up with a good way to refactor it if you'd like. Got this, we've got here. It said a limit default, but we want it as an argument, so we'll go ahead and do that. We'll want to pass this through. And we might as well. Hybrid search, let's see. Okay, this one doesn't have a limit, but the other does. So you could think about enhancing this one. Maybe we don't need it. 5 might be enough. Okay, so we're going to pass this through. Search results. We still print that out. We still do this. Okay, so let's go ahead and let's import our documentation summarization. And we're going to fix the name to be a little bit more clear because all of these are RAG. We're going to add a new parser, which is going to be QA parser. And this will be the summarization parser. And I believe it's going to be called summarize. Okay. And we're going to add query and a limit, which is going to be an int. And this is going to be search and summarize. And this is going to be search query for reg. And then the docs to be summarized. The doc count to summarize. Okay. So that's great. So now we can just do our doc summarization in here. Summarize. Cool. Boom, args.query, and then args.summarize. Args.limit. Apologize. Okay. I think that's what we need. So let's go ahead and we'll just try and run the test case. Movies about action and dinosaurs. Okay. None type and int. Okay. So args.limit. So we need the default here to be 5. Give it a default value. Okay, let's see what results we got. So we said movies about actions and dinosaurs. We wanted Jurassic Park. That is there. Looking for movies with both action dinosaurs on Hoopla? Here are a few titles you might enjoy. A Sound of Thunder. This movie features time traveling. Jurassic Park, a classic film where cloned dinosaurs escape containment. This film was about dinosaurs as a human. They go on a journey. I don't know how to pronounce that. Something like Monster and terrorizes local search community. Okay, so this is pretty cool. So we've got summarization. Let's go ahead and submit. All right, we passed. So we can go on to the next lesson. Conflict resolution and summaries. Sometimes documents disagree, especially if we're searching user generated. So we can think about if we're instead of searching for movies, we're searching for movie reviews. We might want to give a balanced view. If we're searching for, recent events and we're looking for what happened recently in the news or on social media or in legal cases, we often want to know how they disagree. Now, for movies, it doesn't quite make sense in the use case that we're doing because we're not looking to say like, hey, does Land Before Time disagree with Jurassic Park? Like they're different movies and they're made up. That's not actually a conflict. And so we can look for factual conflicts. We can look for differences of opinions. So as we can review masterpiece of cinema versus overrated and boring. We can say, hey, maybe they're not directly conflicting, but they say the main focus is on different things. You can do the same process of using an LLM. You pass in our RAG pipeline, the query, all the documents, and you have a separate prompt in asking it to find these detection. And that's great. So which types of documents would least benefit from conflict resolution? Social posts remarking on a new Apple product. There'd probably be, lots of differences there. Reviews for Amazon products. That might be a good one. News articles from different sources about a recent crisis. That's great. Books in a library. I think it could all be used for them. But I'm going to go for the books in a library. That would be the least. And the reason is, it could be helpful if you've got 2 textbooks, you're checking out a couple of textbooks, or you're checking out some nonfiction books like the biographies of a particular person, and you want to know, hey, do these biographies have places where they disagree? But in general, if you're just saying random books in the library, it doesn't quite make sense. So that's the answer. We've got lesson 4, adding citations. Sometimes you just want a simple answer. If, I don't always need the most factually correct thing. If I say, hey, let me know which of these is good to use, and I don't know. Sometimes I really want a really great answer, and sometimes I'm like, what library is best in Python for plotting? A lot of times I don't really care if I'm doing an ad hoc thing. I just want some reasonable starting point to pick, and I just don't want to do the search myself. And that's okay. Might just say like, hey, Matplotlib is best. So I'm like, cool, I'll use that. If it was central to my product, I would want something more robust. I might want it to say, hey, Seaborn is the best. The reason for this is that Matplotlib has a new object-oriented API that they've been focusing on for the last few years, but it hasn't gotten adoption, and so the old API is there. It's hard to find, your searches are always going to find information about the old one, and there's this conflict there with Seaborn. It's a more modern, it does this. Here's a link to their object-oriented API for Matplotlib and how that's used in Seaborn, and the graphs are better. Here's a link to this blog post about, trying to make good visuals in Matplotlib, and here's one for Seaborn. You can see the Seaborn does a lot more out of the box, whatever, and have actual citations for me to go and dig further. And so if I was building something robust, I might like that. Yeah, so you just want these citations so people can verify claims, they can bump to sources, they can do attribution. Perplexity is well known for this. If you go to Perplexity, you can say, I don't know, let's just keep going with this silly example. What's the best Python plotting library? We can see here that we have citations. I can read this, I can get this. This is very nice. Here's related. I can say, for most people, a combination of Matplotlib, Seaborn, and Plotly covers most needs. So these are general, for general purpose, customizable, most widely used and underpins many other libraries. This sits on top and gives high-level functions. Maybe I would want to look at that. Okay, this is great. I can kind of see, here's Matplotlib. Oh, here's Seaborn. That does look nicer. Hard to compare because they're just completely different graphs. Plot9 for ggplot2. That's based on the grammar graphics, which is super cool. Yeah, so you can kind of look through. So this is really helpful to be able to go through, which is best, And you can do that for all kinds of stuff, Maybe I just want to say, let's not go into politics here. I don't know what this is about. Cool, so you can see here, and I can get a new AI-enabled missile defense system. I can actually go through and read through some of these. What's the role of AI? Okay, I could see the source. Let's look at the most authoritative one, Reddit. So that's pretty cool, right? So we want to have that. The simplest approach is to have the LLM keep track of the sources during summarization to kind of use this formatting. It's very familiar with Markdown formatting, so you can have it do these in line. Another common approach is rather than do this with citations at the bottom, like we do here, like instead of doing 1, 2, etc., and then put them at the bottom or something, is just have it use the Markdown links directly, put like IDs, and just use pure Markdown. Because then if you're rendering it for, a web app or in your terminal, you can parse the Markdown and format it however you want. But this is a really great approach. So let's go ahead and do it. Attribution, plagiarism issues, great. So let's go ahead and implement this. I should probably read what I'm supposed to do. So let's add a new command. It should accept a require query and limit. Citations command. Okay, here's our prompt. Let's add that into our prompts. Answer with citations. .md, that seems reasonable. Query documents, we'll keep this as docs just so it's consistent with the others. Okay, great. So we have, oh, I had a bug here. Okay, well, that's fine. Okay, fixed now. Summarize documents, we can say docs, citations, documents or something. And we're really doing the same thing. And we're doing answer with citations.md. So we can bring this in here. We can use this to create a new function. So we can say doc citations. We load the movies, search, reciprocal rank fusion search. We go through, we get these citations. Let's look at the print. We'll have this LLM answer. Search from the API. Okay, that's great. I'm gonna take a chance and I'll just YOLO submit. Shouldn't have taken the chance. Okay. Invalid choice. Oh, because I didn't even add it to the CLI. Okay. All right, let's do this. CLI. So we need to add a new parser. So let's call it for citations parser. Search query for rag. Dot count to summarize with citations. Form rag. Search and summarize and citate. I don't know if that's how you use that word. And we need to add a case statement down here to do our citation documents function with our args query and our args limit. Okay, so let's try that again. Okay, so this is a lesson. When you start getting on a roll, don't just YOLO submit. Expected it to contain here. It did not contain that. So let's just look at this function here. What are we doing here? Action movies with lasers. Pew, pew. Make sure to read the instructions while I'm waiting. Limit default to 5. Yes. Okay, so we got all that right. So it's not printing anything. We have the citations documents. So let's go to the definition of this. How did that even? Oh, because I don't have it under. Oh, yeah. Okay, so I had the wrong function here. So if I really wanted to be safe, I could define a dunder all. Doc summarization, doc citations. So that gives us a little bit more safety here. Let's try this again. Okay, we got the eliminators based on the documents. Here's some information, and I can see these reference particular documents that were in there. So this is great. And then we can tie those up to what was passed into the function to do anything we'd like. All right, great. So I think we're good to actually submit now. We'll see if we pass. All right, this is great. Okay, next up is question answering. So this is similar to all the others where we're kind of passing in the documents with a slightly different prompt. It's very different. It's very similar to summarization. You can almost think of question answering as a summarization with a specific intent. Different questions might have different things. Do you want direct answer, a comparison, a subjective reasoning? So we can look at this. Answer the following questions based on the provided documents. Answer questions directly and concisely. Use only information from the documents. If it's not in the documents, say you don't have enough information. It may or may not listen to this, but this helps. Cite sources when possible. Factual questions, provide a direct answer. Analytical questions, compare and contrast. And so you can see that it's starting to get specific a little bit on how we want it to answer. And that's very important. So let's add this in. Answer question. I guess we already had one. Detailed. And let's go ahead and do this. We will call this docs for consistency again. All right, let's go through the pieces that we need to do. So first we need to create some sort of detailed question answering where we get our answer question detailed prompt, answer question detailed prompt, and inject all that. We can then use that to create another RAG function, answer detailed question. This we can, what do we do here? So we can import this as well. We can call this here. We can fix this so we have the right answer. Instead of LLM answer, it's just answer this time. Okay, and we need to add this to our dunder all so we can import it. Import it here. We can then add it to our CLI with case of whatever we want to call this, which is question. Okay, so if there's a question, we can answer it. All right, so I've learned my lesson. Let's just try. Who are the main characters in Jurassic Park? Choose from RAG summarize. Okay. So here we need to add a new parser for this. So let's just call this the question parser. We still want a search query. We still want doc count to answer questions with, and search and answer and citate. And this is just going to be called, I think it was question. Okay, let's try this again. Who are the main characters in Jurassic Park? John Hammond, Ian Malcolm, Dr. Alan Grant. Very good. And it gave us which doc ID was responsible for that. So this is great. So now we have a citation. It pulled all these in and it answered the question based on the relevant movies. And one of the relevant ones was Jurassic Park. So perfect. This is great. I think that is all for our augmented generation, and we can move on to the next chapter. All right, chapter 11 is about agentic search and agentic RAG. What we've been doing is considered, vector search. And so we've been doing a keyword search and we've been doing a semantic search. So those are considered sparse and dense vector searches. Another approach to doing this is doing it with agentic search. And it's often very useful. It's very slow. And typically, the best approach is to have your agent also have a semantic search tool as one of its tools, as one of its ways it can search. And so this is not an either or. Vector search kind of fell out of style for code specifically, but it's been coming back. So cursor is announced just in the last few weeks that it's doing a semantic search tool as well. Parallel.ai has made a coding semantic search tool. Mixed-Red has come out with mgrep, which is a really powerful semantic search tool. There's sgrep and osgrep, which are also kind of based on that mgrep approach of doing semantic search, but is more of a local approach. And so these tools for semantic search are popping up a lot. So what's the difference between recursive RAG and normal RAG? Let's go ahead and answer. Normal RAG is typically a vector search. And what that means is that you are doing a similarity comparison to pull the results from retrieval, and then you would pass it to an LLM for augmented generation. In recursive RAG, it's like an agentic RAG system where it can do a search, it looks at a document or multiple documents, and based on that search, it can do another search. And it can kind of keep looking based on what it finds and doesn't find to get a better and better and better results. And so the key is that agentic loop. Okay, great. Tool usage is one of the most underused ideas in retrieval augmented generation. Instead of an unstructured text response to a query, we can give the LLM access to tools. Tools are just function calls. Things like traditional search, regex match, semantic search, and even direct file system access. An AI agent is an LLM that calls tools in a loop, and recursive RAG is just an AI agent. So a recursive RAG might have a loop like this. 1. Pick a tool based on the user's query. 2. Use that tool to gather more info. 3. Update the knowledge base with that info. 4. Repeat. The magic is in picking a tool and using it well. Say we have tools for keyword search and semantic search, and the user asks, "Find me scary bear movies that happened in a forest." The LLM might have a loop like this. 1. Keyword search scary bear. No results. 2. Keyword search scary or horror and bear. 10 good results. 3. Semantic search bear forest. 10 more good results. 4. The LLM re-ranks based on the user's query and generates a summary with citations. The important part is that the tool calls are not pre-programmed. The LLM decides which tools to use and how to use them. And based on the results, it can change its approach and keep trying. Now, you may wonder why we're not building the agentic search here. And that is because there's this build an AI agent course. And an agent is tool calls in a loop. And with this agent, you actually build everything you need. And so as you look here, you see an agent says a list of messages. This is what you actually build in this course. So take this course. A list of messages in a comment. It looks like this. Please fix the bug at calculator. I want to call get files info. Here's the result. I want to call get file content. Here's the result. So it can continue to call and look in a loop. And so this is exactly what the agentic loop is. Now, what is this tool? It could be grep. It could be ripgrep. It could be a semantic search. It could be a keyword search. There's all kinds of tools it could have. But the idea is that you build this agentic loop. And throughout this, you build a coding agent, which is a really great use for agentic search and tooling. So I would really recommend taking this course to learn about that. So what's not a benefit? Power to use tools that access all kinds of sources. So this is great. You could have tools that, for example, one tool could be a tool that takes in an image and describes the image. Maybe uses an image model and puts it into text. So if you have a text-based thing, it can kind of see images. Or it could convert PDFs to Markdown or URLs to Markdown to pass in. That's actually really helpful with agentic search. The flexibility to dynamically choose the best type of search algorithm to use. That's absolutely great. The ability to handle complex queries. That is another really nice thing. Fast response times is not a benefit of agentic search. That is agentic search is a lot slower. So I'm going to click that. Perfect. Okay, multimodal search. So one of the things we haven't covered is what if there is something other than text in the queries? So for example, if someone says, what should I do if my leg is turning purple? We might have an answer. If someone says, what should I do? And uploads an image of their leg, we have no visibility. We haven't handled images at all. And so there's multimodal models that allow natural language text and images to be mapped into the same space, which means then you can find similarity just like we would any others. But we have to create some way of mapping them to the same space. The first way that we're going to do it is we're going to use it kind of like query rewriting. It's not what we commonly think of as query rewriting, but it's the same principle. And so we can create a prompt that says, hey, look at this image and rewrite the text query for better search results. And so we can say, here's the uploaded image, here's a text query. We can send that to Gemini because Gemini is a multimodal model, and it can describe the image as it relates to the query, and we can send that on to our search or send that on with anything else because we have a description of the image. So this isn't exactly what we want to do in the end. We'll look at other approaches, but let's start with this because this can get you going pretty quick and can actually work decently well. Let's go ahead and build this. We're going to need to download this image. So let's go ahead and download it. We're going to call it paddington.jpg. We need a describe image CLI, and we need to set it up to take an image and a query. So let's start with that. So we're going to create a new file called describe image CLI.py. We know how to do this, so we can just take some from here. So the parser, we're going to call this image, describe image. We don't actually, I don't think we need a subparser because we can just do parser dot add argument directly because we don't need multiple commands for this. We're just going to do the describe the image CLI. We don't need this. And so we just need our -- image and our -- query arguments. The query, that is the worst pronounced spelling of query. It's definitely going to be a string, which is going to be the user query that goes with the image, the path to image for the rewriting. Cool. So I think we have some of that set up. Let's get this script. Let's make sure we can actually run it. Print hooray. args.image, and then we'll print args.query. And args can be parser.collect. What is it called? Args. Get ours, parse args. Cool. So let's just make sure we can run our script. Make sure I got all that set up right. So we can do uv run CLI describe image CLI.py, hooray, none. And if we say A, B, C, D, -- image -- query, hooray, A, B, C, D. Okay, so we've got the boilerplate set up properly. Great, cool. Use MIME types, guest type to determine the MIME type. Very good. So we're going to need to import it. Don't need this anymore. Okay, cool. So we can print the MIME so we can see what that is. But basically, we guess the type of a file based on this. And so you can see it maps particular types of extensions to there. And so this is kind of handy to do. So we got that. We need to open the image to read it. So let's go ahead and do this with open image as read in a bytes. So this is going to be args.image. Cool. So we open it to read the contents as f. And so we say we're going to have the image is going to be f.read. So we've got all that in bytes. We need our Gemini API client and a system prompt. So I'm going to go ahead and put the prompt up here. We could put it in our a prompt folder, but I think we can leave this self-contained because it's a very simple script and we're not going to reuse this query anywhere else. Set up a Gemini client using your API key. Build a request for Gemini by using parts and send the query to Gemini using the generate contents. So what we've done before is just send text prompts to Gemini. What we're doing now is we're sending a little bit more. We need not just the text, but we're sending other information as well. And so we can use this a little bit more complicated data type from google.genai import types. And we can see we have a types from bytes, which we read as bytes. So we can use from bytes. Here's the image. And then we can take the query and we just do a little cleanup, just strip it. So now we need to send the query on. We've got all the parts and we can use the client models. So we need to actually set up our Gemini client. Well, we've done that before. And so we can go ahead and borrow from here to load .env as well. OS from Google import GenAI. So I think that should cover most things we need here. And then we need to use this client to generate, what was it? To go into our models. I'm going to generate content, but you can see images and videos are options there. And we need the model to be equal to the model and the contents to be equals to the parts. Okay, so we can use generate content. And then we want to print the rewritten query and the total number of tokens used. Go ahead and do that. We need to save the response. Okay, so let's give this a shot and see if we could still run it. No such directory AB. Okay, that's really fair. We're still using the dummy arguments, and so we need to do the image and to the data paddington.jpg. And we're going to look for a bear in London. Rewritten query, Paddington movie, scenes with bear wearing blue duffel coat and red hat in London. So that's great. So this is the rewritten query, and we can use this for the search. And so this works. So let's go ahead and submit. Rewritten query, total tokens, great. Paddington, great. Okay, so that is the first way we can work with images in a multimodal way. Okay, lesson 2, multimodal embeddings. Image search is one of the most insane technologies that you probably use all the time, but never think about how it works. Searching for cute bear and getting back a bunch of bear photos because cute bear was in the alt description makes sense. But how does it work when there isn't any metadata at all? The surprising thing is that it does work. At least, it does now with modern multimodal search systems. The fundamental idea is that instead of searching for the associated text, we map all the text and images into the same vector space. The best way to visualize that is to think of a big map where all the text and images get their own coordinates based on their meaning. Then, when we search for a term like cute bear, we can find all the images that are close to that point on the map and return them. Even better, instead of a text-based query, we can actually embed a new image of a cute bear and find all images that are close to that image. Multimodal search makes text and images fundamentally compatible by mapping them onto the same space. Images are made of pixels, colors, shapes, and spatial relationships. Text is made up of words, syntax, semantics, and sequential patterns, so creating that mapping is a bit tricky, but it's a well-understood process in AI. The most common approach to use is contrastive learning. The idea is simple. The training data is made up of image-text pairs. Think images and their alt text, or Instagram photos and their captions. The model then learns through pattern recognition. It ingests millions or billions of these pairs and learns the words and phrases that tend to match certain shapes and color patterns. It's then able to make a shared numerical mapping of both modalities. So how do these models learn to map embeddings of text and embedding images to the same? How does it do that mapping? We kind of do it intuitively. If I see this picture, I know this is a picture of a bear. So I've done it. How does a model do it? These videos are also like super phenomenal, so you should watch them. So the idea here, if you look, we pretty much map text and images onto the same space so that we can do the same semantic similarity. So cute bear is far away from fat bear. It's closer to this one. It's far away from sexy bear, etc. So the way it works is we have paired data. When we train a model, we have to have some sort of pair. And so for text, we say, hey, here is an image and here is the alt text. And we can say these mean close to the same thing. And so we're going to try and minimize the distance when we're going to try and create some embeddings, create some numbers, and we're going to minimize the distance between this image, the embedding that this image creates, and the embedding that this alt text creates, because the text goes with the image. And you can do this with all kinds of things. So you can say, hey, let's get an image and the text around it in a news article or from a Wikipedia page. Alt text is one from social media. And so you have a photo and you have alt text that says a brown bear in the forest, and you can train the model to create embeddings where those are close together. And that is exactly what you're doing. And this means you end up with embeddings that use both that go into the same space. Let's answer the question. How do they map images and text to the same vector space? It uses something called contrastive learning. And so the idea is that you want text and images that are about the same thing to be very close together and ones that aren't to be far apart. And so the first step is you create a model that can create embeddings for an image based on the pixel values and embeddings based on the tokenized text embeddings from the text. The goal of the model is to minimize the difference between these related ones, the images and the text that they're related to. And so you get these related text-image pairs by things like an Instagram photo and the description there, or more commonly, the image and the alt text. The alt text that people have put into an image to a web page for accessibility reasons is used because that maps one-to-one. Then you use that as a learning objective to minimize the distance between, or the difference between, the vectors of the image and the vector related to the alt text. Okay, this is great. Okay, image embeddings. So we talked about how we get embeddings. We use contrastive learning to minimize them. So now we actually need to create embeddings. From our perspective, it's not a whole lot different because we're still going to use a model. We're going to pass it in to get these embeddings, but we need a multimodal model that can do both. One model we're using is CLIP, contrastive language image pre-training. It's a very straightforward name. And there's just a huge number of image caption pairs. It's going to work nicely. Now, local models are good to experiment with, but there's some constraints on size and capabilities. And so the model for ChatGPT is about 750 gigabytes. Most people's home laptops probably aren't going to load that into memory. And so that's why we use public APIs. If you use Claude Code, that hits an API on someone else's server. That's the same usually for Gemini, Claude, OpenAI, etc. The model we're using is easy to run locally, but it's super far from the state of the art. Jenna AI has a good API for multimodal search that you can use with minimal code. That's a good option as well. And you can see how that works. So let's go ahead and set this up. So we are going to add the Python imaging library, the pillow library, to your dependencies. Cool. So let's add that. Create a new library module for multimodal search. Multimodal search.py. So let's go ahead and do that. Multimodal search.py. And we're going to need a multimodal search class. We need to create a sentence transformer instance using, this provided model name. So here's an example signature. So let's go ahead and do this. So we need class. My memory is horrible, so I already forgot what I'm supposed to name this. Multimodal search. And we can do self.model is equal to our sentence transformer, and we can say model, and we can just pass in our model name. Okay. We're going to need an embed image to generate an embedding at a given path. So we're going to use image open. Let's just stub out the rest of the functions we need. So embed image, probably going to need an image file path, I would guess. Yep, image at a given path. We're going to use image.open. and pass it to the encode method. And then we need a top level function, verify image embedding. It takes an image path as input and creates instance of multimodal search, generates an embedding, and then prints the shape. Okay, so we have image file path, and we can do multimodal search, which doesn't need anything here. And then we'll do embedding is going to be the embed image. Why is this complaining? Embed image. And this will take in the image file path. Great. Embedding shape has this many. So let's go ahead and print that. Cool. And then we'll create a CLI for it. So let's do this. Image open, and then we're going to pass it to the encode. So let's look at image.open. A file path, image, a file name is supposed to be implemented like file read, file seek. So let's see if there's examples. So we're going to say image file path, and we're going to then do self.model.encode, and we can pass in the image, I think. And this needs to take in self as well. Okay, so here's what we did. We used image open to load the image. Then we passed it to the encode method, and then we're going to return the embedding. You can pass a one element list and take the first and only element. So we might need to wrap this in a list. I'm not sure that we do though, but let's just go ahead and return this. Okay, so then this returns the embedding. All right, so then we need to create a multimodal search CLI with a required okay, so let's create this. Cool. So let's go ahead and grab some of this boilerplate here to reuse. So this is going to be from lib multimodal search, and we're going to implement verify image embedding from that. Our argument here is going to be verify image embedding. So that's good. So with subparsers, add subparsers, add parser, verify image embedding. We can call this verify image embeddings load. And we're going to add an argument for, what's it called? What do we need to run here? So it just needs to be a required positional argument for the image file path. Image file path type string. Cool. And this is the path to the image to process. Okay, so then we need to use our parser to parse the arguments. And we can match, how do we do that? Match on args, is that right? Yeah, match on args.command to do that. And then, yeah, great. Okay, so we match on our verify image embedding. And in that, we need to do verify image embedding, and we pass in our args.image file path. Leave it at that for now, and we can say equals main. We can run our main entry point app. Okay, let's give this a shot. We'll give it a shot. We can grab our command to run it, make sure it works. Already didn't. Okay, did you mean... Okay, embedding shape, 512 dimensions, so we know we got it. All right, I think we're in good shape. So we have our embeddings from our model. All right, awesome. We are just about ready to do a true multimodal search. Okay, multimodal search implementation. So we've got our embeddings, our movie data set. So let's search our movie data set with the image. Yeah, so, okay, so what are we going to do here? We are going to upload an image and some text. We're going to encode both pairs. The image and the text are both going to be encoded. We're going to combine the embeddings with a weighted average. We've already made the embeddings into the same space, so we can do that. We can weight which one. We don't necessarily need to do that. And then we're going to, then you can search. And so, okay, so implement image-based search to find movies. We're going to update our module to do this. So let's get started. We have a multimodal search constructor, and we also need it to assign a list of documents and assign it to a variable. For better search, we can create a self.textlist which concatenates in the following format. So we said we need a self.documents, and we need a self.text. We're going to pass in the documents, I think. Those are going to be our movies. So this is going to be documents. This is going to be a list. And we can go through our documents. For our doc in documents, we can append to our text, self.text.append. And we know we want to append this doc title and this doc description. So I think that's what we need. Okay, I think we're good there. Still in the constructor, generate a text embeddings by putting text into the models in code. So this is where we actually embed all that. Boom, boom, boom. Self.model.encode our texts. Okay, and we'll use that show progress bar of true. Okay, very nice. I think we're in good shape there. Add a new search method, search with image. We're going to generate an embedding for the provided image and iterate over the text embedding, calculating cosine similarity. Boom. Search with image. So this is the image file path, and we'll use our limit of 5 we've been using. We have our embed images that opens the image and encodes it. So we need our image embedding, which is going to be self.embedImage with the file path. No, just that. We need to calculate some sort of similarities. That means we're going to need to go through all of our text embeddings because these were based on the text, the movies, right? We did the title and description. Let's go through for movie embedding in our text embeddings. We'll call it text embeddings just for consistency. Text embeddings and text. We're going to need our cosine similarity. So we defined our cosine similarity somewhere. Cosine, here we go. So we can import that from our semantic search, from lib semantic search, import cosine similarity. And we want the cosine similarity between our image embedding and our image file path. Similarities.append that. Image embedding? No, that would be pointless. Image embedding and the text embedding. So then we need to sort this. So we can say sorted sims is equal to the sorted similarities. But we've kind of lost. So after we've sorted it, how do I know which movie this goes to? We don't really. So let's keep track of an index. So then we can actually append our index with that. So that means when we sort this, we now need a key. So lambda x, and we can say the key, we want to sort it on the cosine similarity because it'll be already sorted by the index, but this makes us keep it. And we want it in descending. So we want to reverse true. We don't want an ascending order. So then we need to get our final results somehow. And what are we going to do? Let's go take a look at the instructions. Okay. We generated embedding. We iterated text embeddings, calculating cosine similarity. We sort the results by similarity score in descending order and return the first 5. It will be convenient to return a list of dicts, each containing the ID, title, description, similarity score. I agree with that. Really, we only need. So somehow we need to get to the title, the description, ID, title, description, and then the score. Okay, so I need to get all this information. We've of course got the ID and the score. So how do we get to titles and descriptions? We have the documents. Okay, so for result in sorted sims. So for one of our similarity score values, we're going to go through and we can do self.documents and we can say sim0. Because this similarities is a tuple, which means I can go index and score, which means this now just becomes index. And so now I can append results.append a dictionary of title being doc title, description being the doc and the description. Okay, so this is cool. The doc ID being the index, and the score being the score. So now we've got this in order. We've got all that information. I'm pretty sure we can just return this now, maybe, but we'll probably need some sort of format to print it. So let's see what it says there. Okay, add a new type level in the library module, image search command, because we're going to be using, okay, so we need this image search. Yeah, let's build this in. Image search command. And we're going to do the search with image method, and we have a particular format to print in. Okay, cool. So this is going to take in some sort of image file path, I believe. Whatever this takes in, and a limit. Oh, so I did that. That's no good. Okay, so that should be limit. Okay, so that's better. And a limit. We'll just default it to 5 for now. And what I need to do is, let's see here. I need to go from lib.searchutils import load movies. Oop, don't need that. Okay, so I can do movies is equal to load movies. My multimodal search can now be created with my movies. And then I can do my search with my image file path, and I can pass in my limit. So this can be the results. And then I need to print. So I can go for R in my results. We can print. We need an index here, enumerate. And we can start this at 1. So this gives us a index. And this looks like a title. And this looks like a similarity colon the score. I think that's what I did. Yeah, score here. And then underneath here, this is R and then description. And I'm just going to truncate it to 100 or something, so it's not too much. And I think we're good there. So let's do the image search command. We're going to need to bring this in here. Not that. The multimodal search CLI. Okay, verify image encoding. Here we go. I think we're going to need to run a command called image search, case image search, which is going to basically run the image search command with args.filepath and args.limit. Limit. This is an integer number of results to return. Path the image to process and to search with. And then this is also going to have to be the image search for movies based on an image. All right, so let's run this and see if we have a successful run and work through any bugs we might have. Okay, so let's see. The following arguments are required. Limit. So let's do -- limit. Let's put a default here. Namespace has no attribute file path. Okay, because this has got to be image file path. Okay, so we've got it. We put our image in, and it found Paddington, and it found other movies that were kind of similar. So that's cool, in the same style, but Paddington was what was put in, and that was the first. So we can clean this up just a little bit to only give us the 4 places. But you know, I think we're in pretty good shape. So it says 309 is what it's expecting. 309 is what we get. So that is really, really, really great. So let's submit and see if we're passing. Expected contain similarity 309. So why did that not work? Similarity 0.309. Is that not the same thing? Similarity colon space. I gotta go to three of these, not 4. I see. All right, so this is great. So we just completed the entire curriculum. So we have gone through and we have done everything from keyword search, semantic search, hybrid search, chunking, re-ranking. We did query rewriting to inject LLMs in there. We did RAG. We evaluated the system. We talked a little bit about agentic search, and now we searched with movies. This is everything, guys, and this is a really, really strong foundation. So if you made it to the end, that's awesome. I don't know if we get like, maybe the editors will put in like confetti or a bugle or I don't know, disco ball, something. But this is great. we've made it to the end, and thanks for joining.